everyone. I don't think there's anyone here yet. Oh, hey, here
we
we
have
go.
2 more participants.
Wow, people get up early on the weekend. I'm just gonna double check this stream.
Yes, morning everyone. We are just setting up at the moment. Oh.
That me or you? I don't.
Muted. There we go.
Oh, no worries, no worries. I'm just checking the stream, and it looks like we are good to go. Look at that, 4 guests already. Yeah, 9 a.m. on a Sunday morning. Fantastic.
Good morning, everybody. Yes, we'll go live properly in about 5 minutes. We're just getting going.
Just setting up, having the good old tea and coffee and a biscuit.
I need more coffee. I'm off to do that later.
Exactly. Slowly waking up myself. I'm glad at the moment Leicester's weather is a bit cloudy, though I should stress I think we may have some more questions like this later on. We're not actually taking the observations in Leicester, as you can, I don't know if I can move the camera very well, but it is pretty sunny out there. We're actually taking our observations in Hawaii, which at the moment is just gone past 10 o'clock in the evening. So we're right in the middle of nighttime for them.
And I should say also, we'll come back to this, won't we? But I checked earlier, and Hawaii is 11,650 kilometers away-ish, depending on where and the telescope is 4,200 meters high. It's right above most of the denser layers of the Earth's atmosphere.
Yes. I was going to say, I could probably show just this slide, which kind of shows this has got the cameras that are on around IRTF, specifically the Gemini telescope, but IRTF shares the same kind of space. Just seeing, you're not seeing you, I'm just seeing a static image. It's just changed. Okay, sorry about that one.
Yeah, I'm seeing you okay, so I don't know, it might be a local connection issue, I'm not sure.
That's no worries. I said, if it does change, just give me a heads up. That would always be appreciated, audience.
It's just changed, they've said, so it might just be a
nice. But yeah, so hopefully we've got spotlight on my second screen at the moment. I'm just going to confirm on the other one that is in fact the case. Yes. So here we basically have various cameras that are on Mauna Kea. These are time lapses, are about, I think, 12 to 14 hours at IRTF and Gemini, and gives you kind of good ideas. Robert was saying that we're very, very high up in the sky. You can probably see it best in the view of Helio. That's the nearest town/city where Mauna Kea is, and you can see like all the cloud is kind of wisping over the top of the city itself, with there being a massive amount of glow from the city itself. It's quite impressive. But it's a sight to see. I'm really hoping at some point in my PhD that I will be able to go over there. Unfortunately, the pandemic hit just into my first couple of months of my PhD, so I wasn't able to get a proposal in time to go over there. So me and Tom have discussed this, and we're hoping perhaps in the future, even if it's the very last week of my PhD, that I can travel over there for at least my first and last time on the PhD.
Well, we're getting ready to start properly, Emma. Yeah, I should stress so that this is in the weird and wonderful world of Zoom that facilitates these things. So I'm in Bristol. We've got people right in Aberystwyth and Leicester, all connecting to a facility in Hawaii.
Yeah.
And presumably, from what I can see on it's not clear where everybody is in the world is watching, but I can see on YouTube at least, people.
Good morning, this is Lucinda. Just checking in here. Emma, I wanted to ask you, I've got your screen up on YouTube, but I don't have your pictures, either of your pictures in the upper right-hand corner when you guys talk. Yeah, I'm changing the view on Zoom, but
I can add spotlights, but it will mean that the view from my second screen will probably be part of that, because it's for everyone at home, essentially my second screen is a virtual camera, so similar to everybody else's camera.
That's what it was. It's because normally when I get started, I show my slide, and that's why our pictures show up. So, all right, yeah. So just when you spotlight your slide, we don't see anyone. But in Zoom, I can change it to gallery. So Robert, there is a attendee view in Zoom. So you can switch what people who are attendees see. So if you hover in the upper right-hand corner of the black space of Zoom.
Where it says view there. Yeah.
Yeah, does it say attendee view and then speaker?
It does, yeah. So
Excellent. So you're in control of what the attendees see there, and sometimes they'll let us know we can't see you guys, so, which is really cool that they tell us that. So
yeah, no, we appreciate that.
And then I'll know that oh, they're not seeing what we're talking about or something. So have a play with that.
That's fine. Okay, I think as long as people can see and hear us, and when the presentations are up, see those things, it's the main thing. As long as everybody hears us as well, actually, that's the crucial thing.
Yeah. So for instance, I can see you guys on Zoom right now. I'm George. I'm in the audience as George, so I can watch you guys and make sure things are going well. Okay, so I'm gonna head out. I would say have a great day, everyone, and we've got a really good following right now, both on YouTube and on Zoom. And you can contact me anytime if you need anything.
Thank you. All right, we will. Okay, thanks, Lucinda.
Yeah, thank you so much.
Should we start properly, Emma? Let's do that.
Yeah, that'd be
fun.
fun.
On a Sunday morning, I have to say. Yeah, so I will look up my documents here. Right. This is the fascinating thing about controlling this. It feels like sort of flying a jumbo jet using a laptop, actually, which I guess to some extent is what actually happens. So, good morning and welcome to day 3 of the weird and wonderful world of Uranus. This is a 3-day live stream, and we are connecting with people in the UK, various parts of the UK, and also with a remote observing facility in Mauna Kea, Hawaii. So the whole point of this is to really enable you to find out how professional astronomers work, and to find more out about Uranus, one of the ice giants, so, way out in the solar system, twice as far away as Saturn. Now, I will introduce some of the other people we're with in a minute. I should say I'm Robert Massey. I'm Deputy Executive Director of the Royal Astronomical Society, and we're the UK body representing professional astronomers in the UK and also around the world. We have quite a lot of members outside the UK too, and amateur astronomers as well, actually advanced amateurs and people who have that professional interest in the subject. So we're going to be watching astronomer Emma Thomas, who is a third-year PhD student at the University of Leicester, and she'll be working with the H3 Plus astronomy team. You're part of the H3 Plus astronomy team, aren't you, Emma?
Yes. So the H3 Plus astronomy team is a team of scientists or physicists or space astronomers, we get many names, who will basically explore and observe and investigate infrared aurora at the outer giant planets. So that's Jupiter, Saturn, Uranus, and hopefully Neptune. That is still an ongoing investigation at the moment.
And also the nice connection for us with the Royal Astronomical Society is that Uranus was discovered. It was the first planet to be discovered basically after the invention of the telescope, and the first planet to be discovered since the Neolithic or the Paleolithic period, because it's pretty obvious that ancient peoples understood there were objects in the sky that moved. So the bright planets, everything from Mercury to Saturn, are very obvious, and they're bright. They're bright. They move compared with the other stars. So people always understood them as wandering stars, as things that weren't like the constellations that they saw. But so Mercury through to Saturn was all we had, and then in 1781, astronomer William Herschel, working with his sister Caroline, who was instrumental in this as well, found Uranus from his back garden in Bath, so actually just down the road from where I am. And the nice connection for us is that he was also the founding president of the Royal Astronomical Society. So all of this is more than 2 centuries old, 250 years old since Uranus was discovered 240 years ago. And our society was set up 200 years ago, back in, our bicentenary was in 2020, and we've been rather delayed in our celebration.
Understandable.
So we'll be introducing people like Emma. I'm just checking the bio for Emma as I scroll down. I mentioned she's a third-year PhD student, and your research is to investigate and document the Aurora at Uranus. Who knew that Uranus had northern lights as well? We're doing this because it's World Space Week, and this year's theme is Women in Space. I think it's fantastic. We've got someone like Emma who has been running so much of this event over the last 2 days and as well.
Well, thank you very much.
We'll also, I should also mention that we'll be taking. We're very happy to take questions throughout. I can see them coming in on YouTube, see them coming in on Zoom. Just type them in the Q&A box if you're on Zoom or in the chat on YouTube, and we'll try and answer as many of those as we can. So at this point, I guess I should hand over to Emma, if that's okay.
Yeah, I was just going to go through today's schedule. So hopefully that's now come up on the Zoom. Yep, I can check that on the second screen. The wonderful things of technology of having several devices. So I can check.
I'm feeling it too, yeah.
So today's schedule, we have, at the moment, we started at 9 o'clock-ish, and we're just setting up. So we're now going through just kind of the scheduling as we're doing this. About 9:30, I'm going to be discussing the science that we're doing today. If you were here yesterday or even Friday, you're probably going to hear very similar themes that we touched up on. But I am hoping to at least add something new, which is I will discuss some of the science that we got from yesterday and what I think happened, kind of the theories that we had from our observations from yesterday. At 10 o'clock, I will then I will hopefully get back in touch with the observing team, and we will see where we are in terms of observing Uranus, anything that we have spotted immediately, any issues that we're having. To my knowledge, the weather at Mauna Kea is pretty good for observing today. We were initially worried at the beginning of the week because they said there may be clouds and precipitation, which are two things we don't like hearing when it comes to ground-based observatories, but it's looking pretty good. At about 10:30, we will be having Dr. Sarah Casewell coming in to discuss about brown dwarfs. But the link here is actually Dr. Sarah Casewell is in 2 days after ourselves going to be using IRTF telescope as well, but to observe brown dwarfs. And we thought it'd be absolutely fascinating to hear about different science being done, but with the same telescope. There are so many different telescopes in the whole world, and it always seems like there may just be one that does one specific thing, but actually all of the telescopes cover such a wide a range of science that goes on within our, the whole world itself. After Dr. Sarah Casewell, we will also have quite a Q&A with Sarah. So if you have any questions for her while she's giving her talk, please feel free to use the Q&A button in Zoom or post those questions onto YouTube. After Dr. Sarah Casewell at 11:15, we will then have a telescope view with, again, checking in with myself and perhaps Dr. Tom Stallard will be coming back. We have a bit of a discussion on that before going to Dr. Sian Prosser's video, I believe from Saturday and Sunday. We'll kind of be touching it and being able to see a lot of things from William Herschel. I know we saw a lot of documents and books, as well as some of the star charts from Caroline Herschel, I believe, some of her annotations, if I recall correctly. Lastly, for this afternoon here in the UK, we then have the Bath astronomers who will be getting in touch with us, and we'll be able to kind of discuss regarding, obviously, there being the discovery, as you were mentioning, Robert, 240 years ago, of that of Uranus, as well as touching in base with William Herschel, as well as Caroline Herschel, and getting more information from that from the Bath astronomers, I believe. And then we're getting to the very end part on this. So 1:30, we'll again touching in with myself and Dr. Tom Stallard. Hopefully we'll also be having Dr. Rosie Johnson, who is another member of the HD Plus team, who will be giving a talk of their work with Jupiter's Aurora using very similar techniques that we're using here on IRTF. Again, very similar to our previous days, we're going to be doing a Q&A with the H3 Plus team. So if you have any questions that are about Uranus, about observing gas giant planets, I think that'll probably be our best time that we will be answering these questions. So if we don't get around to answering them beforehand, we will do our best at 3:15 onwards. And then at 4:15 to about 5 o'clock-ish, we will be doing our last round off of the day. That's around the last hour of our observations here here at Leicester, but on the mountain for pretty much the whole campaign that I put in for. So this will be the last day for the proposal that I've put in for.
It's fantastic stuff, Emma, and I was going to say we've had some questions we had from yesterday that might be interesting to talk about. I know one of them earlier on we were chatting and was why is there no rocky surface on Uranus, I think was the question, which I know you pointed out wasn't quite your area of research, but I'm going to blag it slightly because in our podcast a couple of weeks ago, which I do recommend to people watching on the call, we were talking about ice worlds and we included the ice giants, so Uranus and Neptune. And the idea is, I think, and you can, someone with more knowledge can jump in by all means, that they do have rocky cores. that all the planets formed around some rocky core. But in the outer solar system, they were able to hold on to more of these lighter gases, hydrogen and helium. And so if, in theory, it's whether you define it as a surface or not is a good question. But if you dive down deep, 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 deep into the atmosphere, I guess deep down it becomes more liquid, though. Is that right, Emma? Before you hit that solid surface. And you'd be crushed and all the rest of it, so you wouldn't actually get there. But but there is a sort of surface deep down.
Exactly. Oh, no, we did have some excellent questions. I saw somebody ask yesterday if did we have a date for when we could have humans go out to explore Neptune and Uranus and even Saturn and Jupiter, and I was there going, my first mind was like, oh, well, we can't put people on there because if you try and put people on those planets, they're just going to keep sinking through the atmosphere.
Yeah,
so it wouldn't be a very good mission. But it'd be also if we could have people just be able to be in an orbiter almost and be able to almost like an international space station, but for a planet, you know.
You know, Emma, I mean, I know that when you said that sort of human exploration of Jupiter's moons, for example, is pretty problematic because it's got a lethal radiation belt.
Yes.
So is that true for Uranus and Neptune as well?
I would imagine so. I mean, it's difficult because I don't know too much in terms of the human side of things. I did a very quick internship program as well as elements in my third year because we were looking at constructing an instrument to take C. elegans, I think they're called. That's the shortened Latin word. I think there's a much more complicated Latin word that I can't remember, but they are like 1 millimeter sized worms, very similar to human cells. That we were looking to basically contain like a small little pot of these and take them to the international, actually not even international space station, taking them to Mars to actually see the effects of how radiation and the Martian gravity and just the space environment of Mars would be on the worms themselves. So I can only imagine, the kind of effects that you would expect at the ice giants. Yeah, I think it's a part of two parts. You have to remember with Jupiter, there is the Io Taurus, and that has an incredible amount of plasma. And the most dangerous thing with anything is if you have something that's high energy, because anything interacting with yourself that's high energy can cause any kind of damage, or anything that is ionized will also cause a lot of damage to yourself. So Uranus, unlike Neptune, I think Neptune does have, I can't remember which moon, but I do think it has one of the moons that does eject plasma very similar to that of Io at Jupiter, I think.
Triton, isn't it? I think Triton
I think so,
is
yes.
the cryovolcanic moon, isn't it?
Exactly.
And it has geysers. I think, yeah, they saw nitrogen geysers, and that's all based on 1989 work.
Yes, with Voyager 2, yes.
Sorry, go on.
That's okay. My ending point was just going to be that, yeah, Uranus doesn't have that, to my knowledge. I don't think we've seen any volcanoes on its moons, so we don't have that to contend with.
It's yeah, and I was thinking with this actually that I remember back in 1986 I went to the Herschel Museum. This is I'm guessing quite a long time before you were born, and which also shows how long it's been since we sent a mission there. And I remember they had, this is obviously pre-web, right? So they had printouts you could get for free of the NASA images. And the one that always sticks in my head forever really is the Miranda one. So Miranda is this wonderfully misshapen moon. And when you do the calculation, it has, I think the cliffs are 20-kilometer high cliffs.
Yeah.
And you could jump off them and land at a reasonable speed. You could have sort of an air suit or something, presumably you'd be wearing a spacesuit anyway, and land at not too high a speed. So you can imagine being able to fall 20 kilometers. So I was more thinking of the space tourism opportunities in 200 years' time.
True. I mean, goodness, the amount of stuff that we could have if we could just go and, I don't know, take a tourist trip for like 2 weeks to Uranus, that would be great. But we did mention yesterday, I guess it kind of leads into it a little bit, is if we send anything towards Uranus, I can't imagine with people on it, probably would be a bit slower, but any kind of orbiter or any kind of mission is going to take 15 years to get there. So your 2-week holiday may end up being a 20-year there and 20-year back holiday.
Long sojourn, isn't it? Exactly. Yeah, exactly. That's the problem with all this. So what other things do we have? We had an obvious one, which, so how can you observe Uranus when it's daytime here, I think they mean.
Oh, that's a good question. We had this on Friday, and it's totally understandable. So the images that we have just here in my second screen. I don't know exactly where that is. It could be up here, it could be down here. I'm not sure where it's come up. So the images that we've got are actually through remote sharing of the screens from the telescope on Mauna Kea, which is in Hawaii, which is off in America. So off in America at the moment, they're currently still in nighttime. So at the moment, we're now about 10:30 in the evening for Hawaii, or Hawaii Standard Time. So whilst it's here, it's nearly 10 o'clock in the morning for us, and it's nice and shiny day. We're actually looking up at the night sky and Mauna Kea instead, so that's where we can actually look at Uranus, because yes, trying to look for Uranus in the daytime sky is almost impossible.
That would be an interesting challenge, actually. Yeah, yes, I'm sure there'll be some amateur astrophotographer there that's done this, but it's not a good. It doesn't make it easy, does it?
No, certainly. We wouldn't get the same data that we need, which is, as I said, we're looking specifically for that infrared wavelength. And yeah, we would just get blinded by the sun, and most of our instruments probably get damaged if we tried.
So another question, I think, that I'll ask one, and then I've got one I was going to ask you, which is, so one is, are there any plans to send an orbiter to Uranus? Now, I've heard missions discussed, and I don't recall what stage they're at. Is this the sort of thing maybe mid-century or something?
Yes, so this is kind of touching up. So on Friday, we had Dr. Lee Fletcher come in, who was one of the hosts for the Ice Giants conference, which is essentially a worldwide conference where we invited as many scientists that were involved with ice giant science to come along and try and form a strategic plan of how we could try and get a mission within the next 10 to 15 years. We are in the next, I'd say next 20, 15 years, getting to this point where we are at the best point to be able to send a mission out to Uranus or Neptune.
Why?
So that one's a good question. I think that is the geometry of things, and just trying to ensure that we're not having to spin a mission as past as many planets as possible to try and achieve where we need to.
Is this one where you use a Jupiter gravity assist or something like that?
I believe so. We would be wanting to use a Jupiter gravity assist. But the other, it's the frustrating thing with using missions. The other things you have to remember is obviously there are costs. So we have to try and be as minimalistic with the fuel and the amount of acceleration, because we want to try and focus as much as possible on the instruments, because we want those to last for as long as possible. A good example of that, I suppose, is with Juno. Juno, I think, was supposed to have stopped last year, if I remember correctly.
Tell the audience what Juno is.
Okay, apologies. So Juno is the satellite that is currently orbiting around Jupiter. It is very similar, for anyone that can remember, the Cassini orbiter that was around Saturn. And basically, Juno is our best way of getting pretty much as close to surface. Sorry, there's a quick update that's happened on the other computer. As close as view as we can at Jupiter. So at the moment, Juno is using instruments, ultraviolet spectrometers, visual spectrometers, visual cameras, visual images, as well as other instruments that can detect Jupiter without having to have the issue that we're currently having, such as trying to look through Earth's atmosphere and other, trying to look through Earth's atmosphere, and it doesn't have to contend with clouds or weather. For some instances, it can just, for an instant, just take everything that's coming in from Jupiter. And we've, as I think Tom was saying yesterday, there is so much that we have realized that we didn't actually fully understand. We thought we had a complete understanding of how Jupiter's magnetic field arrangement was, and now actually looking at it, we see that the magnetic field is a lot more diverse in its shape.
So anyway, so for Uranus, we're probably looking at another, say, 20 or 30 years before we see a mission arriving, you think?
Yes, so Lee was mentioning between 2030 and about 2035 is probably the key launch time, and then it would be 15 years later before we could get any data. Like, that's the first part of data.
Do you
full
know off
stop.
the top of your head how far away Uranus is right now?
Yeah, so Uranus is about 19.8 AU, and when I say AU, I mean that's the distance between Earth and the Sun. I do have in my little presentation how far that is exactly in kilometers and miles, but I can't remember it off the top of my head.
By my calculation, that's then 3 billion kilometers.
That sounds about correct. Yeah, I think I have that down.
And when
it's a staggering amount.
you think the moon is 400,000 kilometers away, imagine. So that's what, 6,000, 7, 8, maybe 9,000 times as far away as the moon.
Yeah,
that's a long
it's a
way.
considerable distance.
That's why we're not doing space tourism to the outer solar system.
Yes, exactly. But unfortunately, regarding any kind of mission that's going on at the moment, Tom Stallard, who hopefully will be joining us at some point, was part of a leading team that was trying to push for a mission known as Trident. I'm going to make sure I say that because Trident was going to be looking at Triton, as well as looking at Neptune and trying to take a key window that was coming up with Neptune. I think there was an alignment with doing a Jupiter gravitational assist. And that was kind of our big focus if we could get something done in the next year or two to kind of push to start getting things going. But unfortunately, that lost to, I think we now have 2 Venus missions that are heading off in its place, which I'm happy that they do have the missions. I'm glad that we get to understand more that is going on at Venus. Obviously, it being such a close neighbor planet, it is fascinating to understand why Venus has turned out the way it is comparatively to that of Earth. So I do appreciate that there is science that we need to go on, but it is disheartening, as you said yourself. I'm of a generation that's never seen a mission go to the ice giants, and it is saddening almost in a way to hear that it will be at least 40 to 50, 40 years, possibly more than that I would ever get to see the actual results if a mission started today, because they would need the time to obviously start preparing and getting all the instruments ready and then send it off and then make its way to Uranus and then turn everything on.
You're being pessimistic, Emma. Maybe a mid-career coup will be fine.
Hopefully.
So my other thoughts. So yeah, we should say as well that actually, so you look at that classic diagram of the solar system. So the giant planets are, as Emma said earlier, Jupiter, Saturn, Uranus, and Neptune. These are the worlds that Jupiter and Saturn we've had missions to more recently, but Uranus and Neptune are just so far away. It's so hard, and I think that's why it's taking so long. But I was going to ask you, have you ever seen Uranus through a telescope yourself?
Oh goodness, that's a good question.
Curious about
so I never actually got around to buying my own telescope. Unfortunately, I never really had the funds to. My father did have a telescope, and I would ask him if he could show me one of the planets through the telescope, but unfortunately, we never got it completely running. So I wasn't able to actually see it. I haven't seen it entirely by myself on a telescope, and I'm sure that's probably something I need to be looking into, especially as everybody that I know is like, oh yeah, I'm looking at so-and-so the telescope, and I'm just
good. I think it's not too hard to see. I think I saw it. When did I see it? I think I knew amateur astronomers had very good telescopes who showed it to me. I also looked at it when I went in Greenwich with the telescope. It does look like this tiny blue ball. But it's fantastic. It's fantastic. You realise you're seeing it. I think it's, well, I don't know. I'm probably easily swayed. It's very evocative. But right now is a good time to look for it because it's quite high in the sky in the northern hemisphere, and it's not far off. I think I should really remember this as I was talking about it in this podcast. But it's near opposition. So if you're going to do it, if there are any amateur astronomers out there that want to help Emma see Uranus for the first time, put it in the chat and we'll connect.
Always appreciated. Worst case, the University of Leicester has their own mini observatory for the students. Yeah, exactly. So I just never got a chance because I ended up in, accommodation-wise, I was on the other end of Leicester than where the observatory was. And unfortunately, the buses don't run that late at night. So it's either I take a very long hike home after doing the observing runs. But it's certainly on my list, and I'm no longer in student accommodation, so it makes it a lot easier to do anything.
No, that sounds great. Yeah, I mean, I won't say you'll be disappointed, but it's very small.
Oh goodness,
but the satisfaction,
yeah.
I think we would love to see the selfie, or the not, you know what I mean, the mobile phone shot through the telescope.
Exactly. that would be great.
So I think I'm just looking to see if there's any other questions coming in as we move through this. I've got lots of people saying hello and good morning,
Yes.
which is really nice. So
yes,
nice
good morning and hello, everyone.
And we've got, and later on we'll be moving over to the telescope in a bit. So I'm just thinking through this. What drew you? I mean, are you sort of someone who is a kind of planetary scientist across the board, or was there a particular fascination with these very remote worlds? You know, something about them being so sort of unobtainable on the far edge of the solar system that draws you to them?
Yeah, that's it's an interesting question, because whenever I hear this with other people, they always have such majestic answers, and in my head it's very boring. I was saying back when I started my undergraduate degree at Leicester, I went in just with physics because I was there like, I find all of physics really interesting. I'm interested in knowing what's going on with quantum mechanics. I want to know why some molecules want to bond the way that they specifically do, and why it leads to physical properties. I wanted to understand what was going on with the construction of space instruments. I was just generally curious, and I thought, hey, university is probably going to be the best place if I have these questions to be able to ask those kind of questions, or have them probably straight away answered, which a lot of them were very quickly answered. They are a lot of lectures already deal with a lot of questions. They know what the ones that always come up, so a lot of them got answered. But I came into the degree, and unfortunately, I was really bad at mechanics. Don't ask me why. I just can't get my head around just, you have a speed here, you have a distance, what's the time? I'm not very good at that. And it sounds silly because I know a lot of people who are like, well, if you can't do that, how are you going to be able to do any other kind of physics? Like that's your building blocks. But I found it a good challenge. I kept trying to do as best as I could. I still did really badly in it in my degree exam. But what kind of helped spur towards this line was that I just had an amazing knack when it came to electromagnetics. I found them really fascinating, especially as it was kind of like, here are these invisible forces almost that are just throughout our whole universe. Like, it wasn't just on Earth. Like, you can see magnetic poles out in the solar system with magnetic fields. You can actually see how, you know, there are currents in our surrounding environment, but also in the entire solar system itself, and even outside of our solar system. So that fascinated me, and I went along to Professor Emma Thomas's optional lectures in first year, getting a good idea.
Professor Emma Thomas is our current president, and she is a pretty distinguished planetary scientist.
Exactly. So I learned a lot about what was going on at other worlds with the electromagnetics, as well as we had a good couple of other optional lectures that were discussing I think the best way to describe it is, especially with third year and fourth year, where you start getting a bit more focused in terms of the or kind of the direction you want to go with your area of science that you want to pick for. I went specifically for Professor Steve Milan's options. Steve Milan, who is an amazing Earth-based astronomer, he is looking at the magnetic fields as well as the currents and understanding what's going on with the current systems at our own planet. But he has an amazing course that kind of runs through how electromagnetics works at our Earth, and I loved listening through that. I took on Tom's third year project, which was essentially this project, which was looking at Uranus, but it was looking at one data set that Tom had taken from about 10 years ago and trying to find out any information from that. I got really hooked. I loved trying to work through it. So it was kind of in the back of my head when it came to figuring out what I wanted to do for a PhD. Sorry, Robert, go for it.
No, that's fine. No, I was just thinking, actually, sorry, also my video disappeared. My wife was just kindly bringing me a cup of coffee, and I don't know if she was wanting to be on YouTube, so I couldn't turn off my camera. But no, I was just thinking, actually, it was interesting hearing what you were saying. I actually found mechanics okay, but things like statistics and MHD stuff, magnetic field stuff, was almost all seemed a bit like magic. So I do struggle sometimes with actually how it fits together. I was wondering, I mean, it sounds like a fantastic path to take you into what you're doing now, and I assume, is it fair to say that you want to go on to become a planetary scientist? Are you mulling that over in your head, or like you're absolutely engrossed in this stuff?
That's right. It's a good question. So it's interesting because academia itself, or especially looking towards research in academia, is a very difficult path, at least from my understanding of things. These days, you need to have at least 2 postdoctorate positions before you can then be considered for fellowships, or even further than that, then looking towards being in places where Tom is, for instance, and other lecturers where you can, I believe, then that's when you start being officially with a university and doing research with them. So it's a very steep slope. And it's not one that I'm looking at the moment, but it's not to say that I'm going to step away from research, like being an astronomer, or stepping away from research. I absolutely love research. It's one of the main reasons I came back, because I actually took 2 years out from my undergraduate degree and then came back to do a PhD. And I remember just all the way through that time, I went along to a lot of meetings, a couple of them held by RAS, but along with the students. I'm going to forget everyone's names and things, but there's a student version, one that specifically was looking at careers and stuff. And I remember I went along, and one of the presentations, somebody was just showing their raw data and how they went about analyzing it. And I remember at the time being like, man, I didn't appreciate this when I was an undergraduate. I didn't appreciate because I had a deadline and I just wanted to hit that deadline, and I was getting so angry at the code because it wasn't working. And I'm looking at this going, man, I actually want to be angry at code because I know I'm making progress somewhere. I'm going to be finding something out. So yeah, that was kind of the point where I was like, you know what, yes, I do want to take on a PhD of things, and hopefully I'm hoping in the future that I can kind of still stay with the research side of things, but it's gonna just depend where I end up getting placed. The idea at the moment is to go off into industry. There is the space park that is currently, I think, being finalized here at Leicester. So that would be very exciting if I could kind of partner up.
Any potential employers watching?
Yeah, that would that would be great. I've still got about 2 years, so my CV won't be in anybody else's letterbox for a bit, unfortunately.
I mean, I think it's still a fascinating career path, whatever you end up doing. I know, for example, there are companies like Airbus that, as I'm sure you know, make space probes in the UK and so on.
Exactly.
So maybe there might be a fantastic opportunity there. I was also thinking, if you, bearing in mind this is World Space Week, and particularly, that the theme is women in space, if you have any particular advice for people to want to consider this, because I think what you're describing sounds really sensible, which is, you're not ruling that much out. It's kind of, it's like sort of going into it, enjoying it while you do it, which I think is absolutely the priority for any career path people follow. Do something you enjoy. Absolutely. Sound advice. But whether if somebody watching this is, say, I don't know, 15, 16, and they're thinking, well, Emma seems to have quite this really cool role where she's controlling stuff in the wire and explaining it to the world, what advice would you give to them about the next steps they should take?
Oh goodness, that's a good question to put me on the spot with. I'm trying to imagine myself at 15, 16, which I remember at the time just being like, I'm going to university, and that's all that's going through my head at that point. So I guess the big ones are, I'd say do what you can. Okay, this is a big one, especially if I could say to myself back at 15, 16. There is so much stress when it comes to trying to get to university and trying to get to the right place and trying to tick all the boxes you possibly can when it comes to A-levels, when it comes to all the outside activities, all the clubs, all the languages that you can learn, the musical instruments that you can play, with the amount of books that you can do, obviously you've read. If I could say something back to myself back at 15, 16, it would be to say, yes, it is good to have the A-levels. Those are definitely very useful when it comes to the universities, but I would say it is not a make or break if you cannot get into the top universities. Remember that all universities have their own specialisms. And just because you've made it to the top university doesn't mean you're actually going to get a university that is going to be specializing in the area that you're interested in. So for instance, for the UK, Oxbridge is the big one, and my high school was very, very big on any students that got into Oxbridge were kind of the A-listers of the year, and anyone that wasn't really didn't get the prestige essentially. But I remember thinking at the time of, I felt disappointed almost in myself that I wasn't trying to do Oxbridge, but then I kept reminding myself, but yes, Leicester actually has a massive amount of history with space. There is a lot of investigations that are going on at the moment with Leicester, but also talking with my father at the time, because my dad actually studied at the University of Leicester, so I'm second generation, unfortunately. But
undergraduate there as well, I should say.
Oh wow, small world.
Yeah, back in the late 80s. Yeah.
Exactly. But I remember my dad discussing about his time at the university and being able to actually, because he worked, we had an undergraduate in geology and astronomy, so he actually worked with some of the moon rocks that they had collected from the NASA missions, and he fondly discussed about his time doing that. So that was one of the things that kind of made me go, actually, I want to go to university, and that's the kind of stuff I want to do. I don't want to be just sat in a classroom taking notes. It would be really great if I can actually get involved with the stuff. And that was the great thing about the third and fourth year projects, is that you can actually get really involved with the data that's going on for Leicester, and it's not a decision I regret. So it's something that I would definitely, for anyone that's 15, 16 is looking towards the A levels, looking towards universities, it is not to automatically go, oh, well, it has to be Oxford or Cambridge or UCL, and not think past that. I would always strongly suggest to actually look at what the university provides, what their specialisms are, and decide for yourself if that's kind of the areas that you want to stay in.
Great stuff. I think that's sound advice, and I think actually, there's always, my thought with this whenever I talk to, school students at that kind of age is, well, aim high, but bear in mind there are different paths through, and obviously it's great if you go to UCL or Oxbridge as well. It's fantastic, but you're absolutely right that, there's an awful lot of science around UK universities, and if you're somewhere that's got that strong base, it's fantastic. I was thinking, actually, as we were looking at this, is that is the live view. I can see you on my top left there. It might be
so the actual live view, I think we're now at Uranus, so I can actually make a way. So this is from, I believe, actually a year ago. I was going to discuss, but I can show it just a little bit later. But we have, so here we actually have the live view. Fantastic. So Uranus is just coming in. I have a better picture at the bottom, frustratingly. I wonder, oh goodness, sorry.
That's all right. No, that's fine. So the one saying Uranus cam there.
Yes.
Is that the live view from the observatory in Hawaii?
Yes. I'm just doing my best to fiddle with it as best as possible. And now it's got rid of it. Sorry. We're having slight technical issues.
We'll get it back in a bit.
There we go.
This session. But I was going to ask you, so as well as so I suppose we should continue this description of these worlds. So you're talking about how I think Uranus and Neptune, from what I remember, they are very similar in size, but they're about the volume of 64 Earths. Is that about right? Isn't it, from my memory? And then we'll have
quite possibly. I have a very different. Right, I have a different one from the presentation, which I was going to say, perhaps. Would it be possible if I can go through some of the science, which actually includes kind of elements?
I was also going to say the other thing about them is that they are like miniature solar systems. So they have, does it have 15 moons? Is that right, from memory? I know that they're the 5 that were discovered with telescopes, and then the Voyager mission extended that number a lot. So.
Yeah, so there are, I think, 47 confirmed moons Uranus.
Well, there you go.
There are the 5, as you said, that were viewed before Voyager, and then Voyager found 10 more, if I remember correctly, and then since then we've kept finding more moons at Uranus, to the point where we're now at 47, which always boggles my mind when we think about the fact we've only got one.
I don't know. I remember having seen the Voyager mission pick these things up, and an enormous amount of excitement in the 80s when it got there. As it went, as missions went to Jupiter and Saturn, Uranus, Neptune, suddenly this moon count just expanded ridiculously.
Exactly.
47. There's no chance of remembering the names of 47 moons, right?
No, of course.
So let's see. This is So I can see I've got Uranus cam, Spectrocam inside.
IRTF, sorry.
Okay. No, that's okay. So that's in the view inside the dome, right?
Yes, so that's inside. So these are videos, I think, from last night. The inside IRTF is basically a time lapse of about 10, 12 hours, looking inside of the actual telescope dome. So you can see there the telescope's actually moving around. I think this is either day observations or going into engineering side of things, so just making sure the telescope's working.
And we should stress that IRTF it's NASA infrared telescope facility, so it's looking at light which is beyond the red end of the spectrum we can see with our eyes.
Yes.
And this is and you know, I was surprised when we were talking earlier, this is a 42-year-old facility and a 3-meter mirror. Do you want to talk through how it works? Or
so there's a lot there. So I'm trying to see at the moment the exact view that we're getting from Uranus, just so I can kind of discuss which moons I think we may have in view. Unfortunately, I've picked the wrong view to look at, so I don't know fully. So back to the question. Sorry. So yeah, IRTF, to my knowledge, has been around for 42 years. I haven't been around that long, so I can't completely attest to that value. But they say themselves, and I feel like they would at least be the experts on that. So to my knowledge, there's actually quite a few telescopes in the area. I know Steve Miller, Professor Steve Miller yesterday discussed about the fact that on the mountain we have both the twin Keck telescopes, that's Keck 1 and Keck 2, where we've taken some of our data for projects similar to this. We also have the Gemini telescope, which is where a lot of the cameras that I've been putting up of the time lapses, that's where they've come from. We have IRTF. I think we also have UKIRT on there. I don't know exactly what's going with UKIRT, because unfortunately we don't have access to UKIRT anymore. It used to be a UK telescope and then we sold it off. But we used to use it. The first detection of HC plus at Uranus was actually through, I believe, with UKIRT. So it's one of the things that we can remember fondly of its time when we had it. But there is a phenomenal amount of telescopes. With IRTF, there are a couple of instruments that we use. There's the SPECS instrument, which is basically very similar to what we are doing today. It's a spectrometer, but it works at different wavelengths and is used for different scientific. Do
you want to tell people what a spectrometer is?
Yes, no worries, thank you.
Sorry, right?
No, it's perfectly fine. Sorry, it comes across because I think we've discussed it so much, but obviously today is a very new day and a new audience, so apologies. So my best way that I found to describe a spectrometer is it's a little bit like a prism, where we have light coming through, and a prism will basically cause the light to fan out, and we'll go from all the way from the violets and blues down to the yellows and reds in the color. However, with spectrometers, especially in this case where we're looking at infrared, we're looking way past the red part and going off into wavelengths where we, with our human eyes, actually can't see. I don't know exactly if the wavelength gets longer or shorter. I'm trying to think myself. I think no, I'm not even going to try because it's been a bit. But we ourselves are actually working in the 3 to 4 micron wavelengths. So, well, 3 to 4 for this specific investigation. We may sometimes expand further down past 3 because the molecule that we're using, Hc+, which is essentially 3 protons and 2 electrons, if I recall correctly. Yes, it's 3 hydrogen atoms, but with 1 electron out, making that plus sign. And Hc+, which is the molecule that we investigate to see infrared emissions, specifically emits at these wavelengths, but it will also emit at wavelengths lower than and higher than, I think just higher than. But the strongest emissions, the brightest hellos that we get from Hc+ are at about 3.9 to 4 microns, which is what we're going to be looking more for today.
Great stuff. And the reason, I mean, you mentioned H3+ and so on now, and the atmospheres of these giants are basically hydrogen and helium, right? And then you've got these other trace things, or well, they're not trace things, but quantities of other things. Can you tell us a bit about what the Uranian atmosphere is made of otherwise?
I can give it a best go. Dudley Fletcher's probably going to be the best person to be going into the exact percentages. My understanding from a Hc+ side is that we have predominantly hydrogen, helium, being the main constituents of the atmosphere, though we do want to remember, I believe methane is a big property. The reason we also remember that methane is a big property is because if you look at spectra such as from that of Saturn, So I'll see if I can get the SpectraCam up. Oh no, that's the wrong thing. There we go. So I'm just shifting it so it looks a little bit prettier. So the spectrum we can see at the moment, there's a lot of noise in between these dark bands. Perhaps you might be able to see if I get my mouse. So just this area as well as this area. These areas that are dark are actually off the slit. So everything. So at the moment, this is where the slit is basically emitting light down onto the CCD array, and that's basically just kind of. I think the best way to explain it, but like almost like a scan, like it's slowly going through the wavelengths and it's scanning along, and then goes another line and scans along onto the CCD array. And at specific wavelengths is where we see these HD plus emissions. We're almost seeing it come into focus, which is the brightest line, this Q1 line we call it, which is essentially the brightest hello we get from HD plus.
So this is like the fingerprint in the spectrum, if you like, for this you're looking for.
Yeah,
so
no, that's a great way of saying
that.
it.
Yeah, I'm trying to think that, so you're analysing that to find out what's going on the atmosphere of Uranus as we speak.
Yes. So what we can tell from such as one emission line, we can actually tell where the emissions are brighter on the surface of the planet. So for this instance, we know that there are only two ways that HD plus emits or says hi. The first is due to interactions with what are known as EUV, or extreme ultraviolet radiation from the sun. Typically, this can only really be seen on the side that is lit up by the sun, so it won't be on the night side. But anything that varies from that, because that tends to be a constant, because the sun doesn't typically tend to turn off or turn on too, well, it's variably constant, obviously with coronal mass ejections and whatnot, but the amount that we get from the sun tends to be consistent.
Should we? I was just thinking, actually, could you make that that bit bigger? Should we make that image? I'm trying to think how we do that. probably we need to minimize our own images or something, or.
Yes, so I could probably take the spotlight off myself and you, and we could probably have that up for a little bit. It does mean people will hear us, probably won't see us.
I think we've got the captions up. So Emma, I mean, I was thinking we really should. I mean, there's so much about this planet. So apart from being discovered with a telescope, and the first one like that, I was thinking through the things I remember about it. 84 years to go around the sun. It's tipped over on its axis. So if you imagine the Earth, which has got an actual tilt of 23 degrees, and we get seasons and so on, well, Uranus is tipped over by 98 degrees.
Yes.
And, exactly. This is the perfect picture. And then and it has, and the consequence of that is that it has these extraordinarily long seasons as well. So
yeah. Sorry, I was just going to jump in with that because yes, goodness is a big part of the investigations that we have at Uranus. The seasons are incredibly long. As you mentioned, it's about 21 years for each season at Uranus. So
we whinge about the British winter, but imagine.
Yeah, I know. I was talking with some of the school kids on Friday, and we were discussing about the fact of imagine it being 21 years in just solid night times. You're stuck at one of the poles. Goodness, I can only imagine that you're having your 21st birthday and you get to see your first part of light, first bit of light ever.
and it has this, and the other. I think there's another. Enduring mystery is that it has incredibly fast winds. Is that right? 500-kilometer-an-hour winds in the atmosphere?
That's a good question. I am afraid I'm not an expert on that side of things. Again, Dr. Lee Fletcher is probably the best person in our department if I was going to ask that question. But I believe there are a lot of unknown mysteries at Uranus. It's one of the big pushes that we have of why we need another orbiter to go around to confirm, okay, there are these, again, this odd magnetic field and these weird aurora. What do they do? How are they defined? About the winds, about the atmosphere, needing a better understanding as well, just how the planet is in over the years. Because again, going back to the seasons, I suppose, is we actually don't have a full orbit of Uranus around the sun in terms of data. So we actually really don't understand how Uranus is going to act.
Do you mean with telescopes like the one we're using today? So we don't have
well, I'm meaning with telescopes, but just in general, our first actual data with Uranus has only really been around Voyager, we did have some mission. We had some detections prior to Voyager, but in terms of our understanding of how Earth works versus how Uranus is still it's still in its infancy of fully understanding how the planet works.
Is that because the kind of telescopes we had, say, 50 years ago just weren't as capable as the things we have today?
That's a good question. So it's I would say some part is telescopes. We obviously have been refining, we're getting bigger, even bigger telescopes. We have the extremely large telescope. I know Henrik has a couple slides discussing about
extremely large telescope. Yeah, for the benefit of the audience, we don't always have original names for a telescope.
Yeah, exactly. Some are really cool, some are really fancy, and then some are just the very large telescope and the extremely large telescope. It's a mixed bag. But I would say it is a combination of what the focus was back at the time. So back in the 1960s, it was very much a big focus on the moon, trying to get people to the moon, getting an understanding of how space environments work with people. Was a big focus. And then from that, I would say we started going, okay, and now what's outside of our little Earth moon bubble, and focusing more into the outer solar system. And even past that, I know back in the early 1900s is where we started getting an understanding of how the sun interacted with our Earth. Sorry, is the observational panel available? Yes, sorry. Let me add the spotlights, and we can go back to the there we go. So that's
let's make that one big, maybe, if we can, the observation panel.
Sorry, this one?
Or... Yeah, the one. I think that would be good as we talk through it. I was thinking, yeah. I mean, I was thinking of the, because again, this is like the sort of the rapid pace of advancement in the science. Is that when I was a child and when I was looking, when you looked at books in the 80s before Voyager, all the images of Uranus and Neptune, they basically showed something which was blob-like, with stars, what looked like stars around it, which are the moons. And what I think is remarkable is that not just telescopes like this, but even advanced amateur astrophotographers now produce images of details on the surface.
Exactly.
Yeah, it's extraordinary. I mean, the fact they do that now, I'm not saying this is a trivial thing to do. You need pretty sophisticated equipment, but nonetheless, they do it. And I think that must have, I guess, being able to see the changing weather patterns on the Earth and that kind of thing must have made a big difference as well.
Definitely. I mean, I would say the big things, if I was going to do a short answer, is it's been technology. The boom in technology has been phenomenal for observing with space, and I would say that interest with people. Professor Steve Miller yesterday pointed out that the reason I'm even doing this project was because one of the observers back in 1992 went, well, actually, we've got 3 hours. We don't want to go down just yet down the mountain. Let's just see if there's any H3 plus at Uranus. And then I think 6 months, possibly less than a year later, they wrote a paper going, yeah, actually, we've seen H3 plus at Uranus, so perhaps there could be auroras or anything else at the planet that we don't know.
And that's a lot of. We should switch over to some observations in a second, I think. But that's the point, isn't it? This is the marker for saying there are the equivalent of northern lights on Uranus.
Sorry, I was just going to say, just to add on that. So there are both northern and southern lights at Uranus. They are very weird and peculiar. So if you can get one of James's animations up, and I've put a box on today. I remembered how to do this.
I can see a hand has been raised by David Wright. Now, I think most of the people attending through this, David, if you can paste your question, if you've got one, into the Q&A box, and we can take it there.
That would be great. Thank you. Sorry.
Yeah. And this looks great. Is this So
yes. So this is James's animation that he kindly put together for us over the weekend. And this basically kind of demonstrates. So this is the view that we're seeing from Uranus. Technically, the one that we're seeing in our camera is flipped by 180. So the South Pole in this image is towards the right, but in our image on Kyle, that's the imager that we take to get an idea where Uranus is in the sky, is actually facing left. But either way, what we're seeing here is that we have the southern aurora. That's the one that looks like a red angry oval. and that's towards the southern pole, and that rotates very close to the southern pole, but unlike with our southern lights, it's not actually at the southern pole.
I mean, the first thing that I look at when I see that is that I know, if you have the northern lights on Earth, they're in a kind of ring around the pole, right? And here you've got these single blobs. Do we have any idea why?
So this is a theoretical one. The issue with Uranus is we actually don't have that much data. Again, stressing on to the first time we ever got an in situ or like as close as possible detection of the auroras was back with Voyager 2, and we've never had that ever again. The best detections we've had since then have been from Earth, and they have been very splodgy, I think is the best way to call them. There's no offense to the people observing. It's literally just been we've had flashes of photons come up going, hey, there's some exciting stuff happening over here.
So when you that I think is a really important point there, which is that even with a really good telescope on Earth, you're talking about a small image and kind of these small blobs, right? I mean,
yes.
Is that fair?
Well, the weird thing, well, it's a weird thing, the amusing thing to imagine is the fact that this is even with the Hubble Space Telescope, this is where Hubble has actually, with Laurent, the group in France, have been doing a phenomenal job recording the ultraviolet aurora since our observations back with 1986 with Voyager 2. And yeah, they have been using Hubble diligently over many, many years to keep recording the ultraviolet aurora, but the images that we get from them are usually very, very small contained flashes that only happen over a couple of degrees of latitude and longitude. So in terms of how the actual aurora look, do they look similar to our own? Do they have weird discrepancies? It's a good question. I can't fully say. The reason we have these splodges is because we actually don't know where the aurora starts and stops if it was going to be a ring.
Now, this is also going to possibly tell me if it's an unfair question. I hope not, but I was also then thinking we should really tell people how the sort of northern lights form on Earth and a planet like Uranus. Is the mechanism the same, and how does that happen? Because you think it's the interaction between the material coming off the sun and the magnetic field of the planet, and what's actually happening here? Why does it have an aurora?
So I'm just double checking something because I had a quick question from Rosie, who says, "Can only see myself."
I'm looking at the YouTube feed as far as I can see, Rose. Looking at the YouTube feed, we can see me, Emma, and the image. So it looks as though that's all right. And I'm hoping on Zoom. If anybody isn't on Zoom or seeing everything, do say.
I think I have it in gallery view and everything's correct.
Yeah, there we go. Someone's just said I can see 3 screens. So
apologies.
No, I think it's fine actually. I think it's all right. So anyway, these aurora. So what are these aurora? But we've talked about them.
Okay. So I guess it depends which aurora. There are lots of aurora in our solar system. We do have our northern and southern lights, and everyone's very familiar with those, and they light up due to the ionizing interactions from the solar wind, basically funneling down the magnetic field lines and interacting with the Earth's atmosphere, and depending on which molecules in the Earth's atmosphere gives us the colors that we see with the northern lights. That's my understanding.
So you've got these particles coming off the sun, this stream of particles, and they're charged, and that means this. Yeah, the physics thing, your moving charge gives you a magnetic field, interacts with the Earth's magnetic field, sort of snaps back and comes into our atmosphere. Is that what's happening on Uranus as well, do you think?
Essentially, it's similar in that sense, because any planet that has a constant, I want to stress constant magnetic field that is strong enough that it's away from the planet's atmosphere, away from the planet's surface. One of the issues is such as Mercury, where the magnetic field is squashed so much from the sun that we actually don't. Sometimes the magnetic field is at the surface of the planet. So any aurora there, I think, would be interesting to see. I don't know enough in that area to actually be able to fully comment what would be going on, but it's its own fun area. But when it comes to the outer planets, we do have detections of aurora at Jupiter, at Saturn, and that's both with ultraviolet, infrared, and X-ray, I
And
believe.
there are beautiful pictures of those as well. I mean,
Exactly.
they're Northern Lights displays that are much bigger than the Earth.
Yes, exactly. They're incredibly phenomenal, and I think the fascinating concept is, again, kind of touching back with the volcanic moons, such as that with Io, you can actually see what we call as footprints, where it's basically a dot that you see that is just a little bit lower than the aurora, but will come up in those pictures. I know our colleague Johnny Nichols, or Johnny as we call him, he has done a lot of fascinating work with ultraviolet observations at Jupiter, and he has a lot of videos which show these ultraviolet aurorae at Jupiter, usually the northern aurora, and you can see the interactions of, I think, not only Io, but a couple of the other Galilean moons, and they are a wonderful sight to see. We also get to see similar kind of very cool displays with infrared, but I think this is a kind of perhaps a good stress onto why we need to look at different wavelengths, why we can't just look at ultraviolet or something, is the fact that infrared actually detects more of the weaker side of the emission, so we can actually see fainter things that ultraviolet can't see. So by having the two compiled together, we actually get a much better idea of what's going on.
If you were this hypothetical space tourist that we talked about earlier, so I've done my kind of, I'm terrified of heights, by the way. I don't think I could jump off a 20-kilometer cliff on Miranda, but so I could jump off that 20-kilometer cliff on Miranda in theory and look up at the northern lights in the Uranian atmosphere. Is that a good aspiration for a 22nd century traveler?
Yeah, man, that would be great to see it. I mean, I think one of the things that I always stress to people that's weird about Uranus is the northern aurora actually dips past the equator on the planet. So it's an absolutely weird and fascinating concept to think that you could be right at the middle point on the planet between the two poles, and you would be able to see the aurora.
And would it be visible to the eye out there?
Oh, that's a good question.
I'm just thinking of a book I'm going to write about space tourists.
I don't know if I can answer that one because I've only read papers discussing about infrared, trying to look for infrared at Uranus, at ultraviolet. I know we have seen visible aurora at Jupiter, but they are much fainter and weaker than the displays that we see in ultraviolet and infrared. So if I was going to go to Uranus, I would want to have either ultraviolet goggles or infrared goggles that I could look up and see more fascinating displays.
It's 200 years time. I think we could have got miraculous ultraviolet goggles. We just wear.
Exactly.
I'm just wondering if we should. We were going to bring in, I think, Tom, if he's there, and actually look at what's happening now. Do you want to do that?
So I think at the moment they are still going through a couple of the images. I'll check in with, but I just wanted to check when he feels okay to shift over.
That's fine.
I mean, I still have my slides that I'm very happy to go through, which is just going through the history and the science that we're doing
that would
today.
be fantastic. I think it's been really interesting to hear everything you've been saying about your motivation and what we're actually looking out for, and the fact that this remote world, this giant world at the so far out in the solar system, we've still got so much to find out about it.
So I will just bring up the correct slide before I then start sharing my screen. So apologies, just wait for me here whilst I make sure I get the correct one. So there we go. So I'm just going to grab my notes very quickly.
That's okay.
There we go. So so welcome everyone to today's observations we have here at Uranus. We are currently just finalizing the last bits of observations and making sure that we're at the planet before we ask Dr. Tom Stallard if he will join us for a bit of discussion on what's going on, if the weather is going okay, if there's anything he wants to let us know. We're praying that there will be no cloud cover, no issues, but again, it would be great to hear from Tom himself on what's going on at the top of the mountain. So outside of this, I'm going to discuss a little bit about the science, the history of trying to observe with Uranus and kind of what's been going on since, or what we're doing as the HD Plus team. And I think the best way to kind of bring this up is if we kind of look back in our past. So looking up at the stars, looking up at the stars and skies, as Rob was saying, it's been something that humans have been doing for, goodness, millennia. We've been doing for so long and trying to decipher the meanings that are up there. One great instance, one recorded instance we have is that back in ancient Rome, the Romans named the week after some of the 7 planets that they could observe in the sky. And we know this is the sun and the moon, which is where we get our Sunday and Monday from, as well as the other 5 visible planets in the sky, which were Mars, Mercury, Jupiter, and Venus and Saturn, sorry, you forgot that. And as I mentioned, some of these names we're still keeping in the English language now when we refer to our days in the week. Of course, back then, civilizations had a much better view of the night sky. Unfortunately, due to a lot of the light pollution that we have in our cities, we don't always get to see these planets anymore. But I'm sure they would have had phenomenal displays of the Milky Way, as well as comets coming in and through, as we know from anyone that can remember the Battle of Hastings, 1066, and the Bay of Tapestry, the comet, I think Halley's comet coming in to unfortunately spell doom, I think was the overall message there. But again, we all know now these days comets are not doom bringers. So hopefully though, well, I say hopefully we are still observing more and seeing what happens with these comets. So obviously from that lineup, I have mentioned that there's a lack of Uranus and Neptune, and that was because without, as Robert was mentioning, without our telescopes, without optical enhancements from telescopes, we weren't able to see these planets very well with our naked eyes. So it's really been pretty helpful, especially in the last 200, 300 years, that we've been able to build up in terms of our technology and be able to actually observe these kinds of planets. So really for Uranus, it actually took pretty much hundreds of years before we actually got an idea that Uranus was about, and that was with William Herschel and Caroline Herschel's work, as well as I think on Friday we were reminded that Alexander Herschel also helped with the engineering side of the telescopes. So I wanted to give them a shout out as well. But they all helped in finding the discovery of Uranus in our solar system, which I think everyone will mention, but William Herschel originally thought Uranus itself was a comet at the time, before getting into further analysis and finding out that it was a planet. So Uranus itself, when looking at Uranus, a great way I find is to compare that with Earth. So one of the weird things to imagine with Uranus, we do call it a gas giant, but it is only about 4 times as large in terms of just looking at it as a 2-dimensional image. But it is over 1.8 billion miles, or about 2.93 billion kilometers. We were discussing 4 away from that of the Earth, which puts it out at about 20 AU. Again, I'll just go into that an AU is the distance. It's basically the distance between the Earth and the Sun. So it's 20 times that amount is where you'd go out to Uranus. Because of this distance, Uranus actually only receives about 0.3% of the sunlight that we have here at Earth, which means that it is, we would expect it to be phenomenally chilly at the planet. It's also a good reminder that light, I think it's something that a lot of people get reminded on with space, that it takes about 8 minutes for light to be received here at Earth. For Uranus, it takes 2 hours and 40 minutes. So again, a considerable distance for anything to happen. But because of that distance, we've really struggled to get a lot of information and data from Uranus and Neptune. We last achieved getting anything in situ, and what I mean by in situ means anything close to or at the planet, since pretty much the Voyager missions. That was when they were both launched back in 1977, and it was only until 1986 for Uranus, and I believe a couple of years later for Neptune, that we got our first images and data detections at Uranus and Neptune, which could confirm some of our theories. I think Henrik also wanted to bring up that it was the Voyager missions were kind of thought of as this grand tour of our solar system. They also went past Jupiter and Saturn and gave these phenomenal pictures of the moons as well as the planets there. And it was only actually thought of, I think, of like very close to the time that we saw it was going to be possible to even do this kind of trajectory through our solar system. It only is possible every 178 years. So that is almost 2, possibly 3 people's lifetimes that this kind of journey would be possible. And it's mind-blowing to think that that's the case. I know Henrik wanted to also mention that back in 1977, Star Wars first released. That was the very first Star Wars film came out. So it all kind of happened at the same time. So what did we see from these satellites? Well, back in 1978, we saw the biggest surprise at Jupiter was we saw the that Io was an extremely active moon, had active volcanism, which we didn't think was, I don't say possible, I would say more in the sense of we just never seen it outside of our own planet. So that was one of the fascinating things that we got from then. We also got kind of the most jaw-dropping view of the Great Red Spot at Jupiter. We also saw how the atmosphere moved in these patterns known as belts and zones at Jupiter, and how these interacted with the Great Red Spot. We also then got to see the Northern Lights, or the Aurora, at Jupiter, which scientists were able to begin to decipher, perhaps being linked to the active volcanism that we were seeing at Io. And lastly, we have just here the second arrow where we actually saw lightning bolts, very similar to the upper atmosphere we see here at Earth. So that was some of the fascinating concepts that we got from the Voyager missions. At Saturn, however, back about 3 years later, we got a closer look with Voyager 1, saw structure within Saturn's rings, which scientists originally thought were due to gaps because of tiny satellites, which are basically kind of pushing out some of the debris, causing these gaps. Again, we then got to see Titan, which is the largest of Saturn's moons. On closer approach, Voyager 1 actually saw that the atmosphere, which originally I think we thought was part of the planet, it was actually an incredibly thick part of atmosphere, incredibly dense, that we couldn't detect past that atmosphere to see what was underneath. So past the atmosphere, we were able to find that Titan wasn't the largest moon in our solar system. It was actually slightly smaller than Ganymede, which is Jupiter's largest moon. Lastly, we were able to observe a lot of Saturn's moons. One in specifically is Enceladus, where we found 5 types of terrain, though it appeared that they were incredibly spherical, like almost like in comparison to some of the other moons that we've seen, which are slightly misshapen. Enceladus is one of the incredibly spherical ones, but one of the most interesting parts was that it was almost entirely made out of water ice, and because of this, it actually reflects an incredible amount of sunlight. Because of this amount of sunlight being reflected, again, it's one of the most chillier places in our solar system. So if you enjoy winter holidays, your space tourism, perhaps Enceladus is one of the places you want to look for. There we go. Sorry. So that leaves us with Voyager 2. What did it end up discovering back in 1986? This was back before even the debut of Comic Sans font, which is one of the fonts that we're using here. Henrik wants to remind everyone. So for Uranus, the encounter started in late 1985. I believe that was about November, December time, before finishing up between, I think, January, February in 1986, kind of where we got the majority of our data from Uranus, or at least closer information from Uranus. Pretty much the highlight for the whole thing was the closest approach, which only lasted about 6 hours, but I think that's where we have the most critically important information that we have at Uranus within that window. We also found 10 new moons, with something me and Robert were discussing earlier. We found 10 new moons with higher resolution images that we never had before for Uranus, which were Miranda, Ariel, and Umbriel, which perhaps we may see these today in our imager, as well as Titania and Oberon. We also were able to find out that Titania and Oberon were only about half the size of our moon, but still phenomenal objects within the sky. We also got a much closer look at the intricate ring system, being able to not only photograph these for the first time, but also be able to measure these pretty much since data had begun with these rings. One of the unusual things that Voyager found out was that these rings were slightly incomplete, with varying opacity levels, which led scientists to believe that they may have been relatively young. And finally, that Uranus itself has such a high layer of haze or photochemical smog, which we've detected towards the poles itself, making a lot of the haze that we see at the planet, making the planet almost very featureless. But further discoveries, and again, I would refer back to Dr. Lee Fletcher's discussion on Friday, has revealed a lot to us as we've continued to explore this planet regarding the atmosphere, or the lower atmosphere than we're looking at today. So at Uranus, I think as Henrik's end message here on Uranus is that Uranus is extraordinarily wild. The magnetosphere is a weird and wonderful story in itself. It's tilted by about 59 degrees from the planet's already tilted rotational axis. That's how the planet rotates or spins on its side, by about 98 degrees, if I remember correctly. So that means that we end up with a magnetic field that is completely out of whack, as we like to joke about. So if the magnetic field is so odd, what does this mean for the aurora themselves? Well, when it comes to trying to detect the aurora, see if I've got the last bit. No, I don't, interestingly. Sorry, I'm going to bear with me and see if I can grab the last bit of my note, hopefully. Yes, there we go. So Voyager 2 is pretty much our best way of being able to find out what was going on with the aurora at that time. As we were discussing before, telescopes hadn't quite got the resolution that we needed to pick out spatial information. So that's kind of the shapes, the sizes of the aurora themselves. And you're seeing here the collection of instruments that we were using at Voyager 2, though more specifically, we wanted to use the collection of telescopes, which are at the very end here, Henrik has pointed out. More specifically, we used what was known as UVS, which is the ultraviolet spectrometer. Ultraviolet spectrometer, which is key to discovering the auroras. The expectations, sorry, try and click through. What we did find from Uranus, along with some of the other instruments that we had on board Voyager 2, was that the expectation for Uranus, due again reflecting back onto that 0.3% of sunlight that is received Uranus in comparison to Earth, we really were expecting very chilly temperatures, not only at Uranus but also Jupiter, Saturn, and Neptune, just because of how far they were. I will apologize, I don't know what the Celsius can be converted into for Fahrenheit. I will just promise they are very, very cold. However, our observations actually found hundreds of degrees, hundreds of Kelvin difference, with Uranus being about 600 Kelvin higher than what we were expecting, which led to kind of what we know as the energy crisis, which is essentially we have such hot planets and we don't know why. And because temperature is essentially the measurement of energy, we have all this unexplained energy in these solar systems. We just don't understand where they have this, what systems creates this energy. And that's still an ongoing question at the moment. One of the possibilities us for infrared have been observing is with Jupiter, where we think possibly some of this heating is driven by Joule heating from the aurora. So that is the excitation that we have at the aurora generates a lot of heat. I think the best way I can kind of explain that is if you've ever tried to touch a light bulb after being plugged in, especially the older light bulbs, they are incredibly hot if you've left them on for a long time. So that heat travels down towards the equator of the planet, and we think perhaps that's how the planet is staying so warm. A second way we think is perhaps heating by waves. An example of this is we're investigating the Great Red Spot at Jupiter, where we're seeing enhanced temperatures, if I'm remembering the paper correctly. And these temperatures we think are due to, rack my brain again, are due to perhaps even gravitational waves or lightning driven acoustics, which are generating energy and creating perhaps these systems that are generating heat into Jupiter. And these, again, could be very possible at our other planets. But again, it's still an ongoing mystery that we are looking into at the moment. And looking into it, we do, such with telescopes. So for today's example, we are using IRTF, that is the Infrared Telescope Facility in Hawaii on Mauna Kea off in America. So that's a good couple of hours behind us here in the UK. The funding from IRTF was actually a leftover of the budget from, I believe, the Voyager missions. And we're incredibly thankful. And because of that, it's one of its main focuses is to support planetary science, such as the work that we're doing here today, where we're focusing on Uranus. Inside, we have the better idea of the actual telescope. So to ensure that we can kind of maintain and avoid the telescope being snowed on or rained on, we have the dome. So that's the silver side that you're kind of seeing, the silvery part on the inside. That's the dome, which is used to protect the telescope and the actual telescope. And the instruments are what you're seeing here in the pictures in the orange and blue boxes. Inside of that, we actually use an instrument which is known as iShell. iShell is a spectrograph, which I will briefly go over again. We discussed a little bit earlier, but a spectrograph is a spectrograph, and a spectrograph is similar to a prism. So if you put a piece of glass in light, you can see a rainbow of the colors, it spreads out. Well, a spectrograph does that with light, but over many, many, many wavelengths, including wavelengths that we cannot see with our eye, as we can only see visible light. And today we're actually focusing on this invisible light known as the near infrared spectrum, which is about 3 to 4 microns in wavelength. I'm trying to think, sorry. We use two individual parts of iShell, which are known as the imager and spectrograph, which is where it's broken down. We use the imager so that we can actually work out where we are in the sky. So we can make sure that we're actually looking at Uranus and not something else by accident. And the spectrograph is where we take our information. They are belovedly called Kyle and Cartman, and yes, that is a reference with South Park, because we also have Ike, which I believe is the system that we use to save our data, and I believe Kenny is the whole setup. So unfortunately, if something does go wrong, we do have the jokes that oh my dear, they've killed Kenny. So that one's quite funny if we do see that pop up. Finally, we're using the spectrograph to actually look at HT+, which is a 3 hydrogen molecule, basically 3 protons and 2 electrons, and will specifically emit at wavelengths, or at specific wavelengths, as Robert was saying, almost like a fingerprint. It is at specific points in our spectra where we'll see it light up. So in today, you'll see these lines, these black and white lines that will come up, and that is basically the points where HT+ is going, hello, I'm here. By observing these lights, we can actually determine physical properties such as temperature and density in the upper atmosphere. We do that by basically comparing, apologies, by comparing the intensity, or what we call the brightness, essentially, between these lines to get temperature, and comparing theoretical versus what we have to get an idea of density. I'm going to skip through a little bit. With our observations at Uranus, we've actually found very interesting things. One such thing is that over the 20 to 30 years that we've been using infrared technology to observe at Uranus, we have seen a 8 to 6 Kelvin decrease at Uranus in the upper atmosphere, and at the moment we just haven't seen this any other planet. Another way that Uranus is really, really weird. Our current theories is that we might think it'd be extreme in the seasons. So back in 1986, we may have had the hottest time for the upper atmosphere, and we are expecting consistent cooling, perhaps all the way down to 2028. But it is still an ongoing mystery. We are hoping that we won't keep cooling past 2028, but this is something that's still ongoing, and we're hoping we'll find out more answers as we continue our investigations. So very quickly, thank you everyone for listening on this. I'm just going to finalize on, this is the view that we're going to be seeing today. So this is an example of the Kyle imager, the slit which Henrik has put in a white band here. We're going to be seeing Uranus happening, Uranus at 2 points on the slit, known as the A position and the B position, and we will be what is called as nodding, which is basically shifting from the A point to the B point and from B point back to A point. So Uranus will appear to move along the slit. The reason we do this is not to annoy people. people. It is so that we can remove the Earth's atmosphere. What we do is basically we will have a image where Uranus is in one part of the slit, and if we move it off, we then only just have the Earth's atmosphere. So we can then mitigate Earth's atmosphere in that in the B frame by minusing it from the previous one to basically get a much sharper image. It helps us a lot when it comes to spectra. We then use Cartman to the slit information that we get is produced onto Cartman, which produces these HQ plus lines, and using a ratio of these lines, we can then get temperature. The last part of, we then have the James Webb Space Telescope. We had a lot of discussions yesterday. Please look at the videos that we have from Heidi Hamill, who has a large discussion on the James Webb Space Telescope, but we're really hoping to get more observations planned for 2022, which will help decipher more of the mysteries that we have at Uranus. Final part is that we really, however, really want a space mission to Uranus. The last one that we had, obviously, was back with 1986, was the last one we actually got any information, but they both got launched back in 1977. We know from the Cassini mission, which was sent to Saturn, which was back in 1997, which lasted from 2004 to 2017. So it would be phenomenal if we could have an orbiter or at least some kind of mission to the ice giants, even if it's not Uranus to Neptune, and be able to last for 20 years, maybe. I think that might be a bit of a push, but perhaps 15 years would be phenomenal. I'm just gonna
brilliant stuff. Thank you. Thank you, Emma. That's fantastic introduction. We do have one question actually from Paolo Massioni, and he asks, hello, first of all, thanks a lot for the amazing event. You're welcome, Paolo. And I have a question, maybe it goes a bit off. We've now seen that all gas planets in the solar system have rings. Do we have any idea if this pattern has a deep reason? That's a good, profound question. And if we might see this have the same on exoplanets.
Okay. So that's an interesting question. So it's only Saturn and Uranus that have rings. Jupiter doesn't have rings. I don't know about
Neptune and Jupiter have
okay,
they're
rings,
they're less well developed, but they do have rings.
Okay,
less,
apologies on that one. This is a good question. Unfortunately, I'm not that involved with exoplanets. I simply write papers which go, hey, we've seen this at Uranus. We may have seen something at these. We might see something similar at the exoplanets, but I can only suggest than actually
right.
go into
I mean, look, I wonder.
I think for me, it would be great to know if this is a consistent pattern with the gas giants, perhaps because of their gravitational pull. But I think perhaps it is a interaction between one having enough stuff in your solar system to create these rings, or again, I know there's a lot of discussions on how the rings were made themselves. I don't know too well on the theory side of things where we are on those, so it is a fascinating question. I'm going to apologize on that one, Pablo.
I don't think you've got any reason to apologize, Emma. This is such a wide-ranging number of questions. I was just thinking whether maybe with James Webb it would be possible to detect hints of them. I'm not sure how, if you had a big, thick ring system around another exoplanet, whether that would be detectable, a Saturn-like one.
I'm afraid I couldn't answer that. It would be great to know, but I'm afraid I don't know.
I can see Tom. Have you got
Tom
Salad coming in? Have you got an answer to this?
Coming briefly on that, I know that we haven't seen a ring yet, I don't think, but we've certainly tried to look for one. So there are observations of some of the most well-known exoplanets, some of the earliest and easiest to detect ones that are at such an accuracy that we know that they don't have rings. We've used Hubble Space Telescope to look at the transit of those worlds in incredible detail and measure that. And the techniques we use are very similar both in exoplanets and in what we do in the solar system. So Geraint Jones did an amazing observation using, I think, Cassini, where he was able to show one of the moons of Saturn has a ring system, a very thin ring system. So those techniques are the same, and so we would be able to see the dip of light just as that ring started impinging on the star before the planet did. But of course, those are very close in stars, so maybe they are a little less easy to sustain a ring upon.
Right, I'm going to bring in Sarah Casewell just to answer this particular thing, and then I'm going to do a couple of other bits, and then we're going to bring you in properly, Sarah. But I know you've got something to say about this question.
Yeah, so there are groups where people have looked for rings around known exoplanets using the transit method. So where a planet moves in front of a star, you get a dip, and this is how we detect lots of exoplanets. But you can imagine if there's a ring around that planet, you sort of get a slightly different shaped dip due to the rings either side. And there are groups, notably a research group in Leiden, who are doing this to look for them around exoplanets. But the thing perhaps to note here is that a lot of exoplanet systems do not look like our solar system. So our giant planets are quite far out compared to a lot of the Jupiter-sized planets we're finding around other stars, which are in orbits of a couple of days, orbits of nearer than our sun, nearer than our Earth is to the sun. If you think Mercury's orbit is 88 days, 2 to 3 days is quite extreme for Jupiter. So the mechanisms that might leave you rocks to make your rings could be quite different simply because of how these planets have formed and where they've formed compared to how the planets in our solar system have formed.
Thank you. That's a nice, concise answer. I think the questions I'm putting to Emma, it's probably deeper and more wide-ranging than anything she'll get in a PhD fiber, I'm guessing. So we should be very, frankly, yeah, it's an absolute expert in one area. Doesn't mean you can expect it to be an expert in everything. But there's I thought actually, as it had come up earlier, before I bring you in, Sarah, I think we'll go to your talk. If I can get the tech to work, I did fire up a program called Stellarium, which shows you, hang on a second, there we go. If I do share screen, it shows you what's in the night sky at a given point, because we had, and I was thinking actually this is also for Emma's benefit, so she can actually go out and find Uranus, having not looked at it. So there we go. So that's from Stellarium. So it's a bit complicated, but that's due south from pretty much everywhere in the UK. That's east. The horizon's down here, and this is about midnight. Midnight-ish, 1 o'clock in the morning. There's the constellation of Orion, which will be rising in the east at that time, and Uranus is about there. So if you know your night sky, there's Aldebaran, Uranus is there. You need to find a chart, but if you've got patience, you should be able to find it, and it's possible to see it with your eye, but a pair of binoculars or a telescope will really help. So I will now switch back to the main thing, and somebody in Leicester needs to show Emma Uranus as well. We've concluded that. Can I get back to, sorry, I'm trying to, if I do stop share, there we go, excellent. Right, working the tech. Okay, so I think at this point it would be great to bring in Sarah. Unless Tom, how are you doing with the live stream from Hawaii?
We're doing great, actually. We've got much better weather conditions than we were worried about. Our weather report comes from Thursday, so it's very out of date, and thank goodness, because it was reporting fog on the summit. So
it's not something you associate with Hawaii, is it? Until you realise it's 4,000 meters up. And,
exactly.
Okay, so in that case, how do you want to do this? Sarah? Do you want to go first, or should we go to the live observations?
It's entirely up to you what you want to do. If you've got good weather at the moment, I would make the most of your good weather.
Should we do a bit of that, Tom? Do you want to take us to Hawaii, Tom?
Sure, I can do that. Or Emma, do you want to? These are your observations, after all.
Shall do? Just give me 2 seconds as I go through this, and I'm just putting everyone off the spotlight so we can just get a closer view, hopefully, of. I'm hoping.
While you're doing that, Emma, a reminder to everybody watching: if you're on Zoom, please do type questions in the Q&A box, or if you're on YouTube, I'll go back to the chat and I'll be checking them there. But now I'm going to hand it over to Emma.
So hi everyone. So we are now, I think I showed this about an hour ago or so. So we're now coming up to 2 hours into our observations at the moment. So we've been looking at Uranus for about 90 minutes, I would say. So we have Uranus here in our bigger box. Thank you very much, Tom, for just seeing if we can get a bit of contrast here. So we have Uranus being the bright ball in the middle. I should stress Uranus isn't this white color or these purple colors when we look up at the sky. These are artificial colors that we're using to help spot out particular objects such as the moon. I think yesterday we had another star in the background as well, so it's useful for us to kind of know what's going on. We are just shifting on to the A positioning. So if you remember I discussed before, there's this nodding technique we use. So at the moment Uranus is just shifting to A. We promise Uranus hasn't suddenly ejected out another small planet on the side. I think we have 2 moons in view at the moment. Tom, do you know which 2 moons these are?
I'm just looking them up now.
I feel that perhaps the one on the right might be Miranda. We've been seeing Miranda a lot in the last 2 days, but again, that might be me jumping the gun.
Where are we? That might well be Ariel, I think.
Okay.
Miranda's more to the bottom left, I think.
Okay, my apologies. So that's Ariel. Would that make Umbriel up at the top?
I think so. I'm going to zoom out my view from my ephemeris is too tight in. Let's have a look again. Let's see, Umbriel. Yes, I think so.
Excellent. Okay, fascinating.
Titania's just out of view on the bottom somewhere.
Also, okay, so we'll have perhaps he may pop in again as we go through in our observations today. That would be great. I will move to our next part, which is basically with the spectra. So again, that is where we get our data from to understand what's going on at Uranus. So we here have 2 lines I think are coming through at the moment. So we have what's known as the Q1 line and the Q3 line. The Q1 line is the stronger line that we're seeing here at the bottom right. That's where it's basically the brightest hello that we get from HC+. Any variations that we see on that line is a good idea for us to know what's happening spatially on the planet's surface. At the moment, I think it's just a bit too early to know exactly what's going on. I don't know if Tom, you may have better insight looking at this line, but I think it's just a little bit too early to say definitively if we're seeing anything.
I think we're not seeing the same thing we saw certainly the first night where we saw a very bright region at the top. It looks much more centralized, if anything. So I don't know what the phase is compared to where we were before, but you can see it more with the second weaker line, I think. Often it's hard to see these things, but the second weaker line looks like a single blob on the bright section. So that's in the middle of the line rather than towards the edges. So I think if there's any asymmetry, it's centralized rather than towards the edges.
Yeah. Interesting. Okay. Well, it's something that we will be thinking on in our investigations. The nice thing with doing 3 days is that we're able to capture pretty much a whole 360 degrees longitude around the planet, which gives us a great view of the southern aurora. I'll see if I can bring up James's animation again demonstrating this. So at the moment we're seeing a phenomenal viewpoint to be able to look at the southern aurora at the moment. Unfortunately, the north pole of Uranus is facing away from us, so that makes looking at the northern aurora pretty difficult. Thankfully, because of the jankiness, I suppose, of the northern aurora, we actually have the northern aurora quite far down on the planet, so we're still able to see parts of it in our slit, and that will light up at the very edge on our slit. But anything that we're seeing towards the middle is probably something to do with the southern aurora. So, as Tom was saying, perhaps we are seeing elements of the southern aurora come into the view at the moment. But that is pretty much the round off that we have at the moment. We will let you know if there are any changes in the weather, or we might have seen any new things coming up. But otherwise, I think that's where we'll leave it with today's telescope view-in just before 11 o'clock today, or 11:15.
Yeah, if I just change the color scale, you could just about see Miranda down here. I put if you put the square just underneath it, so that just above this little green square, you can see a slight glow. That's Miranda, I think.
I'd say it'd be close enough too, yeah. Awesome. Thank you so much for that, Tom. We'll come back to this, I think, after we discussed with Dr. Sarah Casewell, and obviously have our Q&A, wonderful Q&A. I want to say first off, thank you very much, Sarah, for coming to today's discussion, as well as today's live stream. I wanted to ask very quickly, so I believe we were discussing before, we were going to do a presentation today with some of the work that you're doing, as well as your experience with working with IRTF. Is I believe in 2 days' time, you're going to be essentially taking over what we're doing and doing your own investigations.
I have Tuesday morning UK time, which is what we'd call the first half of the night in Hawaii. So it's something like 7 p.m. their time until just after midnight.
Wow.
Yeah, 5 a.m. start for me.
Yes, exactly. It's silly the amount of times that sometimes you have to wake up at 4 a.m. here in the UK so that you can do the remote observing. Awesome. Well, if you don't mind, I'll introduce you properly to our audience, and then we can look towards the talk. So again, thank you so much for your time today.
Okay.
So let's see if I can get my lovely notes that I have here. So hello everyone. So we have Dr. Sarah Casewell today, who's from the University of Leicester, who is a Ernest Rutherford Fellow and lecturer, whose research interests lie in white and brown dwarfs. Sarah is the LSST person of contact for the solar neighbourhood in the UK, and leads the aerial working group on brown dwarfs. Outside of her research, she chairs the University of Leicester's Women's Forum, Staff Forum, and is a key member of the school's Equality and Diversity Working Group. Recently has been invited as a panelist of the final episode of the UK Space Pod 2021, discussing space science, innovation and commercialism that are needed to grow the space sector. Her most recent work, and taking place in the next couple of days, is using the IRTF telescope, the same one that we're using for today's observations, to look up and observe brown dwarfs in our night sky, which we're hoping she'll be able to enlighten us with today.
Thank you, Emma. Right, this is where we see if the screen share thing works.
No
Okay, hopefully we are good and you can all see that.
I believe so. I'm just going to make sure that that is correct. I can see that perfectly fine. I can also see your mouse, and I believe we should be just fine on YouTube.
Great. Okay, so thank you for that introduction, Emma. And I guess good morning to everybody, sort of European time. I'm talking today about brown dwarfs or other things that you can observe with IRTF, and we actually use IRTF quite a lot to observe brown dwarfs because it's primarily an infrared telescope and it has some excellent instrumentation for it. So I'm going to talk to you a little bit about brown dwarfs and why they're interesting, and then follow up with what I'm specifically observing with IRTF, and then a little bit about the instrument, because it's not the same as the ice-shell instrument that you're seeing for the observations of Uranus. And there are some key differences, and there are some really good reasons for these differences. So I'm going to talk you through a little bit of that. Okay, so if you're not familiar with brown dwarfs, they are the lowest mass products of star formation. And what I mean by this is that they're thought to form like stars. So you have the collapse of your giant gas cloud, but the clumps that form never have enough mass to fuse hydrogen into helium and stop burning, which is what would happen in a star. So you're left with a hot clump that cools and contracts over time. Canonically, they have masses between 13 and about 75 times that of Jupiter. This is what we're looking at in the middle here. But they're all physically about the size of Jupiter, give or take. So they're still big, but they're nowhere near as big as a low mass star, an M dwarf, for instance. And because once they form, they simply cool and fade, they have atmospheres that are between about 2,500 Kelvin, all the way down to almost room temperature at the cool end. And this means, much like planets in our solar system, they have atmospheres that are dominated by molecules. So things like carbon monoxide, methane, ammonia, and also chunks of iron hydrides and other metals that we would refer to as dust. And these dust clumps form clouds on the brown dwarfs. And you can see that the artist's impression here in the middle of the brown dwarfs, they've been imaged as though they have clouds and belts, bands, not dissimilar to the near-infrared image of Jupiter that you can see in the top right. Now, because the atmospheric composition of brown dwarfs and the way we think they look seem to be very similar to planets in our solar system, brown dwarfs are often described as being exoplanet proxies. And what I mean by this is that we can use spectra of brown dwarfs, and there are lots of isolated brown dwarfs. They don't all orbit stars like planets do. We can take spectra of them and find out what their atmospheres are made of. And then we're using them as templates, essentially, to understand what we might expect to see in an exoplanet atmosphere. So I'm going to have to move my series of pictures, so ignore that. So in the bottom right here, these are the HR 8799 planets. And if we take a spectrum of this one up here, the spectrum looks very much like what we see from low mass young brown dwarfs. Again, sort of validating this idea that brown dwarfs and exoplanets don't look that dissimilar, sort of on the face of it. Obviously, in reality, lots of exoplanets are exceptionally close to their host stars, sort of in 1 to 3 day orbits. And so it's that irradiation that then changes their atmospheres. And that's one of the reasons why they're often so challenging to observe. Okay. So brown dwarfs we normally observe in the infrared. This is where they are brightest. And by the infrared, I'm observing at what we would call shorter wavelengths than the infrared you're seeing for Uranus. So from about 1 micron all the way up to 2.5 microns is where we would primarily observe brown dwarfs in the ground. And you have here sort of a nice little schematic from Christiana Helling that shows you have the sun here and 6,000 almost Kelvin, extremely hot, 1 solar mass, extremely big. And then you have Teddy 1 is a late M dwarf. This is the same sort of spectral type as the primary star in the TRAPPIST-1 planets. And it's still pretty hot, 3,500 Kelvin to 2,500 Kelvin. And then as we move down, you have the brown dwarfs. So they have letter classifications like stars. So M dwarfs are the lowest mass stars, they're red dwarfs. We then have L dwarfs, and these are cloudy objects with dust and patches and quite often variability, a bit like weather. And then Gliese 229b, and you may have seen the famous Gliese 229b picture. This is often described as the first brown dwarf that was discovered. And this is a T dwarf. So in the T dwarfs, the carbon monoxide atmosphere of the L dwarfs, all that carbon monoxide has changed into methane, and the cloudy, dusty atmosphere, all those clouds have dropped below the photosphere, and we're left with what we'd often refer to as a clear atmosphere dominated by methane. And that's the T dwarf. And there is also a spectral type that's not represented on here, which is a Y dwarf, and I'll talk about those in a little while. And then we have Jupiter at the cool end. So in terms of what our spectra look like, they look like this. So this object at the top is an M dwarf. Then you have an L dwarf. So this is titanium oxide. We have this iron hydride here. And the gaps you see in the data are because this is where the Earth's atmosphere, the water in the Earth's atmosphere generally gets in the way. And as we move down to the T dwarfs, you get more of this methane absorption. That's what CH4 is. So you get this methane absorption. So these are the standard brown dwarfs, the L and the T. And then over here, we have the newly discovered objects. And these were discovered with the WISE telescope, which does observe in the same wavelength that we're observing Uranus in here. So WISE took photometry at 3.5 and 4.5 microns. And that meant it was able to discover objects that were much cooler than other brown dwarfs that had previously been known. And because they came after the T, they got called Y dwarfs. There wasn't much choice left, admittedly. It was H or Y, and we use H to represent the 1.6 micron photometric band, as we have J, H, and then K. So H was out, which meant we ended up with Y, which is slightly frustrating because it's really easy to confuse it with white. but it's the best we have. So the white dwarfs are the coolest objects, and some of these are sort of room temperature, and they're not that different in temperature from Jupiter itself. Now, the main problem with the white dwarfs is, though they're bright at 3.5 and 4.5 microns, it's really hard to observe in that wavelength range from the ground if your target is faint. And brown dwarfs are faint in general. So this isn't an option for us to observe at this wavelength range that you're seeing us do Uranus in here. We have to observe at shorter wavelength ranges, from the ground at least. James Webb, when it's launched in December, fingers crossed, will change all that, and we will be able to get spectra for this longer wavelength range here, which we haven't been able to do for, thinking about it now, a good almost 20 years. Okay, so brown dwarfs, this is not a brown dwarf, this is Jupiter from Juno. The beauty of brown dwarfs is, because they have clouds, like the solar system planets, is they are intrinsically variable objects. They're dynamic objects like the planets in our solar system. So you can see, with Jupiter, we know what Jupiter looks like zoomed out on the sky, essentially. But the closer we look, and these are images from Juno, the more we see, and what appear to be sort of broad stripes on a small telescope suddenly show you all this incredible cloud patterns and formations. And most of the planets in our solar system are the same. So this is one of the poles of Saturn, and everybody's favorite, I hope, today at least, Uranus. And we see storms and clouds and patches and formations come and go with time. And observations of brown dwarfs reveal much the same. So this is a very nearby brown dwarf, actually called Lumen 16. It's one of the closest objects to the sun. And we were observing, it was observed with an instrument called CRIRES on the European, the very large telescopes in the European Southern Observatory in Chile. And CRIRES was an instrument not unlike iShell that you're using to observe Uranus. And it takes very high resolution images. And I'm going to talk to you a little bit about what that actually means later. So these are the carbon monoxide lines in the brown dwarf. And what you're looking at here is the black is cloud. This is where we can't see into the interior of the brown dwarf, and the bright chunks are where we can look through the gaps in the clouds to see the interior of the brown dwarf. And these cloud patterns rotate around once every 4.1 hours. And sadly for us, this was published by Ian Crossfield, and then CRIRES was not on the telescope anymore. It's recently returned to ESO. So hopefully we will be able to take many more images like this of brown dwarfs in the future. Okay, so there's my potted history of brown dwarfs. What is it that I am observing and why? Okay, so I'm observing as part of a program I submitted to IRTF on a citizen science program called Backyard Worlds. And Backyard Worlds is looking for Planet 9 or fast-moving red objects in our solar neighborhood. So we're using data from the WISE telescope. And these have been stacked up over time so we can see if objects move over time. And what we ask our citizen scientists to do is to flag objects that appear to move. So we have two sets of objects. We have things that don't move very fast, which we call dipoles, because you have like a bright side and a dark side of the star and it flicks between the two, or something that is obviously moving. And our citizen scientists, it turns out, are incredibly good at this. Humans are much better at spotting things like this than computers in general. And we have found a huge amount of very faint and not so faint, actually, nearby brown dwarfs in our solar neighborhood, which is really cool. And if you saw some of the press articles about a particularly peculiar brown dwarf called The Accident, then that was discovered by one of our citizen scientists. Now, I got involved with Backyard Worlds actually, before I tell you how I got involved with backyard worlds, this method here of taking a series of images and seeing what moves between epochs, this has been used for decades. It's how large amounts of things like comets and asteroids are found, and it's how Pluto was found. So Pluto was here, and then a series of days later, Pluto was over here. And if you map these objects for long enough over time, then you can plot out their orbit. And that's also how the HR 8799 planets I showed you, that's exactly how they work for the same reason. This is, we block out the star's light, and we take lots of images of the system, and then we can map how the objects move and see if they appear to be going around the star, or if there's something in the background that's just moving in a different direction. So that's how Backyard Worlds works. And I was pulled into Backyard Worlds because a lot of our citizen scientists were finding brown dwarfs that moved, but they were finding other objects in the same field of view and the two of them were moving together throughout the sky. And if objects are moving with the same motion, we call it proper motion, and at the same distance, then there is a good chance that they are gravitationally bound, and actually they're a very wide binary. And a lot of the objects that our citizen scientists were finding appeared to have a white dwarf companion. So white dwarfs are stars that have got to the end of their lives. So on my diagram here, we're looking at what's called the wide pathway. We're looking across the bottom here. So my brown dwarf has orbited a star, probably at quite a long way out, perhaps not dissimilar to Uranus's orbit. And the host star has evolved. So it's run out of fuel, it's moved off the main sequence, it's become a giant. And as it's become a giant, it's expanding. And some of that possibly pushes the brown dwarf further out. Eventually that giant, it can't hold on to its outer envelope anymore. It gets rid of it. And we're left with this beautiful, the planetary nebulae that you see, these smoke rings, if you like, of the outer envelope that's been removed from the giant. And what was the core of the star is left as an Earth-sized, physically Earth-sized, very dense object. So about half the mass of the sun crammed into physically the size of the Earth. And my brown dwarf has sort of surfed outwards, if you like, on the shockwave that's come as this smoke ring has been ejected. And I've been left with this very wide binary, maybe separated by hundreds to thousands of AUs. So they're extremely separated on the sky. And these are the objects we're looking for, and that I'm hopefully going to characterize as part of this program. So curiously enough, the first brown dwarf ever discovered was discovered this way. So GD165b, those of us that work on stars are particularly fond of naming our objects in incomprehensible telephone numbers. This one's not bad, some of them are worse. But GD165b is a red companion to a white dwarf. So this is what it looks like in a composite on the Sloan Digital Sky Survey. So the big blue thing is the white dwarf, and it looks bigger because it's brighter in these wavelengths, not because it's physically bigger. And you can hopefully see there is a little dinky reddy brown thing, and that's the brown dwarf companion. And in 1992, a spectrum was taken of this. Again, I think on IRTF, not long after it had opened. And they ended up with this spectrum. And this was a bit confusing because it was clearly something that looked like it was cooler than the coolest known red dwarfs, but it was also sufficiently different. And the suggestion was that maybe M dwarfs just got cooler. They didn't stop at M9 like other stellar types stop at 9, and then we move on to 0 of the next one down. Maybe it was something else. And this was published by Zuckerman and Becklin in 1992. And then in 1995, the first spectra of brown dwarfs were taken. And it was then quite clear that that was what this had been all along. It's an L dwarf. And when you look at them in the infrared, they are about the same brightness. This is the same system taken with very high adaptive optics imaging on Gemini. So this image has very, very tiny pixels. So you can separate the objects well, because what we want to do is measure the position of these objects and the separation between them. So this is the white dwarf and this is the brown dwarf. And at 2 microns, they look the same brightness, but it's quite clear that when you look in the optical at shorter wavelengths, so like 0.6 microns, that's not the case, and the white dwarf is hugely brighter than the brown dwarf. And that's perhaps quite a nice illustration of why we tend to observe these systems in the infrared, because if we observe in the optical, we have to expose and expose and expose and expose to get very little signal, but in the infrared, they're much brighter. Another object you may have heard of is, again, amazing telephone number, WD0806-661. So it's essentially the coordinates, and the WD mean it's a white dwarf. This is the white dwarf. It's a very cool white dwarf, and it has a planetary mass brown dwarf companion, again, separated by a few thousands of AU. And this system was discovered using the Spitzer Space Telescope, which is not dissimilar to WISE. So again, 3.5, 4.5 microns, take 2 images separated by a number of years and see if you can see the systems move together. And this is a more obvious, closer system that we published, one of our citizen scientists published from Backyard Worlds earlier this year. And this is one of the nice things about citizen science, is getting people who perhaps are not professional scientists involved in making discoveries, and in this case, writing them up as AAS research notes, if that's what they want to do. So this one is a white dwarf, and this is a late M dwarf companion. It's not a brown dwarf. It's a very late M dwarf star. Okay, so what am I doing with SPECS on Tuesday? Well, I am observing with a different instrument, which is called SPECS. That's this delightful blue thing here. And SPECS observes in this blue box in the mode I'm going to observe in. So we're observing from just shy of 1 microns all the way up to about 2.5 microns. In comparison to iShell, which I think you're observing in this pink box here on Uranus. Now, the reason I can't use iShell for my observations is that my targets are too faint. And to give you a rough idea, Uranus in the infrared is about 5.7 magnitudes. My L dwarfs in the infrared are about 15.7 magnitudes. They're 10 magnitudes fainter, because magnitude system means it's bigger number, fainter object. And this essentially means that my targets are about 10,000 times fainter than Uranus. So observing at 3.5 microns is not going to happen for me, however much I would like it to work. So in order to explain one of the other reasons I'm using SPECS and not iShell, I need to give you this sort of graphic as how a spectrograph works. And I know Emma covered this a little bit in her talk earlier. So exactly like iShell, I pick my star and I put my slit. It says plate, but this works exactly the same way as if it's a slit. Sometimes it's a fiber, but we put the slit on the star. The light from the star goes through the slit. It bounces off a grating, which is quite often something sort of a specially coated piece of glass with lots of lines drawn on it. And the lines split the light up and we shine it onto the detector. So we have the blue end and the red end. So the long wavelength end over here, the short wavelength end over here. And we get black for absorption lines and bright for emission lines, which is what you just saw on that spectral trace for the H3+. So this is an iShell spectrum of a brown dwarf from a paper by Aurora Casewell. So this is a slightly different wavelength range to the Uranus observations, but this is what I would call the K-band. So you can see that there's a lot of detail here. We're separating out all these little lines. And this is because what we call the spectral resolution is high for iShells. So R is 35,000. And in real terms, what R means is it's the wavelength divided by the wavelength separation. So my wavelength separation here is some incredibly small amount of microns. So I'm getting lots and lots of, I'm not observing a huge wavelength range, I'm observing a very small wavelength range, but I can get lots of detail and I can separate all the lines out if I were observing with iShell. To observe with specs in higher resolution mode, what they call the cross-dispersed mode, or SXD, I am observing at lower resolution. So this is R of 750 compared to that 35,000. And if you look at, oh, I've lost my mouse, there we go. If you look at these two sodium lines here and compare them to the sodium line here, you can see we're still getting a lot of detail, but it's nowhere near as much. But I am observing over a much longer wavelength range. And depending on what I want to observe, that's perhaps more important. If I need to make comparisons between two stars, then I probably want a longer wavelength range. But if I want to measure how much lines are moving or their width, I probably want the higher resolution. Now, what I'm doing is I want to identify my objects. I don't know that these red things that are moving with the white dwarfs, I don't actually know that they're brown dwarfs. All of their brightnesses in lots of filters seem to indicate they are, but I need to confirm that. So I don't need crazy high resolution because that's going to zoom in on lots of lines, but not give me the information I need. And even the SXD, the cross-dispersed mode here at the bottom, is more detail than I need, really. I just need the overall shape to make sure things work. So what I'm using is specs in what we'd call prism mode. And you can hopefully see here that prism mode goes from about 0.8 microns, which is what I would call the Z band, all the way up to 2.5 microns here. And you can see, hopefully, I'm not going to resolve any lines here, really. I'm not going to be able to measure the width or the depth of any lines, but what I am going to get is a broad overview of what my object looks like. And for brown dwarf identification, that's what I want. So I'm using specs, and I'm using it in this wavelength range here, and the resolution this time is about 120. So once I've identified my object, I can go after it at higher resolution if I want to, although it's probably, to be fair, it's probably not necessary. Right, so I'm going to talk to you now a little bit about how I do my observing. Some of it's going to sound very similar as to how the Uranus observing is done, and some of it might be a bit different. So this means I have to do a little bit about how my detector works in order for some of this to make sense. So bear with me. It's a very hand-wavy explanation. It's not too in-depth. But CCD detectors, or infrared arrays, whatever you want to call them, generally work via, you have your light comes in, and then your detector is made of some materials, and there is an energy gap in that material. So our light, photon, light wave, light beam, whatever you want to call it, it comes in, it hits an electron at the bottom, and it gives the electron some energy, and the electron jumps up to a higher energy level. That's essentially how this works. Now, obviously, it's a 3D structure. So we have, if you imagine a grid on our CCD, these are our individual pixels, light wave comes in, it hits the electron has some more energy, and it jumps up and it sits in, if you like, a little bucket. And whether it's able to jump up or not depends on the energy of the light wave that's coming in. So it's tuned to the wavelength we're going to observe in. Now, to give you a rough idea, you have one of these in your mobile phone. In the optical, this is how we take electronic photos with pretty much everything nowadays. And the sensor in your mobile phone is about 5 by 5 millimeters. The biggest astronomy sensors that we use, this is an image of the wide field camera sensor from Edinburgh on Wolfcount, which used to be on the United Kingdom Infrared Telescope, is 3.5 centimeters by 3.5 centimeters. So that's still not very big. If I find my ruler here. So yeah, that's how big that is. It's not huge considering how big a 4 meter, 3 meter telescope is. The actual detector bits are not enormous. Okay, so these are what we call my calibration frames. So these are the things I'm going to do when I get to the telescope on a Tuesday morning. The first thing I'm going to do is take some calibrations, because if I don't take my calibrations, I have literally no idea if my data is going to be useful or not. I'm going to take dark frames. Now, dark frames, this is why I explained the detectors. Dark frames are to do with sort of a base level of current that you get in your detector. And it's really important for the infrared because quite often we're observing wavelengths that are the same sort of temperature as the room. So the dark current is a measure of how much those electrons just jump up randomly on their own due to the temperature around us. So it's really important that we take dark frames, and they have to be taken at the same exposure time as our science exposures so we can take them off. Otherwise, we're going to think we have more counts, more detections than we actually do, because all we're doing is detecting the room around us. And to minimize the dark current, this is the reason why infrared instruments in particular are cooled all the way down to sort of, 4 Kelvin with liquid helium, because if we keep them really, really cold, then we minimize the amount of dark current that happens in the background. Okay, in the middle, we have a bad pixel map. It does exactly what it says on the tin. The bad pixel map is a map of where the bad pixels on the detector are. Sometimes they don't work, sometimes there are defects, sometimes they're just problematic. Because it's an array of squares, sometimes you end up with sort of lines, you get bad columns. That's what's happening here. And over here on the right, we have a flat field, which is, if you like, an image of the detector. So we can remove any differences in sensitivity, and we can remove any other defects. I love flat field frames because you get beautiful night sky images, and then you look at the flat field and you see just how disgusting the chips are in reality. So any fingerprints, any dust, anything like that that's on the chip, your flat field is going to find. So you can see we've got this beautiful defect here in the middle. And my chip is clearly it's not the same sensitivity all the way. So it's bright up here and it's dark down here. So it's important that we remove the flat field. Otherwise, we're going to have all these defects on our science frame. And this is what we would call a sky flat. So it's an imaging flat. Because if you look carefully, there we go. You can see some stars on it. So we might do this internally with a lamp. We might do it using the inside of the dome or a white sheet. It's very technical. Or we might do the sky and we might dither. So we would take an image, we'd move the telescope, take an image. So all the stars are at a different point on the detector. And then we can combine them to remove them to actually see what the sky looks like without the stars. And then we can use that as our flat background. The other thing I need to take for my science for spectra in particular is what we call an arc frame or an arc lamp frame. And this is super important for me because what I'm doing here is creating a map of what pixel maps with which wavelength. So what I do is we shine a lamp with known wavelengths. It's normally something like argon or xenon. And we take a spectrum of it, and we know at what wavelengths the argon lines should be, because these things are well measured and you can calculate them theoretically as well. And then I find them in my image, and then say, oh, okay, so that line's at this wavelength, that line's at this wavelength. And then I can create a map of which pixel is at that wavelength, and I can use that to understand my spectra. This is really, really important if you're going to measure the precise location of the lines. It's probably not actually that important for the data I'm taking with IRTF, but if I had a binary and I wanted to measure how lines were going to move over time with the orbit, something like discovering exoplanets, then getting this wavelength calibration as good as I can get it is extremely important. And then the last thing I would do is to take a standard star. So this is a bright star that I can use to remove the Earth's atmosphere. And hopefully you can see here, I have my bright trace, which is my star. And then it sort of gets weirdly fainter over here. And these are mainly due to OH and water lines in the Earth's atmosphere that are between me and my standard, and they're absorbing the light from my star. And I need to know how much absorption there is there in order to take that out of my data, because otherwise it's going to mask lines that I might actually want to see in my target star. Much like Emma, we nod because we need to remove the sky background. Again, this is not a real color image. But the sky background is quite high in the infrared because it's warm and it's full of water. So again, we nod, I take my star here, and then I slide the slit down, and I take my star at the bottom. And then I subtract one from the other, and I'm left with a bright trace at the bottom and a dark trace at the top. All these lines are skylines. So, and I can also, you can see I've also sort of managed to semi-subtract them by taking one off the other here. What I'm then going to do is tip this edge on, because this bright line is not the same brightness all the way along. If I can look along that line, it looks like a little mountain range. And I'm going to extract that mountain range, count up how many electrons are in each of my buckets that on the CCD, and that's my spectrum. So my observation, the tools I use for the observations look remarkably like Emma's. So you've probably seen a GUI not unlike this at some point over the last couple of days. I'm putting in my exposure time. I want AB, same as with iShell. I give some information about my target. And then these at the bottom here, these are all buttons that allow me to set how wide my slit is, which depends on my weather conditions. I would use quite a narrow slit, I suspect, compared to what's being done for Uranus, because Uranus is big and my targets are not. And also things such as the grating, how many lines I want, which sets the resolution, or if I was imaging, what filter I wanted to look at, what wavelength I'm going to look at. And then at the top, you'll have seen with these boxes, I just watched Tom do it on the images you just saw. So we have these slightly curvy lines on my spectrum. There's an AB subtracted one over here with the positive and the negative. And this line is a cut through, and that's what this red graph at the bottom right is. And that's really important for me in particular. My target is not bright, unlike Uranus. And what I need to do is get a rough idea of how many counts there are in each of those bright lines, so I know I'm getting enough exposures. If my counts are really low, I might want to expose for a little bit longer, or I might want to do some more ABBA pairs to increase my exposures. Alternatively, my standard star, which is going to be bright, might be what we call saturating the detector. So when your electrons fill up the buckets, if you get full, what happens is they start spilling over into the neighboring buckets, and then your data is effectively useless. So I need to make sure that I'm not exposing for too long on something that's bright, because that will also be almost as useless as not observing for long enough. But for all intents and purposes, the observing strategy, I think, is not dissimilar to what you've seen everybody doing with Uranus this week. All right, so I'm going to finish here. I hopefully have got you excited a little bit about brown dwarfs, but also showed you the difference in the instruments and observing, and why it's very much a case of right tool for the right job. I don't want to be cracking my nut with a sledgehammer. But alternatively, if Emma used my settings to observe Uranus, she's probably going to get a flat line, black body, something that's not that functional for her science. So picking the right instrument and the right wavelength for what you want to do is really, really important. So I'm going to end there. Thank you very much for listening.
Thank you so much, Sarah. That was great. If you can unshare your screen.
Yes. Oh, you've done it for me. Wonderful.
Oh, I don't know, or somebody else. I'm just sitting here and things appear to happen. I think it's probably Emma who's really competently running this. So we do have an opportunity to take questions. If anybody wants to post them in the Q&A, that's absolutely fine. I'm trying to keep half an eye on YouTube as well, and there's been some fantastic positive feedback there. Lots of applause symbols and the rest of it. It's quite okay too, if you want to ask very basic questions. We're very happy with those too, although quite often basic questions have really, really complicated answers. It's always fascinating to see that. I mean, I was reminded looking at your talk, Sarah, many years ago when I did my doctorate, I did spectroscopy. I just remember things like straightening out those lines and how important that was, and all the things to think about in the reduction process. It's not just as easy as point it and
no. Yeah. When I wrote the talk, so I know a little bit about what Emma and the team do with Uranus and similar observations they take on things like Jupiter, but I'm also aware that the approaches to the observing and the calibration are quite often quite different. So yeah, I sort of wanted to go through that a little bit as well, because it's not all spectroscopy is not the same in terms of how you point and shoot or not, and what you do with the data. So I sort of wanted to give a little bit of a flavor of how I would do this on a star as opposed to how you would do it on a planet. Because I mean, when you see the slide where I did the AB, you see how big my star is compared to the slit, even though I sort of drew it freehand, compared to how big Uranus is, the slit, compared to the slit on the live view. So, you know, where you guys take slices through planets, that's not possible. My star fits in the slit, and that's, you know, that's it.
Yeah, I do like this sort of, the description of slicing through planets and fitting a star into a small slit as well.
Yeah, no, it's
I mean, thinking through this, so I was thinking actually I might ask you one of the same questions I asked Emma actually is what would your advice be to anybody, say, who's watching this, who's, you know, at the stage where they're thinking about subject choices and universities and that kind of thing, and if they want to get into this stuff, what would your kind of advice be?
I think if you're interested in observational astronomy, looking at stars, a good place to start is your local astronomical society, where people will be, I mean, a lot of the techniques, maybe not necessarily spectroscopy, but a lot of the imaging techniques are the same as the ones we do. People will take flat fields, darks or biases, and they will take their images to measure brightnesses, for instance. It's exactly the same. It's just my telescopes are a lot bigger. But another thing, and you know, I'm sort of quite passionately an advocate for citizen science, having become involved in the Backyard World project. And you know, we have twice weekly hangouts, and some of this, I don't want to say it kept me sane during lockdown, but it really, being able to have a scientific conversation with a massive group of extremely keen people once a week really kept my enthusiasm high, particularly when my day job at the time was helping my son learn about the Great Fire of London. I was devastated it wasn't planets, but no, Great Fire of London. Citizen science, I really enjoy citizen science, and I gave a talk about this at the National Space Centre on Friday, and I asked the citizen scientists I work with what they like about it. And there was a lot of, there's no preconceptions. I can come in and ask basic, I can contribute at quite a high level to science, but I can still ask the basic questions. Or I can enjoy my science, but still have a day job. It doesn't affect my career, but I can still do the science. And I really, really like that. My favorite comment was somebody who said, they get such a buzz out of being the first person to look at something in the night sky, and that resonated with me, because that's what I get in my day job, looking at these objects. So citizen science is another way of, if you like, just tinkering with what might catch your imagination. And there's all sorts. It doesn't even have to be astronomy. There's like cratering on Mars. There's Backyard Worlds. There's Find a Planet. There's classify some galaxy shapes. You know, there literally is a whole world of stuff you can do, all the way down to, like, you know, counting zebras in the Serengeti. So yeah, I think that's also a really, and you don't need a lot of knowledge. You know, it's great for kids, teenagers to have a look at and play with as well, and whether it's something that catches their imagination.
Fantastic, yeah. And you might get to discover a brown dwarf that ends up with the name The Accident.
Dan called it The Accident because he was checking the image for something else, and he spotted it zoom past in the corner. So it was The Accident, and it was only then when we followed it up we realized how bizarre this object is. It's insanely cool. It's very metal poor. And we need James Webb to observe it and actually find out what it's made of. So it's really, really exciting, but it was very much accidentally discovered.
That's a brilliant story. Yeah, and I absolutely agree. I think a lot of this is so much about continuing to ask questions and just being curious and asking the questions that, you know, maybe you'd think the stupid questions. It's always, sometimes they're absolutely the best. So.
Yeah, absolutely.
Okay, Emma, I think we've got one question, haven't we, coming through?
Yes, we've got one from Zoom and one from YouTube. We're just going to touch on the Zoom question and then we'll go to YouTube. So I think this touches a little bit on what we're kind of talking about, more with the data analysis side of things. So we have from AC saying, using the broad spectrum, can you fit the observed curve of a brown dwarf to an approximate black body temperature curve and come up with what the brown dwarf temperature is?
So in theory-ish, brown dwarfs are in general, if you think back to the slide I showed with the spectra, they don't really look like black bodies. So the answer there is no. But for stars and white dwarfs, absolutely. You can model them as black bodies quite a lot of the time. Because brown dwarfs have this deep absorption from either methane or carbon monoxide, instead of looking like a nice smooth curve with little bits out the middle, which is what you get for a white dwarf or a star, we tend to get massive gaps where absorption has eaten away at that atmosphere. So we have a series of people who actually often came from planetary science, modeling Jupiter and Saturn, Uranus and Neptune, and have developed models for brown dwarfs and modeling the clouds in particular in detail. And we use those as templates compared to our data to fit compared to determine the effective temperatures that way.
Okay, yeah, awesome. I was going to say this trying to fit the temperatures and whatnot with stars is a little bit what we do with our stuff, because we usually have to use as we call it, a calibration star, which is usually an A0 star to get our temperatures and whatnot. So we have a good idea at least what we can compare our stuff with. But yeah, I can't imagine not being able to use that. So well done.
So we would do the same with an A0 and observe it. The technical bit is essentially you edit out the absorption features in the star. So you have a black body, you compare it to a black body in a model of the atmosphere, and then you use that to take the atmosphere out of your data. Yes. But we don't tend to use the absolute flux level, the absolute brightness. And we would probably normalize to the broadband magnitudes, because we have JH and K, and our objects, although they can be variable, they're not that variable within the errors in order to do that. So we would normally benchmark to measure broadband photometry as opposed to trust the absolute numbers.
Awesome. Well, thank you very much for giving us insight on that.
That's okay.
I will probably go over to YouTube now. So we had from from John Murrell, who asks, are there any good books on M dwarfs and cooler? I believe that's the question specifically.
That is a very good question. So when I started my PhD, I was given a copy of, I think it's called New Light on Dark Stars, but it's now pretty out of date, I think. The best option is probably to have a look at some of the there are some sort of overview chapters from books like the Exoplanet Handbook, and I think there are a few others that are available online through archive, various places, which are quite good places to start. And because they're designed as sort of a textbook, they're not too science heavy in that sense. What tends to happen, particularly for brown dwarfs, is they tend to get missed off at the end of more typical astronomy textbooks that go through the Hertzsprung-Russell diagram, and they then just tend to stop at M and don't go any further. The brown dwarfs get a couple of lines along the lines of, oh yeah, there are these additional weird objects, and then you know that's it.
Okay, no, that's really great. Thank you. Thank you so much.
Sounds like a pitch for a book there.
It does. That's what I was thinking.
I'm not convinced. I'm not convinced by that.
For him to contact a publisher, Sarah.
So, well, if you do, always let us know if you do come out with a book. So we're gonna get copies.
This is my daughter read was sat with me. She's 3 when my son was reading his school reading book the other day, and she looked at it and she went, "Mummy, I don't like this book. There are no girl astronauts in this book." So yeah,
no, we need to make those changes.
This is the second time somebody said to me in about 2 weeks, you should think about it. I think I might leave that to the expert authors.
Well,
I don't know. I think you guys could do a pretty good job. I think, if I'm right, there aren't any other questions that have come up for now, but do keep posting them in. So I'm pretty sure, from what I can see, the chat with Tom and Emma and so on, that we're good to go to look at some of the observations again. Is that right, guys?
of course. I mean, I was just going to say thank you so much,
Oh, yes,
Sarah, for
apologies.
joining
That's
us.
all right.
Really appreciate
Thank
your
you for having
time.
me and letting me hijack Uranus with not planets.
It's perfectly fine. So the thing that we really wanted you to come here today is to show that the same telescope can do very different science, and I think you've beautifully put that today. So thank you so much for coming. You're welcome to stay with us and hang out in the background, but obviously we appreciate you'll probably have a busy day, so it's up to you on how you feel there. But thank you so much.
Cool.
Thanks so much, Sarah, for being a fantastic tool. That was brilliant.
Thanks.
So, me getting the wrong order. So, are we good to go to look at the observations?
Yes. So
Absolutely are. And I think one of the really wonderful things about Sarah's talk was that it explains so much about what we will do next once we grab this data off of the computer, how we have to slowly but surely massage it into a state that is actually scientifically useful rather than just appealing to look at. So not a lot of difference so far in terms of the observations, except to say that we're continuing to take data and we're continuing to build the strength of the lines that we can see. So if you look at can you put the spectrocam up?
yes, bear with me. Gotta get to the right bit. There we go.
Okay, let's pin that. We've got the nice bright lines down in the bottom right hand corner and a second set of lines in the middle at the top. It's a little hard to see, but there's some other lines coming through in the top left as well. So we're starting to get a third set of lines. I was looking at the brightnesses here. It's very hard to eyeball these and get an understanding of what the likely temperatures are, but you can do a little bit of a job of doing that and guesstimate. And I certainly don't think we've heated up significantly from the past. We're expecting these temperatures to be fairly depressed, and that's basically the relative brightness of these two lines. If we moved back to temperatures, certainly if we moved back to the temperatures we saw back in 1993, for instance, the top line would actually be brighter than the bottom line. Both lines would be very much brighter than we see them now, but the relative brightness would be that this top line would be brighter. And we can sort of scale that. So I would have expected, if the temperature was to increase, that we would see this line somewhat weaker, but not very much weaker. And we saw it took a while to come in. So I think we're probably still very chilly in comparison to what we've seen in the past. But again, still very much hotter than the expectations just from solar heating. So something is heating this atmosphere up. And perhaps that's an auroral heating. Or many of the other things that Emma talked about earlier. We are going to have to struggle to understand that, but you can see that there's a definite difference here. You've got a much more of a blob on one of these, so I'm thinking it's a little difficult to tell what's going on, but once we add this data up, we might get a better expectation of whether we're seeing features rotating around in the data that we're seeing.
Well, I think this kind of touches back on to why we're doing this in general, which is when I first put in for this proposal time, we wanted to do back-to-back observations of Uranus, as one of the key points that is still a very big mystery on Uranus is actually knowing where the auroras are on Uranus's upper atmosphere. The reason for that is the last time we got the error on the rotation rate of Uranus was back in 1986. And that was the first and last time where we were able to go, yes, the auroras are found at this latitude and at this longitude. We still know where they are relative on their latitudes, but because the longitude is what is rotating with the planet, we have, I believe after about 3 years, due to the error increasing with every single rotation of the planet, we've ended up with a 360-degree error on the position of the aurora, which means that effectively we have no clue where we would expect to see them on the longitude of Uranus's map. So that's one of the things myself and many other people who are observing Uranus's aurora are trying their best to refine this error with constant observations to see these aurora. The more times that we see these aurora, we can actually keep minimizing the error, because we can go from, okay, we saw the aurora at this point on Uranus, and a month later we saw it here, and we can compare it to what we would expect to then be able to go roughly, okay, actually it moved only 100 degrees rather than 120 degrees that we were expecting, which helps kind of mitigate the error each time. So is what's incredibly important, having not only 3-day observations, but just having a single day observation or a couple of hours observations are massively important towards us building this better insight into Uranus and getting this full idea of what's happening over the whole planet. I was just going to add any comments was we still have 3 moons, I believe, with us. So we have Umbriel up at the top. I think that's Ariel to the side of Uranus at the moment. I say to the side, to the right. And then possibly a very faint one. I don't know if it is, you can see it currently. We just see it in another camera at the moment. There's possibly a very faint moon at the very bottom.
So there's one more thing, which is a discussion that Nahid and I have been having, and that's whether I found a 4th line. I'm going to put that over, if I can, on top. I think I should just be able to drag it in front.
Yep.
You can
yes,
see.
We see that. Oh my goodness. So I think I can put my mouse over towards it. So is it this?
That feature there, I quickly identified as a clear and obvious line. It's not really come up very clearly. And the negative is very dark, very weak. It's not very dark at all. There is some light kind of line feature at the bottom there, which does look potentially like a line, I think. That's roughly where I would expect another of the lines to come in. We would expect that to be kind of slightly brighter, but then, of course, we've got different levels of instrument function. So once we divide through by the flat that Sarah was talking about, we might be able to identify that more clearly. But there you go, a possible 4th line in our data.
Would that be the Q2 line?
Oh my goodness, I know that it
Sorry,
is
a
line, trying to remember where I found it. It is 3.88, I think. I can't remember off the top of my head. It's a line that's relatively weak in comparison to what we've seen before, but very much less dependent on temperature. So I was hoping to be able to use it as a balancer, but I haven't actually had a look at it recently to pull that up. The line should be about 3.967, something like that. 3.97. It's not one I'm hugely familiar with. It's one that sits between. So it might be the Q2 line. In fact, looking at this,
I think that's a Q2 from what we've done with most stuff lately.
Yeah, so that's nice. It's a nice line that is moderately bright. So the fact that it is weaker, I don't know. Until we do the flats properly, we won't be able to get a really good appreciation of what's going on, I think. But it's a nice thing to note.
Yeah, exactly.
More than just the 3 that we've been looking at so far.
Exactly. Thank you very much for that, Tom. We have one very quick question before we are going to be handing over to look at the videos that Dr. Siam Prasa did yesterday and the day before. So we have one quick question. We have I'm going to ask a silly question, and don't worry, there are never silly questions. There are just silly people who won't answer them. Which why can we get an image of the torus of a black hole or the black hole itself? We can get an image of the torus of the black hole or the black hole itself. Why can't we see the aurora easily? It is a very good question. My knowledge, because again, we do planetary science rather than looking at astronomical science, but I've watched a good couple of documentaries that are on YouTube that are on BBC iPlayer that discuss about this. So to my knowledge, the black hole was done with multiple detectors, all trying to, multiple datas that were all coming in to try and refine and streamline and get the best image possible. And we got the wonderful image that we have of the black hole, giving us kind of a good insight of what's going on. Meanwhile, the data that we use, we don't actually have multiple telescopes all viewing the same thing. At least for today, we only have IRTF. There are campaigns. I know Dr. Wilter discussed on Friday that he and the team in France, that's with Laurent Lamley, have been doing combined ultraviolet and X-ray campaigns, but typically because they're using different wavelengths, they won't always see the same things at the aurora. Additionally, we're also hoping to do a combined X-ray and infrared observations of the aurora in perhaps December. Again, that's still in the works at the moment. But because we don't have multiple telescopes in the near infrared doing this, we just have to work with what we're given.
So I think the really fundamental difference between what we do and what that amazing result in the black hole comes from is time. You can sit and look at that black hole for a very long time and it won't change almost at all. So as you say, it uses interferometry. It's got multiple telescopes to build up a signal. Now, there's a certain limit on that for us anyway, because there are only certain telescopes that have instrumentation. But the biggest problem is just, the aurora's not only rotating out of view in a period of a few hours, it's also very variable. So we don't really know where that signal will come from. So we've struggled a lot compared to a lot of more distant astronomy because we're so time sensitive. As you can see, the rotation of the aurora is such that, if we have a slit that cuts through, the southern aurora will only appear in that slit for a few hours at the most. And so we have to return to look again and again. And all of our work is competitively bidded against other work that is of equal validity. So, we can only get so much time. That's the real limiter on any of the work that we do. So the idea behind the kind of work that you could do to pull out the signature surrounding a black hole, it's just impossible for the kind of work that we do because the spectral characteristics are too narrow, and we want to pull out information about the atmosphere itself, so we want multiple spectral lines, and we're trying to look at something incredibly transient way to capture a fleeting moment of an aurora.
Great stuff. Okay, I'm going to answer one question briefly, which is completely off topic, and that's fine because that's what we're here for, I guess, to be flexible. And so Wendy Griffiths asked on YouTube, has an exosolar system been found like ours, with one with 6+ planets? Well, I'm not sure if it's 6 planets, maybe even 7, but there is at least the TRAPPIST-1 system that was found by the Kepler Space Observatory when they look for transits. They look for planets moving in front of a star and measure the dip down in light. And that one, I think, has 7 worlds, and at least one of them is one that's thought to be potentially habitable. Doesn't mean it is like Earth. It just means that it's in the right place, the right kind of temperature. So nothing to do with Uranus, nothing to do with brown dwarfs, but a great question there, Wendy. Absolutely.
The key to that question, I think, is whether it's like ours, and that is a very loaded question, isn't it?
Absolutely, exactly. Yeah.
So yes, there is planets similar in mass to Earth in similar sort of distances in terms of whether they might have liquid water on the surface, but in many other ways they are vastly different to the planets of our own solar system. Yeah. And that's the joy. We've got 4,000 planets, none of which are alike, and none of which are like any of the planets in our solar system at all. Because
I always feel it's like, we should. It's a good sort of environmental push, isn't it, really? We haven't actually found another Earth yet. There's still this amazing oasis that we've got to take care of. But fantastic question there, Wendy, and keep them coming, please. We're happy to look at things. So I'm being reminded that we have a fantastic video we can go to in a second. And if you were on the stream, I think, was this on Friday that Sian did her slot, wasn't it, Emma?
Both Friday and Saturday.
Yeah, our librarian, Dr. Sian Prosser, has access to some fantastic resources, and in normal times, soon actually, I think we are opening up to researchers at least to come and look at them. They include things like Herschel's original notes, which have extraordinary things in them, actually. Things like he speculated at one point on life on the moon and all this kind of stuff when you read through. It's brilliant stuff to read from the late 18th century. And of course, there's information on Uranus. And the video we have of her also then cuts through to Charles Draper, who's associated with the Herschel Museum in Bath, which is almost like the sort of spiritual home for Uranus, because it's where William Herschel and Caroline Herschel found it 240 years ago. So I am going to share my screen to go to that. We'll have a 20-minute video of that, and then we'll try and we'll be happy, obviously, to continue the conversation and take some more questions. So here we go. Bear with me. And where are we going? There we go. Let's get this working. Can you see that, Emma? Is that working for you?
Yeah, I can see that at the moment. I can see the play symbol.
Great stuff. Let's roll.
So we have been collecting books and manuscripts since we were founded. That's an activity that's happened as long as we've been organising scientific meetings and publishing research and all our other activities. And we have some really interesting, amazing books, but we also have some handwritten manuscripts, observations that astronomers or their descendants have given to the society over the years. We have literally hundreds, if not, well, hundreds of thousands of really interesting observations that we like to share with researchers and the public. So we have a huge number of star atlases, and this is John Flamsteed.
Apologies, sorry, technical
in
issues.
the 18th century. And the reason that I'm sharing this page, this constellation of Taurus, is to show that Uranus actually had been observed over centuries, particularly in the 18th century when telescopes were becoming more powerful, but it was assumed to be a star, and it was referred to by John Flamsteed in his catalogue as 34 Taurus in his list of the positions of various stars. So, Flamsteed and other astronomers did record the presence of this celestial object, but it took William Herschel to, as Charles said, to observe the behaviour and the movements of this very slow-moving planet and realise what it was. But he didn't immediately identify it as such, and that's what I hope to demonstrate to you as I show you the observation notebook, which we're very lucky to have in the Royal Astronomical Society archives, along with many of the observational papers of the Herschel family. So this is the covering page of a notebook which is entitled Observations on the Georgian Planet and its Satellites. The Georgian Planet, that refers to the original title of Uranus. Basically, William Herschel, as the discoverer of this planet, had the privilege of choosing a name for it, and it was politically expedient to name it after the ruling monarch, George III. So its official name for a time was Georgium Sidus. I don't think people started calling it Planet George, but they certainly did refer to it as the Georgian planet, as it is written on this notebook here. It was in the next century that the worldwide community of astronomers decided that it wasn't really sensible to name a planet that could be visible by everyone on Earth after the monarch of one single country on Earth. And I think it was Johann Elert Bode, a German astronomer, who suggested naming it Uranus, keeping in the tradition of classical mythology. And Uranus also is the father in mythology of Saturn, who is the father of Jupiter. So it makes sense if you think about the structure of the orbits. So on the very first page, we have the fateful night of the 13th of March. But as you can see from William Herschel's very clear writing in the top of the page, he's saying, I discovered a comet. It's in this line here, if you can see my cursor. And that is because he can see that it looks different to the twinkling stars around it. And he sees it, it's new, he's not seen it before, he knows the sky and its constellations pretty well by now. But it takes page after page of observations, measurements, comparisons for him to not only satisfy himself, but to satisfy other astronomers and mathematicians in the scientific community. And he was able to share his data with the Astronomer Royal, Neville Maskelyne, and the lead astronomer of Oxford Observatory, Thomas Hornsby. And Neville Maskelyne really was starting to accept the hypothesis that this was not a comet. Here we see again, it's 1782. On February the 8th, this is an observation where William Herschel says the star is left behind by the comet. But on August 29th, 1782, when he's able to see Uranus high in the sky again, he says, "I saw my planet. Full is well defined with 460. Charles Draper explained yesterday that's the magnification, as Jupiter would have been at that altitude with the same power." So, after over a year of measurement and communication and verification, they are, pretty confident of this momentous discovery, the first person since the dawn of time to have discovered a new planet. And here we have it referred to by its new name in October the 13th, the Georgium Sidus. So that was a momentous occasion, not just for astronomy, but also for William Herschel's life. And it had a huge impact on the life of his sister Caroline as well. Now, I'm looping back to the atlas now, because it's very special, not just because it's a rare copy of a historical atlas, but because of who it belonged to. It belonged to Caroline Herschel, and she referred to it directly as she was assisting William with his work of observing the night sky. And he, as Charles very clearly explained, would make his observations. He would pull a cable which would alert Caroline, either in a booth or in the house where she was working, that a new celestial object had been observed, and she would refer to her charts, to this atlas, and to John Flamsteed's catalogue, and make a really accurate note. Her role in this was so crucial to the systematic observation of the night sky, because William Herschel tried to do it all on his own. He would observe a star and then go inside or use candlelight to note down the position, and then he'd lose his ability to see where the star was, because he'd have lost his night sight, if you see what I mean. Amateur astronomers in the audience will know all about this. And, he brought her in to be his right-hand woman. She was doing the incredibly demanding and accurate work of recording his observations. But she was carrying this out. By this time, they'd moved to Datchet in Slough, and later they moved to an area closer to Windsor Castle. She'd been taken from the social whirl of Bath to a country house with a leaky roof in the middle of nowhere. And it was an incredibly difficult adjustment for someone who was, on the outset of a really successful musical career. But she did make that adjustment, and she got really into astronomy in her own right. I'm going to share with you the first. This is the portrait of Caroline that Charles showed us, that's hanging up in the Herschel Museum of Astronomy. And from August 28th, 1782, by this time, because they had the King's favour, they were living close at hand to Windsor Castle, so that they could provide astronomical services to the king and his family and his court. So it's 1782, and she is carrying out her own observations, and she makes important discoveries in her own right. This is the first time that she discovered a comet. As she writes in her submission to the top journal of the time, the Philosophical Transactions of the Royal Society, she basically explains that her brother was out of town, so she was able to use his powerful telescope, and she discovered what in her very clear writing, she says, in the notes, I saw the object in the center of figure 1 like a star out of focus. Now that immediately tells us that this is a fuzzy object that is not behaving like a star, and that could have the characteristics of a comet that people were so interested in at the time. And she makes, just as William made his observations night after night of Uranus, she makes her observations night after night of this comet as it's trucking across the sky. And she finally becomes satisfied that this is indeed a comet. And she discovered at least 5, maybe 8 comets in her time. And she also discovered nebulae. This is a kind of cloudy patch on the sky. Sometimes they can be mistaken for comets. And we now know a lot more about what nebulae are, but at the time, in the 18th century, they were seen as fixed celestial objects, but not twinkling. There were smudges in the night sky. And this is one that she discovered, which was NGC 205 or M110. So it was in recognition of her work, not just as the assistant of William, but as a successful astronomer in her own right, making many discoveries of comets and nebulae, and her excellent work in publishing the catalogues and the data tables that, as Charles explained, astronomers rely on completely. That meant she got recognition in terms of being the first woman of the RAS to be awarded the gold medal of the Royal Astronomical Society. That was in 1828. The next woman to be awarded the gold medal was Vera Rubin in 1996. Well, we have to get better, and we are getting better. And she was the first woman to be allowed to join as an honorary member, not as a full elected member, as a fellow. She was at the same time as Mary Somerville in 1835. So that's just a quick run through of William Herschel, first president of the Royal Astronomical Society, Caroline Herschel, first woman to be awarded the gold medal of the Royal Astronomical Society, and their links with the discovery of Uranus and the discoveries of so many interesting objects.
Yes, I mentioned during my talk about Caroline Herschel that one thing we had done, which I'm rather proud of, is set up a prize lectureship to support women astronomers early in their careers. And we had the idea a few years ago. And I must say, I must give my thanks to Mike Edmonds, who is one of our vice presidents, but also the incoming president of the RAS, who helped me turn the idea into reality. And the thought was that, we all know there's lots of statistics showing that women don't get a fair crack of the whip in terms of getting into professional science. That's true of astronomy and elsewhere. Various efforts to try and help it. And the thought was use Caroline's name and reputation as a means of doing so. And perhaps I could say that there's a curious story, in fact, how it came about. I had the idea a few years ago, and then one of our society members started a big campaign. So at that moment, we were still called the William Herschel Society, and one of our society members started a big campaign to change our name from William Herschel Society to the William and Caroline Herschel Society. And he was a guy called Joseph Heaven. He was very adept at social media. And he got a huge sort of social media campaign going across the whole American community, sending us messages saying, yes, we should celebrate Caroline as well as William. It's fantastic. And I said, well, okay, I get the point. But trouble is, if you start sort of saying William and Caroline, then what about John? So where do you stop? So there's two consequences of that. One of them, it helped get support, indeed financial support, for the Caroline Herschel Prize medal. And the main financial support came from a wonderful British astronomer called Fran Bagenal, who works at the University of Boulder in Colorado. She's a planetary scientist. And she gave us some money, basically, to support this effort to celebrate Caroline. So that helps fund the prize lectureship. And the thing where Mike Edmonds was particularly helpful was identifying what this is for. And it's aimed at people, at women who have got their PhDs, and they're typically doing fellowships. They haven't got tenure, because getting tenure is the key step that turns you from somebody who is trying to be a long-term professional in the business to actually having a secure job, if you like. So it's aimed at that particular group, and the idea is they're applying to a committee, and I have a committee of 3 splendid female professors of astronomy who assess the applications, and they choose the most promising one every year. And we've now had 4 of them, and the 4th is Dr. Jenny Carter, who works on the interaction of the sun and the earth, in effect. And she is this year's Caroline Herschel Prize lecturer, and she'll be giving her lecture virtually, afraid we're still COVID bound a bit, in November, and hosted by the University of Bath, because they've been involved in this from the very start. So that's something we're very proud of. And the RAS is very helpful because they do a sort of a part of sort of the admin task, enabling this to happen. So it's done in association with them. But it's a great way of celebrating Caroline. And I'm pleased to say that the sort of, after 4 years, there seems to be an established part of the firmament. So much so that when Prime Minister Johnson met Chancellor Merkel in the summer to discuss very Anglo-German things, they built on our example, and they decided to have a Caroline Herschel medal to celebrate particular achievements. And I think the RAS is working with its German counterparts on how to do this. So Caroline will have 2 awards named after her. Not many scientists have that.
We are having this event as part of World Space Week, which this year's theme is Women in Space. And that was one of the reasons why we wanted to have, it was a fantastic opportunity to highlight Emma Thomas as an astronomer, finishing up her PhD. She'll be breaking out into the world soon as a female astronomer. And opportunities like the Caroline Herschel Medal sounds amazing.
Sure. Well, Emma, once you got your PhD, give it a go.
Of course. So, I mean, I was just going to add, it's weird, but things are such a small world. Jenny actually works in my office.
Really? Okay.
Yes, so we both work in the same office. So, as I said, it's been one of the high points that we've been discussing since the beginning of term, obviously.
Good. Fantastic.
Sean, thank you so much for taking the time out this weekend and sharing Charles, mentioning the work that Caroline Herschel did as well. And Sean, and if I missed it, that book, I'm so glad you actually took a picture of the cover, because yesterday I missed the cover of that book.
Oh, okay.
The journal, so beautiful. Were those Caroline's notes or were those William's notes? Those were Caroline, right? Because Charles mentioned it was Caroline who was making all the notations.
It depends when you're talking about, to be honest. Yeah, sorry.
No, after you, Charles.
Okay. I mean, they both have wonderful writing. And in the earlier period, I think it was William directly, but later on, quite a lot was done by Caroline. But, Sean, you know better than I do, really.
Yeah, but I need to know a lot better than I do. I know, for example, that there are 2 sets of the sweep books. Now, a sweep was a strip of sky that William and Caroline would observe in one session, and the originals are at the Royal Society, and the fair copies, Caroline basically spent a long time writing up the fair copies there with the Royal Astronomical Society. So that Caroline did a lot of fair copying, and still need to completely get my head around what looked suspiciously neat and what was actually written in the moment.
but they both have wonderful handwriting. I mean, my writing's ghastly. I can't read it, but you can read their stuff.
Yeah, and it's so good to use with primary school children. You know, it's we do invite children to read out Caroline's sort of nightly observations and think about what it was like to be an astronomer at that time and how she grappled with the weather. And sometimes she'd be like, "Oh, it's a nebula," and the next night it'd be like, "Oh, actually, it was a lantern shining in a barn in the nearby fields." You know, everyone. It doesn't matter if you make mistakes; you just have to record it and then learn from it.
And often you learn more from your mistakes than other things. As I mentioned yesterday, I think, when William studied double stars a lot, but he started doing double stars because in the 18th century, everyone was trying to work out how to work out how far stars were away from the solar system. And they realized the stars were basically like our sun, but further away. And from their brightness, you can sort of say they're millions of times further away. And they also realized that they had to use the parallax method to actually judge the distance. But the telescopes were struggled to actually be accurate enough to do that. So what William thought was, if I look at these stars that appear to be in the same part of the sky, that may help me. Now he made two assumptions. He assumed that all stars were roughly the same brightness, and the stars were individual things, and they weren't, going around in twos and threes, gravitationally bound. Now, both the assumptions were wrong. Stars vary hugely in brightness, and most of them are multiple stars. Our sun's unusual from that point of view. But that led him to study them, and it led him to realize that he was wrong. So it's a classic case of making a wrong assumption, but pursuing the logic of that and learning a great deal because of it. So I think making mistakes sometimes can sort of teach you more than doing a thing right.
Absolutely. A really great lesson to realize that that's a really important part of the process. And I highly recommend heading over to Bath when you can, when things are definitely safer to do so, and visit the Herschel Museum. We're going to hear from the Bath astronomers tomorrow. I want to thank our guests, Dr. Sean Prosser from the RAS Library and also Charles Draper from the Herschel Society. Thank you both for being with us today.
Great. I think, there we go. Back to... Hang on a second. Right, there we go. And we're back. So, sorry. Apologies if we had a dropout at one point. That was entirely down to me because I didn't know how to share a sound, ideally, in Zoom. So, even after 18 months on Zoom, there's still things I'm picking up in all of this. What we do have now, we do have the Bath astronomers coming in a minute. And I wanted to mention, actually... not much of a plug, but as we're one of the kind of leader actors in the event, the Royal Astronomical Society, as I mentioned at the start, is open to kind of professional astronomers, advanced astronomers, people with a professional interest, but we also have a friends group as well. So, if you're interested in the topic in general and you want to take part in various activities, including things like lectures, which are, certainly in the new year, we very much hope will be face-to-face again, and hybrid events, and also things like trips to astronomical sites like observatories and places where they make spacecraft. We've been running that very successfully for the last few years now, and there are no preconditions on entry. Anybody is welcome to join that. You can see details on our website if you go to ras.ac.uk/friends. So with that quick plug out of the way, I'm just going to get our schedule for when we're bringing in people. Yeah, so now we will be going to the Herschel Museum with the Bath astronomers, and I think I can see the people on the call there. I can see Jonathan. There we go. Jonathan, I'm afraid I don't have a biog to hand for you, so but I'm trusting that you're very well acquainted with all of this and very up to speed. So I think I'm very happy to bring you in. Feel free to introduce yourself as well. You are actually in the Herschel Museum right now, aren't you?
I am. Can you hear me okay?
Yep, you're coming through really well.
That's
I will mute myself now. Over to you.
I'm loitering in our gallery extension where we normally put the exhibitions on. We have a temporary exhibition on at the moment, and this we named after Caroline, so Caroline Herschel, in her honour, when the extension was constructed a few years ago. I'm loitering around in the gallery extension at the moment, or into the garden. I will drop out and we may lose Wi-Fi or internet connectivity. But more than happy to give it a go, because I don't know whether you can see that we do have some sunshine here in Bath at the moment, in between some intermittent cloud. And I've even managed to, by setting up some telescopes in the garden at the moment. So if we get an opportunity and the weather permits, and I don't lose Wi-Fi connectivity, then of course I'm happy to have a go. So Charles has been excellent in providing some of the background information, of course, on William and Caroline. And this is the garden in 19 New King Street, where the discovery of the planet Uranus was first made on the 13th March 1781. Now, I'm sure you've seen the replica 7-foot telescope that we use here in the museum, made by Michael Tabb. It is the work, Charles may have told you, it's a working telescope. So we're actually delighted to be able to still use the replica. And one or two of us have been extremely fortunate enough. We've even managed to observe Uranus with it. But we're not allowed to move it around a huge amount. So because obviously, even though it's a replica, it's a fairly sensitive and valuable exhibit here in the museum. So the instrument that we do use for the public are modern telescopes. And we're fortunate enough, through funding gained through the museum here and through Bath Preservation Trust and various grants that we've been given over the years, to build up a small collection of instruments that we're able to use for the benefit of public observing. And I'm hoping at some point this morning we'll be joined by Simon Holbeach, who is our chair of the Bath Astronomers. So he'd hopefully be very welcome to join us if you see him pop up on the system. So as I say, the instruments we're using at the moment here in the museum, we have a sort of classical Newtonian Dobsonian, a sky watcher. We have a small personal solar telescope made by Leonardo. And we also have a refractor, a sky watcher Star Travel 120 mil refractor. And I can see Simon now coming in on the top of the screen. Hello, Simon.
Good afternoon. How are you doing?
Hey, at least you can join us. That's absolutely brilliant. So I've just been giving a very brief introduction here. We do have some sunny intervals at the moment. I can see a massive patch of blue sky over to the east here. But I was just saying before, you might run the risk of losing connectivity here from, of course, I'm not quite sure how powerful Joe's Wi-Fi signal is. And we are open to the public. So the other nice thing today is that we've had visitors, and I've been able to show
I'm afraid the signal we're getting is a little bit choppy at the moment.
We got some rather nice sunspots. Are you okay? Oh, it says my internet connection is unstable.
Yes,
so
we didn't get the last 30 seconds, I'm afraid.
Oh, okay. No, I was just saying we've been able to use the Coronado PST solar telescope this morning, as well as the refractor, using a Herschel watch, which actually was invented, I believe, or developed by John Herschel, the son of William, which does allow you to observe the sun safely. Of course,
we lost you again there, Jonathan.
Normally point a telescope or binoculars at the sun. It's the Bath astronomers, perhaps, as I'm dropping out occasionally.
Do you want to come in for a little bit, Simon?
Yeah, sure. So what is Bath Astronomers? It's a typical local astro society. There's hundreds all over the UK. Bath is just one of them. And it's got 56 members currently. But it's had an interesting career. It's sort of like our little badge says we were established in 1781. That's slightly tongue-in-cheek because we're actually established in 1976. by Bob Newman and Dave Ollis. But we like the joke because we feel that William Herschel is definitely a member of Bath astronomers. So yeah, it's been around since then. Like every Astro Society, it's had some very strong individuals leading it. And when they move away or do other things, it sort of gets a bit quiet. But we've had a resurgence. We sort of got reborn in 2019. And with a very, very strong link to both the Bath Preservation Trust, the Herschel Society, and the Herschel Museum of Astronomy, doing, I like to say stepping up the amount of outreach we're doing, but it sort of like went from maybe 1 or 2 events a year to 50 odd events a year. So we've really sort of managed to re-energize the community. Bath Astronomers is out for 3 things. Number 1, sharing astronomy with the local community in terms of sort of fellow astronomers, helping them get better at doing their amateur astronomy. And then finally, it's actually taking the astronomy out into the community in terms of schools, both independently, but also alongside Bath Preservation Trust and other bodies such as the Scouts, etc. So for 56 members, we kind of pride ourselves on being quite active out there.
I see we just had a question about the pandemic and how are things with public observing. You'll probably just notice that I've been put my face mask on. And that's because we've got members of the public here with us this morning in the museum. So when there's other people around, we're still encouraging people to do that. But the good news, I think, Simon, is that we have now started our public outreach observing sessions again. And we've actually begun our first face-to-face meetings as well once again. So not everything is on Zoom at the moment. But it's gently, gradual, isn't it, I think, with the public outreach and the observing sessions?
It's fair, yeah. We first went back into schools in September. So Hayward Prep, who we go and see 2 or 3 times a year, they reopened their doors in September to us. And we've got a couple of schools lined up over the next few weeks to go into. And on general observing, we've got sessions all the way through. So I think, gosh, we've got observing tonight at our observatory at Monkton Combe. We've got a scout session tomorrow night. Wednesday night is, I think that's a school club we're running. We've got sessions all the way through. So I'm actually trying to remember. So I think on Friday, we're helping support Wells and Mendip astronomers at their event at Wells Cathedral with the Museum of the Moon. So yeah, we're busy, but it's masks on, it's keeping the social distancing. But we've got to the point now where we've got ways of mitigating the risks, and we can run sessions and get people actually looking through. If they're sort of not able to come to our sessions, we're doing hybrid sessions as well. So they're both in person at the Herschel Museum and via Zoom. So you come whichever way you like. It's been an interesting time, but one of the things it's actually taught us is normally all our speakers are local to the southwest or the south. We now have the opportunity to get speakers in for our monthly talks from all over the world, for the rest of the UK. And so we've got Professor Lucy Green doing our October talk, and she's going to be safely sat at home, but she'll be talking to us whilst we're at the museum.
Yes, it's been really good in terms of speakers and putting on live events and things like this, isn't it? The pandemic's taught us quite a few lessons in that respect. Not quite so easy to do the live streaming actual physical observing, although I do remember we banned you to a car park with a webcam on one occasion when we were trying to do an eclipse, I think. Simon is certainly one of the most active members in our local community group. But the other nice thing, I think, Simon, is like all these societies, we have our links to all our sort of neighbouring and surrounding societies as well. We quite often sort of put joint things on as well, don't we?
Indeed. So one of the societies actually decided to, because of the risks, and it didn't have the sort of the people to run things like Zoom sessions, decided to actually close its doors. But what we did is we invited all its members to come along to our Zoom sessions. So all the way through the pandemic, they had invites to come to ours, and we're continuing to extend that through so that they've got the support. They can still get essentially their monthly hit of astronomy. So that's good. And as I say, those relationships are going on. So we've got a joint event with Bristol Astronomical Society and Cardiff Astronomical Society that we've got a whole Saturday devoted to extreme stellar environments, which is online talks that have been organised between the three societies. So what we've learnt during the lockdown period, we can take forward to give sort of a richer experience, not just to the local members, but people from all around the UK, all around the world that wants to get involved as well.
I mean, the other thing which, again, as we begin our sort of face-to-face observing again, and the school at Mountain Coombe is a great example of that, the hands-on observing is obviously we're building up a collection of quite good sort of instruments we can lend out to people to have a go as well. So not only if they buy their Christmas present and don't know which end of the refractor to look through or which way the mirror should be up, we can help them with things like that, or the dreaded go-to systems. If they can't work out how to find the objects in the sky, once they do become a bit more familiar, of course, you know, they can actually borrow an instrument rather than going and splashing the cash in the first case as well. So I think we've got some quite nice ones we can lend people out in our local area, haven't we now? Which is really good.
That's a key area. Lots of people buy telescopes. They don't perhaps find a society first of all, and we'd always recommend sort of getting in touch. You don't have to join, but just get in touch and have a chat. And they can make recommendations, those societies, the individuals in them, about what kit to get. And we find a lot of people walking past when we do outreach at local shows and things. Lots of people say, oh, I've got a telescope, don't know how to use it. That's probably our most common starter for a conversation that we have. So we encourage them to come along to our stargazing evenings and bring their kit, and we'll show them how to use it.
I just noticed on the chat, we got a question from George. What will you be observing tonight? Is it open to the public? Does it take place at the museum or somewhere else? Well, it's not at the museum tonight, although if you look on Bath Preservation Trust, we got Halloween at the Herschel coming up. So if you want to be really scared and freaked out by some crazy astronomers dressing up and some pumpkins in the garden, you're very welcome to try and book for that on the Bath Preservation website. But Simon, what's happening tonight, and is that open to the public?
Unfortunately, no. We have agreed some rules with the owner of the observatory, so it's only members at the Bath Observatory. So it's the community observatory based at Mountain Coombe, which is just south of Bath. So it's only to members for this evening. But as we learn and people get a bit more confident about the running of those sessions, we hope to open up to the general public as well. But we are organising sort of other sessions elsewhere. In more open spaces. The problem with the observatories is it's a little confined, so just controlling the in and the out. So we'll get better at that. Tonight will be a bit of a practice. So if you pop along to the bathastromers.org.uk website, you'll find some details in there as these kind of events get organised.
And I think you mentioned earlier this amazing Museum of the Moon, which I think I'm right in saying has been worldwide, let alone just over the UK, hasn't it? Now that's going to create a lot of interest, I think, amongst the local sort of community and just people who are fascinated by the art installation, I would imagine. So it's been in Bristol. I think it's going down to Wells Cathedral, I think I'm right in saying, and very shortly is coming up to Bath Abbey. What amazed me, I mean, apart from Simon dragging us up to the top of the tower at Bath Abbey the other night, which is hopefully where we're going to do some observing from the very top of the Abbey, which if you don't mind climbing about, I can't remember, was it 250 steps, something ridiculous like that?
212, I think it was, yeah.
Okay, it just seemed a lot worse. I mean, that's going to highlight a number of things, because although, you know, we'll be pretty much restricted to the bright planets, I know Jupiter and Saturn are particularly well placed at the moment, and I'm not sure about the moon phases. Hopefully, though, in the period that the installation is in the Abbey, we'll be able to do some observing of the actual moon itself. But of course, it's going to highlight other issues which we all face these days, such as the light pollution, and particularly from the middle of Bath. And I know, you know, some people like Charles and some of the other societies, and particularly Bath Preservation Trust, of course, with their planning permissions and commenting on planning applications, light pollution is a big issue for us here as well, I think.
Indeed, yeah, it's key. So that's one of the reasons why we popped along to Bath Abbey in the dark last week, is to see what the light pollution level was like from the top of the Abbey. It's much as we expected, and we'll stick to the brighter objects, the moon, the planets. So we've got Venus, potentially, we've got Jupiter, we've got Saturn. Uranus should be able to get from up there as well as things like double stars. So that's okay. So even though there's light pollution around, there's things you can always look at. There's filters you can apply on the telescopes, which give you a slightly better view than you would if you just look up through a little bit of the murk that's caused. But we can help. So there's organisations, local organisation we work with, which is Starlit Skies, to try and encourage and support things like the CPRE in all their activities to try and either mitigate or control light pollution.
It's amazing, though, what you can still achieve from your back garden. It's extraordinary, though, because with modern, I'm not a sort of keen imager in that sense, but even with a modern digital SLR camera mounted on a tripod, and even where I am sort of based between Bath and Bristol, if you have the right settings on your camera with a modern camera these days, it's extraordinary what you can get to image, even in relatively poor, what I would consider sort of fairly poor observing conditions, really. We've had a reminder, I think, on one of the chats here that in fact the Royal Astronomical Society did hold a workshop back here in Bath back in July, I believe it was, on the very subject of light pollution. And is it Bob Frosby, who is sort of one of the big main campaigners in that area, I think?
Yes, looking back, he basically comes from the science upwards to the problem. We look at the visual problem and try and understand it. He's actually looking at the wavelengths of light, exactly how they're produced within these lamps, what the effects on the human body are. So he's a really good advocate, having Bob Frosby around.
I think he's quite good at mentioning the fact to most of the commercial companies and industrial installations about the cost implications as well, and how you can save a lot of money by turning your lights off at night. So that always seems to work when you talk to the accountants anyway. George is asking, do I go to your webpage to become a member too? Well, that's extremely nice of you, George. We can recruit another member today. That would be absolutely brilliant. So yeah, absolutely. What would that make it? 26, 27? I can't remember now. But yeah, all the details, all the links on our membership. And of course, you don't have to live in Bath, do you, Simon?
But I will interrupt to say there's lots of local societies. I'd love to be selfish, but actually one of the benefits of being part of these societies is actually going up and meeting people and sharing sort of like the pros and cons, especially on things like that astrophotography. It's a really popular activity that people are going through or sort of taking part in now. And there's loads of stuff online which is helps you get over those first few steps of how do I actually get this to work. There's lots of things, just like buying a telescope for the first time. It can be a bit daunting. If you just point a camera at the sky and go click, then what comes out usually is a bit fuzzy. There's star trails all over the place. But once you actually chat to someone from maybe a local society, then usually within a couple of hours of an evening of just chatting whilst clicking away, you can actually go from sort of very poor to very good images just with your ordinary telescope or your ordinary camera. So yes, Bath Astronomers is there, but I would recommend any local Astro Society to get that kind of link going.
Simon, I was just going to interject and say the Federation of Astronomical Societies is not absolutely comprehensive, but for UK societies, it lists the vast majority, I think. Is that fair to say? You can find one in your area by looking on that website. I think there's at least, I don't know, a couple of hundred.
Indeed. And if you're not completely wedded to an Astro Society or sort of like you're not sure about joining, there are other services like Ghost Stargazing, which a colleague called Neil runs, and that collates all the activities of all the societies around the UK as well. Neil's got a bit, he's very, very active. So if you want sort of a single source, I'd always recommend going to www.go-stargazing. I think it's .co.uk as an address. But yeah, FAS is a great place to start as a list. Yeah.
I mean, the other thing you mentioned earlier is about Simon is about all the sort of public outreach and stuff. But of course, the other angle, which we're very fortunate enough to have, and I suppose I'm being slightly more selfish. My other hat is working for Bath Preservation Trust, is of course through the museum environment as well. So we're able, thankfully, due to Simon and the Bath astronomers, to host various sort of events. And Charles, I think, mentioned the Herschel 200 and the early sort of tentative plans for that next year. Bath Preservation Trust are quite involved in some of those aspects. A grant, which is being applied for the Director of Museums here, where we have a very tentative plan about some of the activities with the help of the Herschel Society, the help of Bath astronomers, the help of many sort of local volunteers that we have, enable us to sort of host a number of activities around that, both educational and in terms of an exhibition, but also the musical side. But at the end of the day, Simon and I, no doubt, will be in a field somewhere with a telescope, hopefully.
Just like tonight, yes.
I think the other thing that amazes me, and I'm sure, I mean, this is a wonderful example of that, isn't it? It's just how much now is available online as well, just how many events. I sort of can't keep track of the invitations to live streams and podcasts and lectures online at the moment. So it's the last 18 months, the pandemic, I think, has sort of changed dramatically the way many of the amateur astronomy community sort of tap into the resources, I think. So I think gone are the days where you have up at your village hall in the middle of winter with your flask and hope you might sort of pop outside and look through a telescope. I mean, it's been quite a revolution, I think, the last 18 months. I don't know whether you found that, Simon.
Yeah, so I'm also part of a panel, it's called Reach Out and Touch Space. So that's a bi-weekly panel that talks about space on Astro Radio Earth. But there's loads of those all over, people doing their podcasts, etc. All the great stuff the RAS is doing. So you've got the Supermassive podcast. So you were right, you could actually spend an entire evening just on these things and actually not get out and do observing. So you have to be a little bit careful. But what I've taken to doing is listening to some of them whilst I'm observing. So that's kind of a happy halfway house. But yeah, I'd still recommend trying to get that personal touch back into it. So societies are still key to actually getting people to talk to each other and sort of get over that hurdle of sort of astronomy is a great hobby to take up, but as I say, using kit for the first time can be quite frustrating. Finding your way around the sky is quite tough, doing it from a book or even an app that you're holding up and things like that. But if you've got someone sort of a few feet away saying, oh, and that bright star is that, and if you follow it down there, you'll see these stars. It's a lot better way, I find, to learn. And once you find a few of those sort of way markers around the sky, you can then start filling in everything else. And so given that sort of that first guided tour, you can start filling in the whole picture, and it's a lot easier than trying to open up a big star atlas and go, where am I?
Yeah, the dreaded Norton Sky Atlas, I remember it well. But I mean, I find that as well at the school visits and when we have school groups come here, because one thing that always slightly shocks me to some extent, like talking about the Milky Way, and you suddenly realise most of these children who live in the middle of Bristol or live in the middle of Bath have never actually seen the Milky Way, let alone sort of really appreciated what it is. So if you get the opportunity to actually get them outside and actually do some physical hands-on observing and get them away from their tablets than their smartphones to actually look up into the night sky. It's quite amazing, really, because you know, a lot of them just see these things for the very first time. They've never realised actually what it is, or they haven't particularly realised what that bright star over there actually a star. It's Jupiter or Saturn, and to actually the opportunity to look through a basic refractor or reflector. I mean, the rings of Saturn are always the ones to get people hooked, I find, for a lifetime on astronomy. But even sort of looking at the moon in detail through an average sort of amateur telescope is, you know, just blows their mind away, really. And I think that's a great way to get people involved. It says my internet connection's unstable again.
Oh, we
Sorry,
still hear you, Jonathan.
Are you hearing?
I was going to mention, actually, as well as the workshop,
okay?
I went to that workshop too, and I agree it was very good, and we are looking to do more of those, and we're trying to do something locally with the CPRE in the region as well. But I was at a conference last week, which was, well, two areas. One is called Dark and Quiet Skies Ubiquities, huge international conference, actually 700 odd people registered, and part of that was about light pollution the first 2 days, and a huge range of policy initiatives to try and control it. The slightly depressing news that I think there's only one city in the world, which is Tucson in Arizona, simply because it's very close to the Peak observatories, the US national observatories. They've taken really good measures. There are very few other examples of large cities that have done it, so you tend to be looking at protected places, but it is very important to the RAS. I was going to see if I can share a screen of the cover of the one we were using, which is probably down to me knowing what I'm doing here. Here we go. I won't make a mistake with the sound again, but if you see this, that cover image is a bit small, but Bring Back Dark Skies, you know, we do take this very seriously, and with a good review of that workshop there. So I would encourage, if you're listening to this and you have an interest in this area, we could certainly give you advice on the kind of things you could be saying to local authorities to control light pollution better. And there are actually other organisations working quite hard on this too at a national level. So fingers crossed, but I think it's a long way to go to get this under control. Actually, I think we've got an awful lot of work to do. But I know Bath has done good work in this area, I think. Have you seen any difference in the light pollution over Bath yet, or is it early days?
It's still early days, and I think we're still on the downward. The program of replacing sodium, high pressure sodium, with new LEDs with the high blue content. So, hey, you get a lovely white light, but that bounces off the roads, and taking a photo, it's one of those ones where we're taking the photos of the comet last year, and the amount of light pollution, you actually had to change your position. It wasn't quite as photogenic, but there was just too much light pollution. It was drowning out the comet above Bath. So that was a little bit frustrating. But as I say, bodies are sort of all joining together to see if they can help influence policy. And we're hoping, actually, in Bath, there's a lot of sports facilities up at the University of Bath, and they've their policy over the last 10 years has been to create great facilities and things like that. But unfortunately, the light's a bit too strong. So it's working with them now, with them recycling that kit and getting sort of upgraded tech. To say, can we lower the intensity of the lighting? Can we make it a softer color? Can we manage it that way? So it's not about telling people they're doing things wrong. It's about going in and helping them make better decisions when they're replacing kit.
And they do have a very active astronomy group there, so they must be your natural allies in this, I would hope, as well. So. Thanks. I can see Emma's coming in there.
Yes, sorry. I was going to come in with a very quick question we had from YouTube. I'm afraid I think this is probably going to be more for Simon than anything. We have from a Lazy Single Daisy who asked, I would love to ask the Bath astronomers if they know what Uranus means and that a dinosaur was named after this planet. Uranosaurus, I believe that's the correct pronunciation, but feel free to correct me.
I don't know.
No, that's fine.
I try to know lots of stuff, but I don't know that one.
Fair. Well, I said a new bit of knowledge.
That's
no,
a brilliant question.
I have no idea either. we might have to crowdsource this one, I think, Emma. See if anybody else can answer it.
We get. You mentioned there were no silly questions. Indeed, it's true, but we do get asked some real toughies. whilst we're out doing astronomy, as well as sort of the weird ones of, well, not weird ones, but that we do quite often. Did people actually land on the moon? That's quite a common one. But I was in a primary school, and one of the questions was along the
yes is the answer to that,
yes.
Simon.
Okay. Oh, okay. I'll use that next time. I think it was year 5 primary school was tell me about the distribution of non-baryonic matter in our local galaxy group, and I was saying either you're very clever, you're very interested, or your parents have set me up.
Yeah. Goodness.
But we enjoy it. We do it. We're going into a school, I've just remembered, actually on Thursday. So that's their year 6s. So we'll be taking in telescopes. So we'll be looking at Jupiter and Saturn as our primary objects, and also be looking at the moon on Thursday night. So again, just to inspire people in year 5 and year 6, where before they go into their secondary schools, where they're making decisions on science and things like that, to see if we can keep that inspired sort of angle on science. But some societies don't go for things like a reception in year 1s, year 2s. I actually find that some people have made their decisions about sort of what interests them as young as like that 5, 6 and 7. So we also try to go into the younger groups in primary schools as well, to sort of show them that it's a big wide universe out there, and there's lots of exciting stuff that they could be doing in their futures.
I think on that, actually, also I would encourage you, anybody who's qualified to do things like become a STEM ambassador, because you get things like a free DBS check, which is really convenient, a little bit of training in it as well, and they really welcome that. And you get connected to various groups that are interested in the speakers of the type you described, Simon. So strongly recommend that too for anybody interested in even occasional public engagement work.
Yeah.
So do we have any more questions on YouTube, Emma? I couldn't.
We did have a question, but if it was going to be okay, we have I'm going to apologize on this. Masa Yetsdi, apology. But if it's okay, I'm going to hold that question for a little bit later, because it's more to do with why we want to look at HD+. I think that's a great question for the Q&A that we have later. So apologies, we're going to hold on to that, because that is a gem of a question. I really would like to answer that later.
I have a question, actually. Something that always I wonder about is what, as a professional astronomer, I can do to help support my local astronomy clubs. What do you guys want from us as people working in, mostly teaching, mostly administration, and the odd weekend? When I'm working the weekends, I'm an amateur astronomer too, right? So what can we do to help you?
There's loads of stuff, really, because we all have our sort of programs to go out and do outreach. Actually, sometimes it's more effective if we do it together. So the amateurs and the professionals go out, because the professionals can seem too distant, and bringing the amateur in as well sort of says, and you could do this in your back garden, and this is how you do it. So that's a good balance. But for us, it's quite hard to reach out to get in sort of like what's the cutting edge. So things like getting hold of speakers. One of the things I really enjoy is talking to someone from a university, and they say, I'm sorry, that's not my field, but I know someone. Tell you what, if I give them a ring, I'll let you know if they're interested in that kind of thing. And sort of making sure that this big wider community is actually connected as well as it can be. To sort of, there's some absolutely amazing astro speakers out there, and I sometimes feel they're hidden in university departments. And I want to bring them out and give them an audience. I've got an audience. I just want to find them. So sort of promoting people both post PhD and before as well. Sort of as you're doing your PhD, sort of everyone can benefit from having a little bit of a chat to the general public, the informed general public, and going through that. So those are the two areas. Sort of get us more involved in some of the outreach, because we'll pull you into our outreach as well, but also that technical expertise and speakers and things like that would be sort of an easier way of getting speakers. Every astro society has problems getting speakers. So that would be absolutely great.
There's a lot of comments coming in about the role of amateur astronomers as well, and sort of some of the areas and some of the work that they can do that isn't necessarily covered by the professional side as well. I mean, we've got quite a few observers who specialize in things like observations of variable stars and things like that, and there's huge communities out there of amateur astronomers who contribute in more detailed sections of organisations like the British Astronomical Association, organisations like that, where they're making constant, regular observations and feeding their results in, which then the professionals then go on to use, don't they? I believe so. It's,
there's a great heritage there. Our colleague was on, I think 2 days ago now. Lee Fletcher has regularly used amateur observations, sustained observations over longer periods of time to bookmark the kind of observations we can make with the larger telescopes, because frankly we can't spot things. You know, we have 1-2 nights every 6 months if we're lucky, and there's always interesting weather systems forming, and there's always the chance of impacts on Jupiter. We saw another impact a couple of weeks ago, and you know the gears start grinding very quickly when one of those impacts happens. You know, if we happen to be observing Jupiter, I get lots of calls from colleagues that don't usually call me saying, is there any possibility that we could have a couple of frames of images at different wavelengths to see whether we can see anything? So it's really it comes straight through. The work of amateurs is absolutely intrinsic to a lot of the science that we do.
Particularly comet spotting. Caroline was a fine example, of course.
Exactly.
So there's always a good chance of spotting a comet. And Simon, you're a great meteor. You've got some kit set up, amateur radio kit set up for meteors, I believe.
So I do radar reflections off the Grave radar station in France, which picks up meteors that are going over the Med, but also just to join the UK Meteor Network. So I've got 5 cameras, or it's actually Bath Astronomers effectively. We've got 5 cameras that are looking north, south, east and west, slightly overlapping, so all the way around. And that's going in, that's being sampled every night, and counting meteors, working out where the radiants are. And so that group, with people like Mark McIntyre, who helps run it for the UK, they're finding new meteor showers from what they do. So having that kind of huge sort of amount of cameras, and it's also the kind of thing that's it's like networks like these that allow us to find meteor falls as well, meteorite falls. So the more cameras you've got pointing up. So the Winchcombe meteorite, helping to track down where that hit, that was part of these amateur networks, which is people just, effectively they're just security cameras. Instead of pointing at buildings, they're pointing at the sky.
So I hope your neighbours have been warned.
Yes.
Some of that footage was from sort of doorbell cameras and dash cams and so on, wasn't it? That's exactly the stuff that they just looked in the morning and thought, wow. And yeah, I mean, I'm always struck by the fact that you see these incredibly bright meteors in in this footage, and hardly anybody's actually seen it, but it's been captured because it's sort of 3 o'clock in the morning, and yeah, absolutely remarkable. So my colleague on here was part of the team that went down to Cheltenham to Winchcombe, and they had to keep it quite quiet actually, because they didn't want meteorite hunters who might grab the findings and then try and sell them from an extortionate price. So yeah, apart from the one on the driveway, they then were combing through fields around Cheltenham for a few days until they got lucky and found some fragments.
And now even the driveway is gone.
Has it? Yeah. Has it been resurfaced?
But it's been. I think
been filled in.
The Natural History Museum, they've cut a section out of it, and it's gone to London, I believe. And the family, is it the Wilcox family? They've got a new driveway, or it's been repaired, or there's a plaque where it fell.
I think that's a fair exchange, isn't it, really, for donating a valuable meteorite to a museum to get them to cover the cost of the damage it made when it hit your drive. That's brilliant. So there you go. If a meteorite lands on your driveway, I think I can reasonably say that the NHM will foot the bill for repairing it if you give them the meteorite. Don't know if there's anybody from the NHM on the call here who may argue with this, but it seems like a fair exchange. So.
Well, if it hits your brand new Tesla or your Porsche, they might have a different view. But
act of gods. Yeah, I think then they might take the Tesla off your hand and put that in the museum or something instead. So we'll see.
Yes, and even if you're not looking up, if you're online, then there's all the Zooniverse activities that citizen scientists can take part in. So sort of it's a wonderful period to be around in, so that you can actually contribute just as that amateur with an interest in a lot of these programs.
One of the questions that had come in was about when there are next good meteor showers coming up. Now, there's always caveats on this, because good for amateur astronomers would say a few an hour is not necessarily the most visually spectacular event for the public, but particularly if you live in a city. And I looked at while we were talking, the International Meteor Organization keeps a good record of this stuff, and the best prospect, I think, it's not ideal. There's one called the Geminids in December, which the moon is about 4/5 full. So I think probably for that one, it'll be people who are very patient and prepared to get up about an hour and a half before dawn and look out for it then, when the moon should be mostly out of the way. But there are various lists of these things. There tend to be a few a year that are really strong and good too, and we recommend that people go and look at those, or if they've got clear skies, obviously. And then I don't know anybody, Simon or Jonathan, you might, is the Quadrantids presumably after that?
In January the 4th peaking.
What are the prospects for that this year? I wasn't sure.
I haven't looked at the moon phase for the Quadrantids, so I don't know. Right at this moment, I think we've got the Draconids, and then that's moving on to the Orionids as well later on in the month.
And they're all fairly low numbers, aren't they? I think, in terms of what you'd actually see. I was just wondering.
Just bear in mind, last week. Oh, sorry.
No, I was going to say there's always a good chance of a sporadic as well. So it's always a pleasure to on any clear night you stand a good chance of seeing some sporadic meteors, which can be quite significant in their own capacity, of course. So it's always worth looking out.
And what I should say, when we're referring to the moon is the natural source of light pollution. Although it's a stunning object. I mean, I wrote a book about it, but although it's a stunning object, it does light up the sky. So when there's a full moon in the sky, it's absolutely stunning, but at the same time, it makes it harder to see faint meteors. So astronomers, you'll often hear talking about the times when the moon isn't around, when they can see the faintest objects more easily. So
I'm not sure if you can see my screen now.
I can see that you're sharing something, Simon.
But if I go to...
The signal's taking a little bit to come through. There we go.
There we go.
Okay. Oh, it's not working.
I can see something up on my screen.
Was actually the output. Yeah, it's not working. So, okay, it's it's very slow, but this is just a view. So these are what the cameras that we've got monitoring over Bath are taking.
That's coming up. That's coming
one
up.
Of the major things you see is there's lots of annoying aircraft.
Do you find that you're getting sort of increasing?
This is just from overnight.
Do you find you're getting increasing issues with satellite trails and so on as well? And there's another part of this conference I was at, was the problem they present.
We do. I think we recorded last week on one of the cameras 435 meteors in one evening. No, it was Starlink. We had multiple passes of Starlink, and it just perfectly hit the sensors, and the algorithm picked them all up. So actually caught the entire evenings of Starlinks going across. That's how we had 435 meteors. It was actually satellites.
Okay, while we were on this, I also checked on the Quadrantids, which is the 3rd to 4th of January, I think you were saying. That actually has really good prospects. The moon is new. So, 3rd or 4th of January 2021 is the next best chance to see a really strong shower. If you've got clear skies, of course.
And the dark adaptation and observing later at night is quite key as well. So we always recommend people allow a good 20, 30 minutes. Find a dark site if you can. Allow your eyes to sort of get properly dark adapted. Use a red torch. Don't switch your light on your mobile phone, because you'll just blind all your amateur astronomers around you. So red torches are always good. And again, you can set up your SLR on a tripod. Just let that run for short periods, and if you're really lucky, you might capture some photographs or some video footage of them if you haven't got the kit that sort of Simon's got to do it. So it's always worth looking, and a good time of season, I think, Simon, for noculent clouds as well. I think as well this time of year, with the extremely high atmospheric clouds.
They're out of season, but. Yeah, I wouldn't really go out looking for them this time of year.
Okay.
Right, I'm going to bring this to a close now, I think. So thank you very much to Simon and Jonathan, and I hope the Herschel House is in good shape, Jonathan. It's a pleasure having you on the call and, telling people a great example of an amateur astronomy society. But as we must stress, if you're watching this in the UK, there are hundreds. There are also obviously many around the world in different countries across Europe, North America, Asia, Africa, and so on. So, please, if you're interested in actually doing things like looking through telescopes and you don't own one, they're great people to help you with that, or to show you how to use your own telescope and to, to find out more about this science. So my next job, I'm going to sign off in a minute, is to introduce our next co-host,
Cheers.
Dr.
Thank
Rosie
you.
Johnson. Thank you very much.
Cheers. Thank you.
And it's my great pleasure to bring Rosie in. I can see her now. Brilliant. Okay, we do need to do something like make her host, or I think if I make you co-host, there we go. Excellent. You are spotlighted. Brilliant. Emma's doing a lot of these controls far faster than I am, I have to say. Probably, yeah, that's great. Okay, so Emma has a very interesting pedigree. I was just scanning through very quickly, and it says you're now at the University of Aberystwyth. Are you still an associate lecturer there? Sorry, Rosie, rather.
Yes, yeah, I'm an associate lecturer at University of Aberystwyth.
And I see from the description on the staff website, which is much more informative than some are, I have to say. I think you worked as a teacher before, but it says that you have experience in the outdoor education outreach sectors. You worked as a whitewater raft guide in Austria, a Northern Lights guide in Finland, and as an education coordinator for the Royal Society of Chemistry. So already you've got a really interesting background to take us through into the afternoon. So I'm going to hand over to you at this point. You're in the very capable hands of Emma and Rosie, who will be taking us through to the afternoon. Two brilliant co-hosts to carry on with things in there. So thank you so much, everybody, and I will leave you to it.
So I'm going to say thank you so much, Robert, for all your hard work today. Thank you very much for your hosting this morning, and thank you for also just taking on, as I said, you've been a great sponge to take it all in terms of the live streaming. So that's really, thank you so much. Again, we want to reiterate, thank you so much for our Bath astronomers today, as well as all the speakers that have arrived today. And again, Robert, thank you so much for being here. We hope you have a very lovely and calm and a relaxing afternoon this Sunday.
Bye now.
So, hi, Rosie.
Hello, Emma. How is it going?
So it's going very well, actually. So I have spotlighted us both. I've also got Tom. I might unspotlight us so that we can just focus mainly on what's going on in the background.
At the observations now. Let's see what's going on.
So we are now, where are we? We're about 4 hours in, so we're midway through our observations at the moment. So we're 4 hours of looking at Uranus. I do have some fun things to show a little bit later. I think Tom is trying to show us the Q2 line again.
No, this is a whole other line that I have found. So this is the Q11 line that is out slightly below and to the left of the really bright Q10 line. So I have now identified, I think, 5 lines in the data. I've been looking for a sixth, but I can't see it anywhere. But you can see that coming through really nice and cleanly.
That's great. So I'm a little bit behind on this because I didn't join yesterday, but these lines look a little bit more bright than on Friday. Is that a thing, or am I just getting excited?
I guess my 2 cents at the moment is that we are seeing variations that are going on the planet. I don't know today. Today's been a bit of a mixed bag on that one. Friday we think we saw some real good patches of highlights that were coming through, but I didn't on Friday, and that's my own fault, actually go looking for many of the other lines. I just saw the Q1 and Q3 and got excited that we were able to see those. So I have a sneaky suspicion we might have been able to see some more lines if we were looking for them. Otherwise, I don't know. As I said, we've got some great conditions for observing at the moment. Tom can probably back me up if I am saying this correctly, but I don't think we have any cloud cover at the moment. I don't think we have any clouds that we need to worry about. So that is some grand positives when it comes to observing. We've mentioned a lot today that even yesterday we had a discussion with Ophelia on the pluses and minuses of doing observations in space and doing observations in at Earth. And one of the big things is obviously issue of weather, whether it snows at the mountain, whether it's raining on the mountain. These can be very big factors of whether or not we actually get to look up at the sky. So, and even from that, depending if we have cloud, that may cause our image of Uranus to appear more blurry and be harder to actually see a finer detail on Uranus. That's something we have to consider. I'm just trying to think if there's anything else to kind of get you up to speed here. I mean, you're welcome to ask any other questions for yourself there, Rosie, if you want to get a little bit more up to speed. In terms of the moons that we have Umbriel up at the top of the Uranus cam. I'll see if I can get my mouse over. Here we are. So that's, I believe that's Umbriel. We then have, I think, Ariel just over here, and then just above where the green box is.
Somewhere in here.
Yeah, is that Miranda? Was that what we were discussing earlier? I
can see it in our actual data, but the compression has washed it out by the time it gets to you guys. It's very weakly seen in there. Yeah, the weather today is really good. It's really clear. The seeing's really good, apparently, although I'm not convinced from our observations that it's quite as good as yesterday. We've never seen a clear view of the rings like we did yesterday, and I think that's quite telling. I think that maybe the atmosphere was just a little bit crisper at the wavelengths we're looking at, and at the whether there's some slight variations that are happening on longer timescales. I'm not sure, but still very good, very clear.
So definitely more than the 1 or 2 pixels that we usually get to see, or as we get to see with, as you say before, with the brown dwarfs that Sarah was telling us about earlier. So I'm just making sure that I can't actually see my other screen on the Zoom at the moment. I want to make sure that's still being viewed.
Yep. Yeah, we can see it.
Yeah,
okay. I can't see it on mine. But
I'm going to try putting my arrow where I think Miranda is, which is right here. Mm-hmm. It's not easy to see, but hopefully you can see it's a little bit lighter right here.
Oh, I think, yeah, you can see it.
It's much easier to see when you add them up a little bit more, but
yeah,
it's a little difficult to do that.
So what is Uranus's rotation rate?
That's a good question. So Uranus's rotation rate is about 17.24 hours. So one Uranus day is slightly shorter than one Earth day.
So, and you've got how many hours of observation? So you've had
maths. All right, yes, fun maths here.
Well, basically my question is like, how many times has Uranus like rotated like during your observations?
That is a good question.
But so, yeah, like more than once, right?
Yeah, so in the 3 days that we've been observing, it's been about
3.
Well, it'd be 3 and a bit. I don't know if we're going towards 4. I'm just doing some quick maths now. So we have 24 hours, 17. So that's 7. 3 7s is 21. So I think we will have had 4 days at Uranus.
Okay, that's really cool.
The weird that said it was quite remarkable when putting this proposal together, because I wanted to at least have a good couple of days together, because one of the issues, I was stressing this before, was at Uranus, if we leave it for an amount of time, so let's say back in 1986 we took observations, and then the next time I think we got to take observations at Uranus again was back in the late 1990s, so it'd been almost 10 years. And as we were mentioning, the error on the rotation rate that we have for Uranus, though it doesn't seem large, it's about 0.01 out of those 17.24 hours. And when you say it like that, you're like, oh, that's really good, isn't it? But unfortunately, you've got to remember that's for every single rotation of Uranus there is, and in a year there are a lot of rotations. And because of that, the error just keeps building up and building up and building up and building up to the point where I think it's after 3 years we have a error on any point on the planet as about plus minus 360 degrees.
Okay.
So it means that we basically lose track. Yeah, we lose track of whatever's going on Uranus. So it is incredibly vital to have as many observations on Uranus with a known object, And one of these known objects is the Aurora. So we're doing our best at the moment to see if we can, not only with today's observations, but also with, we have a set of observations in December, I believe, as well, that we can use to basically see where the Aurora is, if it matches up with where we expect it to be. And if it doesn't, how much does that vary? And that can actually help refine the error that we have for the year planet's rotation. So exciting stuff that we are doing, the groundbreaking stuff, I suppose.
That's really interesting. I never thought about that. I guess maybe I take Jupiter's rotation rate for granted. There's a lot more, I guess, resolvable features.
The wonderful thing with this live stream is realizing that I feel like I've taken a lot for granted with Uranus. As Sarah was saying, she only gets a couple of pixels and I only get about 21, 23.
No, it's interesting. It's funny. It's funny because well, we basically do the same thing, but at the same time it's so different at Jupiter and Uranus and brown dwarfs. So it's kind of funny to really experience those differences.
Yes.
I did have another question, but I forgot it. I was asking you about the rotation. No, hopefully it'll come back to me. Oh yeah, no, there it is. So as you said, you wanted to observe more than one day, and that was something important for collecting the data and for what you want to do with your analysis. But is there a reason why you asked for these observations in October? So obviously you just mentioned that there's some in December. Is there a particular reason for observing Uranus at this time?
So apologies, I'm just getting up. I think my other camera, unfortunately, or other screen decided to keel over. So I'm just getting that up at the moment. There we go. Hopefully that's back to spotlighting. I will just make sure that this is the same way for everyone. Fingers crossed. Yes, there we are. Apologies for that one, everyone. Thank you for bearing with us there. So the main reason we were looking at, originally when we put this proposal to IRTF, we had asked for in a month's time, essentially, because that was when Uranus was closest to Earth. A great way that we can get more pixels at Uranus is essentially just being a bit closer. So Uranus would take up a bit more of the screen and we get slightly better resolution. It may not be masses, but every little pixel does help when it comes to this kind of work. So we had originally put in for this time, but we did say, look, at the end of the day, as long as we can get some time around November, that would be great. So we have on either ends of November, so we have observations in October and we have observations in early December. But as I said, we're not going to be here going, oh man, we haven't hit exactly the closest, because we are talking, I think, 0.01 of an arc second. And what I mean by that is oh god, I'm trying to remember exactly. So there's degrees of the sky, and then there's arc minutes, which are 60. There's 60 arc minutes in a degree, if I remember correctly.
Yeah, I think so.
I believe that's correct. And then there are 60 arc seconds within a arc minute. So we are talking 0.01 arc seconds. So that is, I'm trying to put through the numbers here. I think that's divided by 360,000 of a degree difference. Which, honestly, if you say to somebody like that, oh man, I'm missing Uranus, to be just 1/360,000th, 1/360,000th larger, someone would be there like, I don't know what you're complaining about, you're overseeing Uranus. Just get on with it. So as I said, no, there are no worries. We're happy that we have our observations, and we're happy that we have double observations. And anything I have to again thank our colleagues in Boston, actually colleagues now, both Luke and Omakshi, who had joined us yesterday as observers, and were running in the background, kind of doing the making sure that Uranus is where it's supposed to be, as well as taking the lines. And yeah, Luke put in for time in December with IRTF again. And again, I have to thank him for all his patience. He was additionally helping us out with the Keck proposal that we sent off. Pretty much the same idea here, and we're hoping to send another one back to Keck because unfortunately they weren't interested in taking on our proposal this time. So we're going to try again next year.
Well, yeah, try again. It's a lot of luck in it, isn't it? So well done for getting that first proposal in, and very well done for getting this one successful. That's amazing as well. Like we're here, so you know you did one thing right, so that's you know must be good. They just didn't realize it was good.
I'm sure they will do. Also, I've got a very grumpy cat that's decided to join me. I'll see if I can lower down perhaps the camera. There she is. She's my little observing companion, but she's complaining. I think she's going to be complaining because I haven't put her lunch down just yet.
Oh, yeah.
So I will probably have to dart off very quickly to go sort that in a second. But in the meantime, I wanted to just touch up on a couple of questions. So I've been sent a question from a friend who's watching the live stream. Hello. And they ask that there is what appears to be a green line that is close onto our slit. I think this is perhaps a way that we can kind of describe the green line that you're seeing in, I believe it's the Kyle, we're seeing in Kyle, is actually one of the ways that we go about trying to pull objects into our line of sight of the slit. So it's not something that we're seeing in space. It's not a green line that's invading us from space. As Tom is now pointing out, it is basically something that we can draw on the imager itself, and we use it to drag in objects. So we'll click on an object such as Uranus. If it's not on the slit, we'll pull a line and we'll pull it in.
So if we wanted this moon up here to appear on our slit, we would draw a line from there down onto the slit like this, and then we would offset the telescope, and it would know to follow that line, which is really useful. It's a great way of getting ourselves around.
Although I always get muddled up and like click on the wrong way. Get upside down.
It's incredibly difficult when arrows to know whether you're moving the object with the arrows or you're moving the telescope, and of course those are the opposite of each other. So
that sort of brings us to a question we just had in the Q&A from George. So he's asking, how many people does it take to do an observation? Is it ordinarily a lot? I feel like this time we are having a little bit of a social. I don't know if Tom and Emma feel differently, but obviously when you're learning how to do the observing, you wouldn't want to do it yourself, but once you have got to grips with it, it is possible to take the observations by yourself, but it can be boring.
Yeah. So Nahid is currently observing. His experience of today is much less interesting than ours. It's just sitting and making sure nothing's gone wrong continuously, basically.
Yeah, that is it. And sometimes, because I don't know how much this has been discussed over the weekend. It's probably been mentioned, but we have these things called macros, which are programs that you can sort of tell the telescope to automatically run through a program of the observations that you want to take. But if you take your eye off the ball and the telescope suddenly loses guiding, then it'll like go off and ruin your observations. So it's nice to have at least like more than one person just in case.
Definitely. Just last night when we started up, Nahid spotted that we'd not put the slit in. So we were seeing Uranus on the imager, but we weren't seeing that little gap where the light goes through. And so, we would have spotted it pretty quickly because we wouldn't have seen a spectra of the star and we would have figured it out. But it can be incredibly useful to have more than one pair of eyes on these things. These observations are much easier than some of the other observations we do, like the Jupiter observations are a lot more involved because instead of taking a single slice at a single position, we are scanning and trying to build up much more interesting pictures of what's going on, which is more useful in many ways for the science, but much more limiting. And I think sometimes we train students up. So certainly yesterday we were working with my most junior PhD student, and so that was their first chance to really get to grips with it. And so there was obviously a lot more chatter then, working on what does everything mean and how do we work things. And then if we're on a big observation, so if we're at Keck, for instance, that's a much bigger deal. We are fairly au fait with how IRTF works, but usually if you manage to get time on a really big telescope, you want to make sure everything goes right. So in the past, we've had quite fun sets of people going out, with people from Boston, Japan, here, all meeting up. So there is almost like a mini conference workshop. 2 people will be on the telescope trying to make sure everything's working. I usually sit near the back and just think about what we could do better, and then work on sort of longer term, several hour long plans of what we might try next, what's the next object that might be coming up, things like that. And then always just talking through the science as well. It's a really great opportunity to think about. So just observing this morning, very quiet, just me and Nahid. Once we got the guiding going, I've already come up with ways to improve these observations for next time. So there's always things to think about and things to improve on.
And it really does depend on the telescope, because as you said, it's different for Keck. But say we were observing different objects, say we weren't doing infrared or something, sometimes at some telescopes they have like a queue system, and you say what you want to observe, and then the telescope operator, they might do more of the work. So I think in these observations, we as astronomers are actually quite involved, whereas other times at IRTF as well, like the telescope operator might be doing more.
Yeah, definitely.
So I think our observations are quite involved. They are quite like task heavy. You do have to pay attention the whole time.
IRTF's pretty hands-on. It used to be even more hands-on. Things have gotten a little easier now. We used to have to focus the telescope ourselves and everything, whereas there's automated procedures for that now. Keck is pretty hands-on too. They do focus up and everything first, but you basically have quite a lot of control. So we're like VLT, which is usually on a queue system, but you can sort of tag into that queue system and go to the telescope and do the observations. But there you have a support observer with you at all times and a telescope operator, and the telescope operator has a lot more control than they usually do. So effectively you're an advisor. You're not really doing the observations yourself at all. You tell the support observer what you think should be happening, and there's a lot of discussion time before about what you want to do in terms of observations. And then both Gemini and VLT typically are just remote. So you write a program that says what you want to do. We're fortunate that a lot of our observations are hard, and so they don't like the idea of doing them by themselves. And so they tell us that we have to visit the telescope to do the observations. They worry that it's too complicated and they'll get it wrong. So we're in the joyous position that the telescope is telling us what we have to go, whereas most observers are told explicitly that they can't. So that's quite nice.
I was going to add, I'd noticed there are a couple of questions we have on YouTube, which I think are probably good, probably just for a recap for anyone that has been joining us this afternoon, who are asking, first off, where it is we can see Uranus in this picture, because again, everyone's very used to seeing Uranus with the visible, and that being the very blue color, and here we have extraordinarily yellow planet. In comparison, equally, we have questions if we're working in ultraviolet, and I think that's because of the colors that we're using. I'm sorry, I'll take these questions, if that's okay with everyone.
Go for it.
So Uranus, we are seeing, again, I'll see if I can get my mouse, it's this bright ball of light, almost looks like the sun in our imager, but we promise this is Uranus. The way that we can tell that this is Uranus is the moon, the moon's around it. So at the moment we have Umbriel up at the top, we have Ariel just to the side below the slit, that's the black line that you're seeing just over the planet itself, and possibly a third moon around this area, but it is quite hard to see, unfortunately, due to the compression of streaming in from Zoom. So we will mainly just focus with these two moons up at the top of
Tom's just moved his arrow onto, you can see it really
right
faint.
there. I can see it.
Yeah,
I have
I feel
astronomer
like I
eyes
can see
though.
it now too.
I can see almost anything in blurry messes now.
So that's where Uranus is. The question about ultraviolet. So we are in fact using infrared, but our images that we're seeing are in purple, and that's because we can choose which color schemes that we decide to look at the data. You've got to remember when we're looking at data itself, and again, I promise I've had this a bit, but at the moment we are shifting positions where Uranus is on the slit. I promise you Uranus hasn't suddenly duplicated and become two planets. This is a in-between shot of us shifting from the position B to position A, or A to position B now, I think. In fact, yeah, Tom is now demonstrating, in fact, we can change the color schemes. So this is what we get from the images. It's simply a grayscale image that lets us know how much light is coming from certain objects. To assist us with viewing, we can decide to pick very funky colors, such as the blue here that Tom has picked. It is honestly just a preference of the observer on the day, on what they decide to pick. Religiously, we tend to use a color scheme just called bb.cm. I'm not entirely sure what the whole stands for. I presume color map is probably the .cm, and we tend to use that more because it my knowledge is that it is more towards the red and the yellows that we kind of more associate with infrared, but obviously there are purples which don't help when it comes to trying to explain why it's not ultraviolet. So apologies on that confusion, but thank you, that was a great question.
I've always been a fan of rainbow, but I've been shaded down by everyone else, and so
I'm not going to lie, Emma, I'm fairly sure I remember observing with Henrik and Tom, and then I was like, can we change the color scheme? This one is pink. And then I always
some of our team are very much more vociferous than other members of our team about preferences of color. I have a mild favoritism for this color scheme because I think it picks out weak signals. Look, you can now very clearly see the third moon Miranda up against the background. Clearly. It's very clearly there. Yes, absolutely. But there are some members of our team that are almost religious in their reliance upon the BB, whatever that means, color scheme, which is the one that you've all been seeing. Yeah. Out of a sense of harmony, since some of us don't care so much, we use this color scheme for their delicate sensibilities.
So I spotted we had another question in going, again, I think this is just touching up, I did mention a little bit, which is why is there sometimes two dots for Uranus rather than one? And again, that's going back to the nodding. So Dr. Sarah Casewell was discussing about this with her observations, and we do it with our observations, where to mitigate the effect, or when I say mitigate, I mean to get rid of the effect of the Earth's atmosphere, we will take a picture, we'll take almost two pictures, one with Uranus at position A on our slit and one with Uranus on position B on our slit. The reason we do that is because in one picture, Uranus will be at A, and we'll have the atmosphere and Uranus
just
at A.
Pull up right now. This is what we could see. If I go down to the buffer A, this... no, that's not it. I pressed the wrong button. Hold on. We want this. And then buffer A. No. Yes. So this is actually what we see at the same color scale, and what you can see is it's very bright. Everything is just super bright, and the reason it's super bright is that we're looking through the Earth's atmosphere. So in comparison to the brightness of the lines we've been seeing, this is what we see. So it's not very useful. If I change the color scale, you can see that there's a lot of really bright stuff, and we can't see anything from Uranus at all here. All of this is the Earth's atmosphere. So you can see these really bright emission lines across the whole slit. That's Earth glowing. So we're at a temperature regime where we're looking at a wavelength where the Earth's atmosphere is incredibly bright and glows with incredible brightness. So we have to get rid of this somehow. And so that's what we're doing. We're subtracting this brightness out. Sorry, Emma. That's how you end up with this mirroring here. So you can see the positive and negative here. That's two separate positions. And what that means is when we're at the bottom here, we can use the top bit to subtract off and get rid of everything. And then we're at the top, we can use the bottom bit to subtract off. And it basically gives us a measure of just Earth without Uranus at all. We're just measuring the sky everywhere up here when we're down here. And we could subtract this really bright emission from the Earth away and just leave what isn't the Earth. And that's why we have to use two positions, so that we can bounce between locations to always have a measure of both the object and the sky.
Awesome. Thank you very much for that, Tom. That was a better round off than I would have been able to. Thank you. So I was just thinking, so we're now coming up to about 1:30-ish. And I wanted just very quickly to go back to our lovely schedule that Lucinda had put together for us and presentation slides, just to reiterate for anyone that's joining us in the afternoon where we are. So let me just share my screen. There we go. So for anyone that is now joining us in the afternoon, I say the afternoon, it's not the afternoon everywhere, it's afternoon for us here in the UK. My name is Emma Thomas. I am the lead astronomer today on the observations of Uranus that we've been undertaking for the last 3 years. I'm joined with my supervisor, Dr. Tom Stallard, who also works at the University of Leicester, as well as our wonderful and esteemed colleague, Dr. Rosie Johnson from Aberystwyth University. So we're now on day 3 of our observations. Just making sure, there we go, at IRTF, which you can see here on Mauna Kea. We are using specifically the iShell instrument, which has been around for about 6 years now. So it's getting on in its age, but certainly not the oldest of instruments, I wouldn't believe. But it's been incredibly useful for our research, not only here at Uranus, but looking at Jupiter, as well as looking at Saturn. So we are very interested in seeing all the data that are coming through for today, and we've kind of discussed a little bit about the results we've been getting in. Again, I want to reiterate we have quite a few notable mentions today. I noticed Cinda said sponsors, but I think more in terms of the organizations that it wouldn't have been possible without to do today's observations. So we have the Royal Astronomical Society, who of course is leading the live stream today. We have the University of Leicester, the School of Physics and Astronomy. We also thank the Herschel Museum of Astronomy for the wonderful speakers that we've had, as well as the videos and information, and the Bath Preservation Trust. So today we're on day 3, Sunday the 10th of October. We are currently on our 3rd day of program. So we're now about 1:30, where we're now going to be going back to the telescope view and a slight bit of discussion with ourselves and Q&A. At 2 o'clock, hopefully, Rosie will be talking with yourself about some of your previous research that you've done with H3+, looking at Jupiter and kind of getting almost doing very similar investigations that we're doing here, but just at another planet. So it'll be absolutely fascinating to get a further discussion with yourself on that. At 3:15 will be another Q&A session. That's with myself, Tom and Rosie, and perhaps a couple of members of the H3+ team. It will depend if they are about. If they are, then we'll see if we can rope them in to have some further discussions. And then from 4:15 onwards, we will continue to look at the telescope as Uranus makes its way across the night sky. We have until, I believe, about 4:55 a.m. in Hawaii time. That is 4:55 p.m. here in the UK. Actually, I think it's 5:55, apologies, in Hawaii Standard Time in the morning for them. And at that point, we are pretty much about 10 minutes until the sun rises in Hawaii. So that's the point where we're going to have to start signing off, as we won't be able to see Uranus past the sunlight coming in. I'm just going to stop sharing this. So there is today's wonderful schedule, or the last of today's schedule. Just trying to think of anything else to kind of come up. Do we have any more questions? Or have there been any more questions that have been pointed our way? I know we had an excellent question, although I kind of wanted to keep it for the Q&A later, but I'm happy to bring that up in general. I said it was an excellent general question. Let's see if I can scroll back up again. Where are we? So Masa Yazdi has specifically asked that they had a question from yesterday's topic, and I think that's with talking with Professor Steve Miller, which was wondering why detecting and studying the spectrum of triatomic hydrogen ions, so H3+, was such an important discovery. What can we learn from H3+?
Oh, there's so much. Yeah. There is a lot that we can understand, not just about the planets, but about whole vast range of different topics. I had the honor of writing a review paper on this with Steve, Tom Jabal, who is one of the most eminent infrared astronomers in the world, and Jonathan Tennyson, who is the person that basically cracked the understanding of the theoretical constraints of H3+. So what an honor for me. That paper had 650 references in it. It's a huge array of different types of science that H3+ has unlocked. Obviously, we've been talking about the stuff that we've done here. Steve mentioned some of the things that have been unveiled. One of the things that I found absolutely fascinating from that study that's quite recent that Tom Jabal was writing about are studies of the center of our galaxy, where images and measurements of the redshift of H3+ has shown that our galactic core is expanding incredibly quickly, so fast that it means that you don't have to go very far back in time before it reaches a 0 point and it's all gathered together. And that's really strongly indicating that in the past our galactic core was incredibly active, not very far in the past, we're talking millions of years, and that it's likely that all galaxies have a cyclical expansion and compression that leads to periodic bursts of activity, which absolutely fascinating stuff. And H3+ is a real indicator. The thing about H3+ is that it is incredibly simple, so you can make it very easily. All you need to do is get the most common molecule in the universe and hit it with some energy. So H2, molecular hydrogen, is pretty common. It's not the most common thing in the universe because there is also atomic hydrogen out there. But as soon as things get to the point where you can start forming bonds, you get H2, just two hydrogen atoms stuck together with an electron. And that allows you to have an incredibly large amount of material. All you have to do is basically strip away one of the electrons, the two electrons that bind. You remove one of them, you create H2+, which is just a simple but incredibly reactive molecule. H2+ will react with anything, including molecular hydrogen, and so it will steal a hydrogen, a proton, effectively, at the core of a hydrogen atom from molecular hydrogen, and that will result in this stuff that we're looking at, H3+. And so it's really easy to make. It's also incredibly reactive. It's not quite as reactive as H2+, but you're able to produce it in very large amounts. And so it's unusual to see it anywhere. You can't see it in the lower atmosphere of Jupiter or Saturn or Uranus because it just gets swallowed up by everything else. It will react with almost anything. And so that's incredibly useful for the interstellar medium, where you have all sorts of long chains of molecule, which initially were quite hard to explain. Those regions are pretty low energy, and yet they're seeing all sorts of tars and wonderfully complex organic chemistry that basically very difficult to produce unless you have something super reactive like H3+. And so, you can just get something that's like a moderately ionizing star involved, and that will make some H3+ for you, and suddenly you've got at very low temperature a whole load of really interesting chemistry going on. So it's incredibly powerful in the early universe. It was incredibly important in developing a richer level of chemistry within the universe. So, fundamentally important for the development of gas clouds, planets, and everything around us, effectively. So we are team H3+. We love H3+, so maybe we are a little biased, but generally speaking, what we study is a very small minutia of the true importance of H3+. The reason why we like H3+ is that it sits almost uniquely at the layer that all of these wonderful processes are happening, just because it's destroyed so quickly. So because it's destroyed by the lower atmosphere so effectively, what that means is it produces this lovely shell around the planet, a beautiful, clear, fairly narrowly confined shell right where the aurora occur. And it also happens to emit light at a wavelength where a lot of other stuff is absorbing. So the reason why we can't see anything of Uranus in the spectra that we're producing is because of all of the global warming at Uranus, and it's basically absorbing all of the sunlight. and basically removing that so it doesn't reflect back to us. So all we see is this beautiful clear shell of the top of the atmosphere and nothing underneath, which is absolutely perfect if you want to measure and understand that top layer. So we're very spoiled because it's a window in the Earth's atmosphere where the light goes through really well, but that light does not go really well through the atmospheres of gas giants at all. There's a huge amount of absorption because there's a lot more methane and other hydrocarbons in the atmospheres of these gas giants than there are at Earth. And then also there's this emission from this wonderful molecule that also happens to fall at exactly the right wavelength. So this confluence of 3 different windows of wavelength let us effectively map out the top of the atmospheres in as much detail as we can manage. So that's why we're interested in it, but it's a very small minutia of the wide array of science that you can do with H3+. And that concludes my rant about H3+ and why it's awesome.
Thank you, Tom. It was a very interesting rant. We've also got a question coming on the Q&A. So will H3+ react with any of the noble gases? So maybe like helium. Do you want to add to that, Tom? I mean,
well, that's a good question and left me reeling a little bit. I do know that it doesn't react with helium because helium is also a very difficult thing to react with. I believe that it does react with other noble gases, though. It's quite hard to make things to react with the other noble gases, but under the right conditions, you can do it. They do have the right conditions to, and I believe that's true, but I would have to go back and have a look.
I guess the conditions aren't. I guess maybe those conditions aren't in the gas giants, which is where we're familiar with. So. Oh, Emma, you're muted even though you're not muted.
Yes, sorry, I muted my headset. It's the fun part of having a mute button on the back, but also the difficulty of remembering if it's on or not. So I was just going to add, yes, it was always intriguing trying to know what reacts with what. Some of the fun parts, especially what will be coming up with my own thesis, is going through the usual with H3+ of understanding how we get H3+, and then from H3+ how H3+ is destroyed in the atmosphere, so understanding that there's actually a lifetime in which H3+ persists at planets.
So a quick Google search has revealed that yes, indeed, H3+'s affinity to combining with noble gases is something that people have looked into in the lab and with ab initio calculations, and they show that neon to xenon have really strong reactions. It's a way of changing and capturing composition, and it's really got strong implications for potential changes in the composition of astrophysical objects. So while helium is somewhat free of it, it's one of those rare molecules that can do damage even to the most inert of other elements.
That's really interesting. I didn't know that.
Neither did I till about a minute ago.
Awesome. I think that's something we could possibly talk a little bit on, which is I think everyone always thinks when they think astronomers, when they think scientists, physicists, that we are these big eggheads that we're like almost like the same people that you see on the panel. I don't know if Eggheads the series is actually still going on, but the people that go in and are just like they'll get asked a question of how far is it going in the in a straight vector direction from Milan going down to possibly all the way down to Brisbane in Australia. Like, exactly, could you tell me that and how many hours it takes for the airplane? Unfortunately, we know a lot about our own area, but when it comes to other areas, we really do rely on a lot of the communication that we have between ourselves and our colleagues, going to conferences, going along to talks, and even coming along to situations like we have today where we're live streaming. we will come along to these even just to discuss with colleagues or people that we don't have the chance to be able to go see, especially after the last year or two where we haven't been able to see people in person. It's been a big thing where conferences have, I wouldn't say struggled, they have done very well actually in changing between the in-person to virtual, but it has been a new frontier, certainly, for a lot of conferences going into this online switch, but it has allowed a lot of potential for us to actually reach out and discuss with our colleagues in a phenomenal number of countries. It's been really astounding being able to just be able to be sat here. In fact, it'll usually be 7 in the morning for myself, but being able to talk with colleagues in Japan, in China. I think we've had a couple of colleagues from, oh goodness, I'm trying to exactly remember, possibly I think Malaysia. I've seen a couple of colleagues as well, being able to kind of present some of their work. So that's been outstanding, knowing that I'm talking with people pretty much on the other side of the planet. It doesn't seem real until I actually take a moment to realize where I am. So it's been absolutely incredible on those sides of things and getting this insight. I also just wanted to quickly, I don't want to hijack, apologies to everyone. I just wanted to give it a bit of insight. So I have changed at the moment to the Uranus cam, and this is the Uranus cam from yesterday. So these are the observations that we took with Kyle. That's the imager that we have with iShell. And it gives a good insight of some of the surprises that we have on the day. So yesterday we had Miranda, Ariel and Umbriel, and that was all on the left-hand side, but you're seeing here repeated on a loop. We actually have, I believe, either a star or a binary star that is just moving past at a diagonal and interacting with our slit there. And again, we got a question yesterday, a very good question that was asking us, when we're taking or proposing these observations, what do we do to make sure that there isn't any interactions with anything else in our observing space? And it's certainly a good question. When I'm making these proposals, the first thing I have to do is find what is known as a calibration star. A calibration star basically means I need to find a naught star. The reason for that is that the light that we receive from the star basically is continuous. It will come along and basically be a very long streak along the spectra. Wrong people entirely today, apologies. Dr. Sarah Casewell was showing us a lovely set of star spectra this morning. It basically looks like one very dark line and one very bright line along the spectra, and we use that to get a good reading of what the intensity is in comparison to the number of photons that we receive from the CCD on our spectrograph or on Cartman. But the interesting part is that, yes, we'll look in the nearest vicinity for these A0 stars, and that's what I did. I found two. We call them one leading and one trailing, just in case of when we wanted to take our calibration star. But by doing this, I'm obviously neglecting to look for any other stars that are in the vicinity, so it can mean that we end up with surprises when we're looking at our observations. In this case, we ended up with this star, which we know is not an A0 star, but we believe, I'm not sure which category actually. I think looking through possibly a J or a K, but again, I'm very hesitant.
We should shout out to John Morell, who I think is listening again today, was providing amazing information, and I believe John said that it was a G star, but I might be remembering that wrong. But again, people with different expertise are able to provide us with all sorts of interesting information that we wouldn't have time to look at ourselves.
Cool. So we are juggling at the moment. Well, not incredibly juggling, because very nicely Nahid is with us but being the lead observer at this point, actually, and keeping an eye where our observations are at the moment. So again, we really do want to shout out Nahid Riang, who is taking a good look at the observations yesterday as well. They are pretty much the foundation on today's observations. They would not be possible if they were keeping a due diligent eye and keeping in touch with the TO, that's the telescope operator on Mauna Kea in Hawaii. Without them, we'd probably end off drifting off from Uranus and off somewhere else and taking HD+ of the space in general. So we love and adore them, and we're so thankful for their time in basically just staring at a screen. So I also wanted to, just before we have about 10-15 minutes before we're hopefully going to Rosie, and we're going to be discussing more about her research with HD+ at Jupiter. I was hoping that I might be able to give a bit of insight. Earlier today, we saw Dr. Sarah Casewell actually give a snapshot of the GUI. That's the basically how it looks when we're observing at Uranus. So I was hoping if I get rid of the camera on my main computer, I might be able to actually give a glimpse of what it is we are seeing, rather than all the borders and pretty pictures that we have at the moment, which I know I spent time on, but obviously at the end of the day, it's great being able to see actually the raw stuff. So I'm just going to stop my video there, and I will see if I can share the screen. I will probably bring up Kyle, as that's more probably what people are looking for, if I be honest. That is no worries. I'm very happy on that side that we have people that are interested in seeing what's going on. So here we are, hopefully. So that is the view that we get from Kyle, that is the imager, as well as the rest of the setup. So as Sarah was kind of talking about earlier, we have to put in specific parameters, such as what the I time is, what the coad. So I time basically means the, is it the integration time, if I recall correctly, Tom?
Mm-hmm. That's right, yeah.
And that's the number of seconds that we will observe at a planet. The coads is the number of times in which we'll do that time.
So I think Sarah did a really good job of explaining how a CCD works and how it reads data out. And so what we're doing effectively is every 2 seconds we're reading data off of the chip. And then rather than showing that or using that in any way, we store that in the memory, and we do that 4 times. And then after 4 readouts, that automatically collates those 4 readouts into a single, effectively 8-second integration that we can then use and show. So that's what those 2 values mean.
Awesome. Thank you for that one, Tom. Appreciate that one. So, sorry, I just got the chat up. There we go. So let's see if we can get my mouse about. There we go. We also do have a couple of other things. We have some easy parts. We'll have the object name, we'll have the comment. So depending on what we're viewing, will vary what object name we'll put in. So if we're looking at Jupiter, we'll say, if we're looking at the calibration star, then we'll usually mention, hey, this is the star we're looking at, not the planet. It helps immensely when it comes to trying to pick out the data, especially with the file names, because they actually save the file name into whatever, I believe, object name, and the comment is saved within the data itself, letting us know very quickly, rather than having to peer through lines and lines and lines and lines of data of exactly what it is you're actually looking at. Additionally, we will always put the observer, so we usually put whichever observer has signed in at the beginning of the morning, or whoever's taking the lead that day. So today that is Tom, so we put Stallard et al.
I should point out that Nahid set this one up and I set the other one up. I put him and he put me, and that's why I'm listed. We're very collegiate.
Exactly. And otherwise, we also have the we have on top of this the autosave file. Autosave is our lifeline. Autosave makes sure that every picture that we're getting in from Carl is being saved onto a data drive known as Stefan. That's where we get all our information, hopefully at the end of the day, we bring in. Sorry, I'm getting slightly distracted with Tom having fun with the color scheme in the background. Very psychedelic.
It is with purpose, but not to any utility.
So the autosave here is letting us know what the file name is going to be saved as, the path directory in which this is going to be put under. So at the moment, these numbers actually mean the program number and when in the semester it's taking place. So at the moment, we're currently in 2021B semester, and our program is 079. So we end up with that as our username. And finally, the path is just the last date, the the last numbers are actually the date, but going from year, month, and day. So that's the end of the path name there. So it seems like a lot, but you start breaking it down, you actually realize it's into like very small parts. As I said, we there have more of the jewel of our observations, where we have several screens actually which are showing Uranus. So we have in probably what's going to be picked up more is D being the obvious difference here. The D panel here, or the 3 panel, which is the bottom right, is actually a close-up view of Uranus. To ensure that we are focusing on Uranus, we will have basically a guiding box on it that will make sure that the signal within that guiding box is strong enough for what we are expecting for Uranus to keep viewing. As soon as the signal for that starts degrading, that's where we start spinning off almost into space. So we basically pray that that is what is as high as possible with the signal, so that we keep viewing at Uranus. Otherwise, we will have the A, C, and G. A, C, and G are currently being picked up in the top left, the top right, and the bottom left panels. Now, we can ourselves actually pick what these are showing. So at the moment, A is showing whatever it is we're looking at the moment. I believe C is to a similar effect, doing the same job. But G is showing us, I think, the negative of where Uranus is in the A frame, as we're now at a B frame, or at the B position.
So what G is, I've been sneakily taking shots of both the A and B frame as we've been observing, and adding them up and then subtracting one from the other to try and get a clearer picture. It's not really working. You can see that the Miranda much more clearly in this frame. What you can also see is that this moon over here is blurring, and that's because it's actually rotated at the time I've been doing this. So it started moving down away from where it was initially. It's not as good as I had hoped it would be. I was hoping to see a ring, and I think you can see something of the ring here, which is why I've been fiddle-faddling with all of the color scales to try and pick something out. You can see a sort of a halo with a brightened ring all the way around, and I think that is the best we've managed with it today for getting an actual ring out of the data.
Awesome. So yeah, otherwise we have to the right, we also have what we know as the T3 remote. That gives us an idea of what the UTC time is. So that is 1 hour behind us in the UK. We also have Hawaii Standard Time, letting us know roughly what the date is in Hawaii as well. So we have a very quick reference to. We also have an idea on the air mass that's going on. So we're about 1-ish, I think, but I don't know if that is at the moment, but I think that was when last detected. We also just have an idea of exactly which beam switch. So again, touching on what we were discussing before about the A and B positioning. So we're currently at beam switch B, so that's position B, and you'll see that flick back and forth to beam switch A, to beam switch B, depending on which position we are at. Just thinking if there's anything else on here. There's so much. You could probably spend the whole
afternoon. Have we talked about the guiding and how the guider works yet?
I don't know in that much detail, actually.
No. So you can see in the A0 box that I've got here, there's a green square, a nice green square inside of Uranus. And this is basically asking itself where the brightest point inside of the box is. The box moves over as we beam switch between A and B. And that's what this zoom in here is. It's done some clever stuff to get rid of some of the light, and you can see that it's looking for the center point. So it's identified the center of that with the square. The square keeps moving, so this purple square has a line drawn to it towards this crosshair, this green crosshair. So every time it takes an image, it goes, where's the brightest point? It says, oh, the brightest point's down here, so I need to move the telescope from here back up to here. And it's allowing us to reposition continuously to make sure we stay solidly on what we are at. And I would just like to point out over on the right, the T3 remote has all of these lovely arrows. And this is something that Emma has never dealt with, but sometimes your guiding doesn't work. It's especially true in the past before we had iShell with its own internal guider. We used to have to guide off axis. That didn't always work. So many, many nights in the past was spent diligently watching Jupiter or Saturn, trying to follow where it is and basically moving it around by hand, doing this job of guiding with the arrows, which is a very fun way of spending your evening. I'm sure you'll agree.
Sorry. Thank you very much, and that's I appreciate it.
Yes, so George has just asked, do the arrows move the telescope? So yes,
they do indeed. If I was to press
do.
it would be a disaster.
And you can change how much they move. So it's like a pink arrow, a yellow arrow.
These numbers here are definable. So that's 1 arc second, which is about a third of the way across of Uranus, and this is 5 arc seconds, which is wider than Uranus. So if I was to press this pink button, I will definitely keep my hand well away from the mouse button. If I was to click that, the telescope would move up by 5 arc seconds, and so Uranus would drop down out of the slit by 5 arc seconds. We'd lose guiding immediately because it wouldn't be able to find
and then it all escalates pretty quickly from there.
Yeah. But when you're not guiding, it's really useful. And if you're moving around something like Jupiter, which is a really big object, that's a really good way of moving from the South Pole to the North Pole quickly and having a really effective way of moving around. So
unless you forget which arrow to press, because it always seems to be backwards in my mind. I'm like, I want to go up, but I need to press down. Or
exactly that.
And then you're like, I think in the past I've had to just ask the telescope operator to just slew back to Jupiter because I just completely lost it. I couldn't see it.
So someone asked what would William and Caroline Herschel think about this, and I think Caroline would figure it out pretty quick, and William would be frustrated by it until Caroline figured it out. That's what I think.
Goodness. I'd like to think that the astronomers that have come before us and the astronomers that even came before them would be pleased that we're still continuing the science, because at the end of the day, because we're doing it, and we do hope that the science that we're doing is going to be helpful for the scientists that are coming behind us. But until we get a time machine to go find out who they are, we just have to hope that they are the ones that will pick up the questions that we leave behind.
I think William would have been distracted by the implications of the size of the mirror we have to be using to do this, and what that meant for the engineering of that mirror. Yeah.
Sadly. Awesome. Well, I'm just going to stop sharing. I appreciate this is probably an amazing view for some people that are currently on stream at the moment. But we are now at our, I think, second or third talk, apologies, for the day. I'm going to see if I can get up the correct screens here. So bear with me. So there we go. So Rosie, hopefully it's just myself and you now. So thank you, Rosie, again for coming along today.
That's okay.
So we are hopefully going to have yourself discuss about your research that you did whilst you were a Tom student here at the University of Leicester. Now, instead of looking at Uranus, you were looking specifically at Jupiter, looking for the auroras. And I'm just going to leave a little bit of an intro to yourself. So I think Robert was mentioning earlier, obviously, that you are an associate lecturer at the University of Aberystwyth University. Apologies. But we had some other really cool things I also kind of wanted to mention. Let's see if I have my little document here. So Rosie Johnson is an associate lecturer whose history in research has been with the team HC+, which has been looking at space weather interactions with the giant planet Aurora, leading to our understanding of the interaction between the solar wind and Jupiter's aurora. Outside of physics, Rosie was the education coordinator for the Royal Society of Chemistry, providing regional support to teachers of chemistry across Wales. So I'm not going to lie, that blows my mind. During her PhD, she was awarded with 76 hours of observing time with IRTF. That's the same telescope we're using today. And so we hope that she'll feel right at home for today's observations. This leads to today's talk with Rosie, where we'll be looking into how infrared observations are taken at Jupiter and what processes we use with infrared observations to fully understand the upper atmosphere of gas giant planets. Right. So when you are ready to, Rosie, feel free to share your screen if you have your slides ready.
Yeah. I just was accidentally nearly changing the sharing settings, of course. Let's get rid of that. Okay. There we go. Okay, so if at any point I freeze, the slides freeze, just let me know. Otherwise, I'll be waffling on to myself.
No worries, we'll let you know.
Okay, so let me just hide myself. So thank you, Emma, for that introduction and for inviting me here today. So as Emma said, I'm going to be speaking about my research on Jupiter's northern lights. Just sharing here on the title slide, one of the pictures I took while I was observing at IRTF. I think maybe this was my first trip to Hawaii with Tom and Henrik. And I really like making these long exposure photos. So you get your torch and you have to write backwards. So that was another skill that I learned during my PhD, was how to write backwards with a torch. But yeah, so I really enjoy taking these light painting pictures with the lovely telescope IRTF. So I think this is in the morning, the sun is rising, we've just finished our observations, and I'm just messing around outside while Tom and Henrik finish off the observations and we get ready to go back down the mountain to get some sleep. So as Emma said in my introduction, she mentioned my career path so far. So I'm an associate lecturer currently at Aberystwyth University, and that's actually where my journey into planetary science started. So I did a combined master's course at Aberystwyth, and during that I got to go to Svalbard, to the University Centre in Svalbard, for an Erasmus semester, and I got to study the Earth's northern lights. So here I am jumping in front of the IceCat Svalbard radar, and we use that to take a look at Earth's upper atmosphere, so the charged layer known as the ionosphere, where the northern lights are created. So after I did that, I was like, oh, what could be better than studying the northern lights in the Arctic? I decided that studying Jupiter's northern lights in Hawaii was a more exciting option. So I moved over to the University of Leicester, where, as Emma said, I became Tom's PhD student, started working on Jupiter. After I finished my PhD, I did have a little time working as an outdoor guide. So I worked as a whitewater raft guide, and then I had a bit of a dream job working as a Northern Lights tour guide, although it was very, very, very remote location. So even though it was so much fun talking about the Northern Lights and seeing them all the time, it was very cold and very remote. Then I moved back to Aberystwyth, and as Emma said, I became an education coordinator for the Royal Society of Chemistry, so helping out chemistry teachers. But unfortunately, because of lockdown, I didn't really get to see anyone in person. So the little picture that I used to describe this is me on my stand-up paddleboard, because I do a lot of that in Aberystwyth. And then, yeah, now I've gone full circle. I'm back at Aberystwyth University. I'm doing a bit of teaching on undergraduate courses, and then I'm trying to get in some of my own research. I have this lovely new data set that I took during my PhD. So this is some data of Jupiter's northern lights, so looking to analyze that. So before we get on to Jupiter, I want to talk give a little bit of context about how the Earth's aurora is created. I've had a few of the other speakers have also spoken about the Earth's aurora, and it's just to help us understand what's going on at Jupiter. How are they different? How are they similar? So at the Earth's northern lights, so the northern lights and the southern lights, they're created through this interaction with the Earth's magnetic field and the solar wind. So the solar wind is continuously coming from the sun. So it's like a stream of charged particles all mixed up with the sun's magnetic field, and that gets dragged out into space, where it bumps into the Earth's magnetic field. So the Earth's magnetic field forms this bubble. It forms a shield that expands into the surrounding space around the Earth, and that protects us from the solar wind, which is good news for life on Earth. Under certain conditions, the solar wind with the sun's magnetic field and those charged particles, they can interact with the Earth's magnetic field. So the magnetic field lines here at the day side would break apart and they get swept over the poles, where they reconnect on the night side, ping back towards the Earth like elastic bands, and then they fire those charged particles into the Earth's upper atmosphere, where they bump into other molecules, the neutral atmosphere of the Earth, so like oxygen and nitrogen, and they excite those molecules. Now, those molecules, they don't want to be excited. Like, imagine being in an excited state all the time, like a toddler or a dog. You eventually get tired. So those molecules, they don't want to stay excited. So to relax down into a ground state, they release the excited electrons, they come down and they release a photon, so they release light. So oxygen making green and nitrogen making like blues and purples and pinks. So that's how the Earth's aurora is created. Sometimes the solar wind is a bit more exciting. Sometimes there's a solar eruption. So we call this space weather. There's variability. So there's always this solar wind, like a constant breeze, but just like weather on Earth, sometimes there are storms. So here on the left-hand side, we have some spacecraft footage of these coronal mass ejections. So these are the solar storms where material and magnetic field is exploding out of the sun. And in that last explosion, you can see all these little like dots in the picture. And this is where that solar coronal mass ejection has hit that spacecraft. And the electrons in the coronal mass ejection have sort of interfered with the circuitry of the spacecraft. And so that one would have gone on to hit the Earth. And then when the solar storms hit the Earth, they can cause a lot more auroral activity. And this can produce really nice aurora. But the sun isn't always really active. Like, it goes through like periods of quiet and then moving on to more active. So in 2025, it's going to be more active. So it sort of has this like 11-year cycle. And so we were moving out of this minimum quiet period into more active times. But even when the sun is quiet, we still get aurora at the Earth. Like this is a picture of the sun. So, and these black parts, these holes, they're called coronal holes, where the corona is the atmosphere of the sun. And the solar wind is able to like stream really fast out of these holes, and then that can hit the Earth and make aurora. So you can still see aurora if the sun is being a bit more quiet and a bit more active. I think I've switched over into the Aurora tour guide mode at the moment. The Earth's aurora, it forms like an oval around the pole. So you can see this is like a spacecraft footage of the Earth's southern lights. You can see Antarctica there, and then the aurora makes this oval. So the person who kind of like thought, was thinking about how this works, why is it making an oval, how does the magnetic field interact with the solar wind? They sort of had a brainwave, they were called Dungy, and they had like a brainwave, like when they were having a cup of coffee. So they were thinking, when you stir the coffee, like say you put your spoon down the middle of the coffee cup, then the liquid on the outside will swirl back up and around. I forgot to change that arrow. Pretend that arrow is pointing the other way. I meant to change it. So imagine you pull your spoon down here, and then the liquid will flow back up, and then this is how it makes the Earth's aurora, makes it an oval. So the day side, the magnetic field lines are reconnecting, then the solar wind pulls them over the magnetic pole. They don't really have many particles in the solar wind there, so you don't really get much aurora over the pole. Then on the night side, it reconnects, the magnetic fields ping back towards the Earth like elastic bands, and then here they've picked up particles from the Earth's magnetic field in its magnetosphere, as it's known, and they ping back, and then they start to excite the Earth's upper atmosphere into making aurora, and then those magnetic field lines drag back round to the day side, and they start again, and that's what makes it oval. Sorry, I forgot to switch that arrow. So on that side, they're being dragged right around to the day side. Okay, so that's the Earth. Moving on to Jupiter, which has the most powerful aurora in the solar system. So it's Jupiter's, everything about Jupiter is a pretty big deal. It's a big planet. Here we've got a familiar picture of Jupiter. You can see the visible light image. We've got the lovely bands. You can see the great red spot. And then overlaid on the top of this image is Jupiter's northern aurora. So Jupiter's northern lights, but taken in the ultraviolet with the Hubble Space Telescope. Oops. And then on the right here, we have the infrared aurora, and this was taken with the spacecraft Juno. So this is the H3 plus aurora, and it's in the southern hemisphere. So this is Jupiter's southern lights. So, as I said, Jupiter's aurora is really big. Here is the Earth to scale-ish. So you can fit the Earth about 5 times across Jupiter's aurora. And Jupiter aurora is a little bit different to the Earth's aurora. So the Earth mainly has this oval around the pole, and you can see that, like, obviously sometimes when it's active it's more fatter in different places. There's like arcs and you get waves and stuff. But at Jupiter, as well as having that sort of oval, you also have this like dot and tail. So this is a footprint aurora from one of Jupiter's moons called Io. And then poleward of this main auroral emission, which makes a kind of circle, you have this polar aurora that can be like super active, really variable, and really bright. And there's this dark region here, and that sort of always pretty much stays dark. So that's what it looks like in the ultraviolet, and then in the infrared, which is the H3 plus emission, like the emission that we've been observing today. We have a similar picture. You can kind of see like an oval thing. Can't maybe see any footprint aurora from any of the moons in this image, but we can see the polar aurora too, and we can see that there's like that dark patch there. And it's like a little bit more fuzzy compared to like the ultraviolet because of the timescales of the lifetime of the H3 plus molecule. So the H2 emission for the ultraviolet, that's like more instant. So you kind of get like this crisper image. But the really cool thing about the infrared H3 plus aurora is that we can take some measurements from the spectra, and we can work out some properties like temperature, velocity, density, as well as the intensity. So how is Jupiter's northern lights created? So Jupiter's magnetic field is super massive. It's super strong. It's about 10 times that of the Earth. You can see the Earth in this little box will fit into Jupiter itself. If you could see magnetic field lines in the sky, Jupiter's magnetosphere, so its local magnetic environment, everything inside this purple bit here, that would be bigger than the moon. So it's a really massive object in our solar system. And Jupiter rotates about like once every 10 hours. And so the magnetic field lines, they've got their feet in Jupiter's atmosphere. So they also get dragged along as well. So this whole thing is trying to go once every 10 hours, this massive, massive magnetosphere. And it's also full up of plasma from Io. So this is Io, the bottom right down here. This is one of Jupiter's Galilean moons, and it's a really volcanic moon. You can see all over the colors on its surface due to the volcanic activity, and the sulfur is making it yellow. And when New Horizons flew past, it took this really cool video of an eruption from one of Io's volcanoes. So Io is continuously erupting, and all of this material, about 1 ton per second, goes out into Jupiter's magnetic field, where it becomes ionized. So now they are charged particles, and now they're interacting with Jupiter's magnetic field. So loads of plasma, magnetic field lines, all whizzing around Jupiter once every 10 hours. And so if you think about, say you had like a group of people holding hands in a line, and the center person, they were pretending to be Jupiter. And you're all spinning around and around, and the people on the edge of the line, they've got to run the fastest to keep up. But if the person who's pretending to be Jupiter feels a bit mean, they might want to spin faster. And eventually it's going to get to a point where the people on the edge of the line, they can't run fast enough. They can't keep up. So eventually they can't hold hands anymore. The line breaks apart. And this is kind of what happens in Jupiter's magnetosphere. So as we move away from the planet, the plasma and the magnetic field lines, they just can't keep up anymore. And once you have charged particles moving at different speeds relative to each other, this sets up an electrical current. And this electrical current drives Jupiter's aurora. So it's kind of from then, it's kind of sounding a little bit like the situation at the Earth now. So once we've got this electrical current set up, charged particles are getting sent down Jupiter's magnetic field lines into Jupiter's upper atmosphere, where they impact the neutral molecules there. They excite them, and they excite them into emitting light. So, which we can observe in the UV, or in this case, like we're doing today, we can observe in the infrared, so we can see the H3+. Okay, so how do we observe Jupiter's northern lights? So one way we can observe them is using the Mauna Kea observatory. So this is a picture of Mauna Kea taken by some of the astronauts on the International Space Station. So you've got the Mauna Kea volcano here, and it's a massive place. You can see all the little like cinder cones from when the volcano came to like the end of its life. And at the top is, you can see these hopefully you can, depending on your screen resolution. They're the little like white dots of all the telescopes at the top of Mauna Kea. And then down here, you can kind of see the road there, zigzag road down to Halepohaku, which is like, so the summit is like 4,200 meters above sea level. And then Halepohaku is like 3,000 meters above sea level. And that's where you stay as a visiting astronomer. You sleep there, you eat there, and then each night drive up to the top of the volcano to do the rest of the observations. And we might have mentioned over the weekend that it's a really fantastic place because it's so high up in the atmosphere. There's not as much atmosphere above you, so you get really good seeing, which means you get really clear observations. Typically you're above most of the clouds, fingers crossed. Looks like we've been above the clouds for these observations. Because it's in the middle of the sea is obviously quite flat compared to land, so you get very stable air. You know, in continental regions you get a lot of turbulence in the air. So there's lots of reasons why Mauna Kea is a really great place for observing Jupiter and of course Uranus. During my PhD, I also used observations from the Very Large Telescope in Chile, another fantastic place. It's just high up in the deserts and the mountains. And we use some instruments at both of these places that are quite similar. So today, with the observations of Uranus, we're using iShell. So here's a picture of iShell before it was put on the telescope. But in my PhD, I also use seashell. Here's a picture of seashell on the bottom of the telescope, but seashell has since been retired. And then over at the Very Large Telescope in Chile, I used an instrument called CRIRES. And these are all called long slit spectrometers. So they split up the wavelengths of light. I think everyone's sort of familiar, well, depending on how long you've been watching over this weekend, maybe you've seen some of the spectra from these. So this is what some of the data looks like. So here's Jupiter, it's on its side. So this is the North Pole of Jupiter. This is a slit picture, so there's the slit of the instrument. So that's the orientation for all of this data. So originally with seashell, this is the data that you would get. So mainly 2 emission lines, so one really bright one there, one sort of less bright. And then with cryo-res at the Very Large Telescope, there's 4 spectral arrays, so you get quite a few shiny lines, as I like to call them. And then with iShell, there's many orders. So at Jupiter, since the Aurora is so powerful, it really lights up that spectra. And I think Henrik was saying, like on Friday, this is like 25. That data was taken in 25 seconds, but that would take you more like 90 minutes to get that at Uranus. So it is different. And so today at Uranus, we've got the slit in like a fixed position on the planet. But at Jupiter, we step the slit from the top of the planet. So I've got an animation here. So Jupiter on the right, we step the slit down through the auroral regions to take a scan of the whole Aurora region. So at Uranus, we usually have it in a fixed position. At Jupiter, we like to scan the auroral region and also the southern auroral region too. So what does the spectra tell us at Jupiter? So the spectra tells us a few things. So we can get the intensity. We can get the intensity from fitting a spatial, fitting a curve or a Gaussian to every position along the spectral emission line to find out a number of properties. So for this slit position, which is a cut through the Aurora, you can see the emission line there. There's the one bright side of the Aurora and another bright on the other side of the Aurora. So you can see again in the line graph here, that's the emission. And then because we've scanned through the whole Aurora, we can make a map. So this is a map of the intensity of the H3+. So the rotational pole is in the center at the top there, and we're looking down on the Aurora. And then this is just half. This is the day side of the planet because we can only observe the part that's facing towards the Earth. So as well as intensity, we can get velocity. So for the same section slit position across the Aurora, same emission line, you can see by eye that it's not completely straight. If it was completely straight, then it would follow this dashed black line, but we work out the exact position of this line and we can tell that it's not completely straight. So we use the Doppler effect. So that's the one, you know, when like an ambulance goes down the road and you can hear the pitch change. We use that effect to calculate the velocity of the H3+ that's making the Aurora. And then I've also mapped this. So we've got the intensity and we've got the velocity map here. And so what we discovered was a region of Jupiter's Aurora that is coupled to the solar wind. So this side of Jupiter is the limb rotating towards us. So it's blue shifted, it's coming towards us, then moving through the center of the planet to the other side as it's moving away from us. So it's red shifted. And then there's a lot of activity going on, a lot of velocities, different flows to create the Aurora. And this one part is thought to be connected to the solar wind, which Tom had discovered previously. But this data set with a very large telescope had amazing spatial resolution. So we were just able to make this really great map and found that it was like in a new position. but we still don't know exactly how it's coupled to the solar wind. It's not exactly the same as the Earth. So it could be through Kelvin-Helmholtz instabilities, which sort of make these sort of wavy clouds, like you can see them on the Earth. So we think the magnetic field might be interacting in a sort of wavy way like that. Or it could be like at the Earth where we have these like, we call them convection cells, but it wouldn't be two convection cells like at the Earth. It would just be one, and it would be squashed because Jupiter's magnetic field is going round so fast. It's squashing it. So there's a few open questions there, which I'm still working on. I also took a look into the temperature. Again, this is the same position across the planet. So these are two emission lines, two different emission lines. So it's still H2 plus, but they're just at two different, slightly different wavelengths. And you can see that they have different brightnesses. So by taking the ratio of these brightnesses, you can calculate the temperature. And then, of course, I've mapped that onto a projection of Jupiter. What has caused this temperature pattern? Could it be from the velocities from these strong flows? So this is the velocities in the planetary reference frame. So you can see in the Aurora regions, there are really strong flows. So this is the winds that you would be seeing if you were able to stand on Jupiter. And where the strong flows are happening, there'll be a lot of friction between the H2 plus and the neutral atmosphere. So this should cause heating. So when we compare this, it should be hot where that dark red is, which I guess it kind of is, but then it should also be a bit more hot over here, and those patterns don't really match. So it can't just be from that friction. H2 plus is known as a thermostat, as it's really, really good at radiating heat into space. So it should be that where H2 plus is, where it's bright, it should also be hot. So if we compare the total emission and the temperature, you can see that, again, they don't exactly match. There's got to be more going on. And when we look at the density, this tells us where the particle precipitation is happening, so where those electrons are coming in on the magnetic field lines. So they can also cause heating through those when it's creating the aurora. So it should be that where it's dense, it's also hot, but again, looking over at the average temperature, they don't really match. So we decided to have a look into this. And we found that there were some temperature changes. So one part, so you can see this is the average temperature at the start of the night and average temperature at the end of the night. And then I've like calculated an average difference. So this one part moves from hotter to colder, and a middle part moves from colder to hotter. And this could be because as the planet rotates, these are moving through different local times. So maybe this starts off with H2 plus is being made at a high latitude where it's hot. And then for some reason, as it moves in this region, now H2 plus is being made at a lower altitude where it's cooler. Or it could be that something happened at the sun. There might have been a coronal mass ejection, and this has squashed the Jupiter's magnetosphere. And models have shown that this can cause heating in the lower atmosphere, and that heating maybe is heating the upper atmosphere, heating H2 plus too. So something dynamic, something is changing in this time period. But we need to take more observations so that we can see if this temperature change is repeated. So yes, definitely more observations needed to solve the velocity questions and also the temperature questions. So that was a summary of the work that I've done on Jupiter. Obviously, as always, it's still ongoing. So thank you so much for listening to my presentation. I'd welcome any questions that you have.
That was excellent, Rosie. Thank you so much for your time as well as your presentation slides.
And that's an absolutely brilliant picture showing exactly what we're using today So you want to put that back up? I think that's amazing.
Sorry, share the screen again.
So yeah, we often talk about how IRTF is a small telescope. It's only a 3-meter telescope, right? And that is much smaller than some of the largest telescopes that now sit on Mauna Kea. But you can see just how enormous that mirror is. And that's how we're able to gather light so effectively from a distant object like Uranus. It's an absolutely enormous mirror. And what you can also see in this picture, which is also great, this has been taken from when the mirror is down on its side, and so we're standing, the cameraman, you can see me in the corner at the bottom, look at me. The person taking the picture was taking it from about underneath this sort of, you can see a sort of a grey cross with a small disc in the middle to the right of where Rosie is. That's the secondary mirror. So the light comes off of this main mirror, bounces up towards the secondary, off the secondary and down through that hole in the middle. And that's how the light goes into the instrument. The instrument sits underneath there. That's how we get the light. Really good. Thank you.
Yeah, and then the instrument was, where's it gone? Yeah, so that's the bottom of the telescope there. So the instruments sit on the bottom. I think there's 2 there. There's seashell and specs.
Right, so the way IRTF works is a bit antiquated compared to some telescopes. Most big telescopes now have instruments that are so big you can't stick them on the end of the telescope. So you basically have a mirror on the end of the telescope that bounces the light off into 4 directions, and the light goes into an instrument off of the main axis, whereas IRTF still straps them to the bottom. So you can see a whole slew of different wires and everything coming out. There's a red plate with a circle in it. That's an empty mount. So you would mount your instrument somewhere there, and then when you change instruments, basically one of the guys at the telescope has to get a wrench and undo all the bolts and slide it off. Obviously it won't be tilted over like this. It will be pointing straight up, and you can slide one instrument out and one in, tighten the bolts back up, and then it will move with the camera. So right now we are not too inclined, but it's slightly inclined towards the west, and so is iShell. It's pointing in the same direction as the telescope.
Thank you both. That's a lot of stuff that I didn't quite know. I've been very enlightened on. Thank you.
I think it's some things that you when you get to go to the telescope, I think that's it's amazing that we can do the remote observing, but I think it's important to try to go maybe at least once, because then you really do get like a feel for all the procedures that go on, and then you just end up learning like loads of stuff from the telescope operators, and sometimes you meet the other support astronomers and things. There's a lot going on that maybe you don't see from home. And there's also like a lot going on culturally, like understanding the importance of Mauna Kea to the people who live there. There's a lot more to it that sometimes you don't get the sense of maybe when you're remote observing.
So John Morell has asked about that mirror. If we go back to the picture, sorry,
No,
Rosie, we keep making you appear. The last picture, yeah. So when we were looking at James Webb the other day, it was gold because it was a gold reflective surface.
Yeah,
it's got an orange hue, but that orange hue is actually this orange frame that makes the telescope. It's this giant orange frame, and all of that light bounces off of the reflective surfaces. Basically, the whole of the inside of the dome and the outside of the dome of the IRTF is a silvery color. The dish itself is made out of aluminium, and that's true for most of the Earth-based telescopes, is that they are polished aluminium.
I find it quite funny actually when we got to see the telescope this close up, how dirty the mirror was. Apparently that doesn't matter. Because,
that's the joy of an infrared rather than visible telescope. So that would not be true of something like
kind of maybe see it. Like there's like a little bit there, a little bit. But yeah,
generally speaking, you can get away with a little bit of. I mean, it's also quite dangerous to try and clean it as well.
yes, yeah, you don't want to. They did describe, I can't remember exactly how they clean it, but they do have a way of cleaning it. I don't want to be like, I'm not saying that it's not well maintained. It's just yeah, obviously the dirtiness of the mirror was within acceptable levels. But I just thought that's quite interesting, and that just also always blows my mind when learning about other telescopes. You know, like radio stuff, you can reflect that off like chicken wire. Like it's just different wavelengths of light and stuff. Needs different things.
Of course. So I was going to say thank you very much, Rosie, for your talk today. I have put in the chat. We have kind of any kind of Q&A we have next for, I'd say for the next 10, 15 minutes, I mean, however long that you're happy to stay with us, Rosie.
Yeah, I'm welcome to stay, yeah.
Fair. So I just want to have a quick look. So is it okay if I share your slides?
Yeah, please do.
Awesome, thank you. So I'm just going to pin up at the moment because I thought it would be quite nice to just have in the background. So I have a comparison with, this is James O'Donoghue's work with his lovely animations. I have all of the planets in our solar system, including Pluto, as kind of a nice comparison as we're here talking about Jupiter as well as Uranus, looking at infrared observations. I think if any questions that we have specifically come in for Rosie, I know we had obviously the discussion about the IRTF mirror. I know we had we have one, but I think that's more to do with Uranus, but it does mention about Jupiter, about there being electrical storms, but I'm not sure I could answer that one, but perhaps discuss that a little bit more in HC Plus Q&A, which is coming up very shortly. So I guess my main question for yourself, Rosie, is I guess the topic that we've been kind of discussing about over the weekend. And perhaps this is throwing you in the deep end of Ice Giants discussion. But if you had the money to, but you could only send possibly one mission or a smaller mission to both planets, to Uranus or Neptune, which would you decide to go for?
Wait, who would I choose? Uranus or
which favorite planet do you want to pick out of Uranus or Neptune? Again, there's no pressure, you can say both.
Yeah, I think I would choose Uranus, though. Don't know if I'm going to get told off, but at least we have H3 Plus there right now, and it's been a bit tricky finding the H3 Plus at Neptune. So I would like to put like something like iShell or Cryres on a spaceship and send it there, but awesome. This is quite difficult to achieve. There's not currently any spacecraft that have the same capabilities as ground-based telescopes do. So that's why it's so important for us to keep doing what we're doing, especially for the velocities. Like you can get temperatures and stuff from spacecraft who have some spectrometers and things, but we need this like super high spectral resolution to get the velocities basically, and it's quite hard to put that on a spacecraft. From what I understand, it's just like it's like a big thing and it's sensitive, and we don't want to just like shake it. I don't know what the technical, like what we would have to overcome to be able to do that, but that's what I would like to put IRTF on a spaceship and send it to Uranus.
I think I agree with you there. I would love to have that. But thank you very much. I was interested to see what would happen there. Yeah, thank you for your answer. I'm just trying to think. So if we have any more questions, so we have another question from the audience. We have, is HC Plus difficult to find?
Well, it is on Neptune.
Yes. That's I don't know how much you know on the side with Neptune at the moment. Obviously our colleague Luke Moore is one of the he's done his own paper discussing about HC Plus at Neptune, and obviously our colleague Henrik Millen, who's with us on Friday, has been a leading head in trying to find HC Plus at Neptune. But if you want, I can leave the trying to think of the word. It's gone from me entirely, but I can leave this to you, Rosie, if you want to have a bit of discussion on your thoughts on H3 plus at Neptune or even other planets.
Yeah, well, so we've found H3 plus at Jupiter, Saturn, and Uranus, but not at Neptune. And even though people have tried, our colleagues have tried, like, to find it, they've had some really nice observations. And even though they've not been able to find it, it's they've been able to put sort of like an upper limit on like the amount of H3 plus that would be there, because I guess, you know, like if there was loads, then hopefully we would have been able to detect it. So I guess people are just going to keep trying to find it at Neptune, whether it's you know, like something to do with the atmospheric composition that makes it difficult, whether there's something that might change over time. Who knows? Because I guess, I don't know, like Uranus it's been known to be decreasing in temperature over time, and so the H3 plus is getting less and less bright. Maybe something similar is happening at Neptune. Yeah, but it is really interesting, and is something really interesting for us. Like, we've got the 4 giant planets in our solar system, and then we've got a whole host of exoplanets, and theoretically we can detect H3 plus at exoplanets, so planets around other stars, but no one has detected H3 plus at an exoplanet yet. We've had a couple of attempts, but not like, you know, we can still try. We haven't given up yet, but basically it's really interesting, you know, that we found it at 3 planets in our solar system, but not at Neptune. So, you know, is it going to be the case that we can find it at exoplanets? And, you know, will that be easy? And that will be interesting because, as you know, like, as technology is improving, we're like being able to resolve spatially exoplanets. That's really cool. But, you know, it can be more than 1 pixel, but obviously I don't think it'll be that we can make beautiful maps just yet, like I can make at Jupiter. But even if we can see that there's H3 plus there, you know, if it's bright and if that brightness changes, if it's changing over time, then maybe there's Aurora at that exoplanet that's changing as that star. Maybe that has stellar wind, like the sun's like solar wind. So yeah, so sometimes H3 plus is easy to find. Like at Jupiter, it's very easy to find, very bright. At Uranus, yeah, it's okay. You can find it. You might have to look more than 30 seconds. But Neptune and exoplanets have eluded us so far.
I think that's just like an added point on the fact that, Jupiter, one of the things that astounded me when we were doing Jupiter observations and Saturn observations was that it would take a minute or 2 minutes, especially at Jupiter, and oh, there we are, we have lines already. At Uranus, we have to wait about 30 minutes to start seeing the very beginnings of something, and up to about 90 minutes before we get a confirmation of an exact line at Uranus. So it really shows you it can vary depending on how long you're looking for H3 plus and how difficult it can be to find it.
Yeah, for sure.
Awesome. So let me just answer that one. So there we go. So this is another good question that kind of leads into the same thing. Apologies, we're going to be touching again with Neptune. Is the solar wind too weak at Neptune to form H3 plus?
Well, so H3 plus can be either produced by so there's 2 ways. There's like from extreme ultraviolet radiation, so just the ultraviolet radiation from the sun can excite the molecular hydrogen, and then that can react then to make H3 plus. Or it can be excited from energetic particles like electrons coming down and then hitting the molecular hydrogen, and then it goes on to then react again to make some H3 plus. So there's 2 avenues to making H3 plus. So it can either start off with extreme ultraviolet radiation, or it can start off with electron impact. So Neptune is like, yeah, that, you know, could be like a Uranus. There is like enough. Obviously there would be less EUV, extreme ultraviolet radiation at Neptune. But my understanding is that it would be enough to make some He+. And then in terms of like the solar wind being too weak, so the solar wind does, like, obviously it's, you know, it's starting off at the sun and then it's spreading out into the heliosphere. So maybe by the time we're getting to Neptune, you know, you could have a coronal mass ejection that might be more dispersed. I mean, well, no, it will definitely be more dispersed by the time it reaches Neptune. But yeah, exactly like how the solar wind and Neptune interact is just a crazy unknown. And just another thing to add to our list that we've been compiling over the weekend, why we need more missions to the icy giants, because it's really unknown. Like, we don't have too many data points what the solar wind does there. You know, you can sort of list off all the space missions that have gone that far, you know, like Voyager 1 and 2, New Horizons.
That's okay. Yeah, there is.
Ulysses kind of went up, but I don't think it went further. But anyway, yeah. So this is an interesting question about the solar wind. We don't really know how it exactly will be over by Neptune.
Yeah, I was just going to add to that, if you don't mind, Rosie, with some of Henrik's work that he's done, which has been looking obviously with Uranus intently over the last couple of years, but has also been with Neptune. I think the last big paper that Henrik did that was mainly focused on the quest for H3 plus at Neptune was approximating, because of the observations we weren't able to find anything, finding an upper limit that we expected for the intensity of H3 plus, and perhaps predicting why we can't see it. I know discussions with Tom has been perhaps when we are observing at Neptune, we're just not able to see past the day glow to see the aurora itself. So any variations that are happening are just below where we're seeing the day glow. So it doesn't matter what it's doing underneath, we just can't see it past it. So again, another plug as to why we really need a mission. It would be great if we could actually see the night side, or towards the night side of Neptune, because we won't have so much interaction with the day side glow, and be able to actually observe the aurora, perhaps even on the night side, and see those interactions. So again, another big push as to why we really need orbiters at these ice giant planets. But thank you, Rosie. Thank you very much for answering that question. I appreciate. We are out of Jupiter and Saturn, more towards the ice giants. We appreciate you tackling these.
I'm a big fan of all of the planets in the solar system, so
they're all your favorites, hopefully. So I'm trying to think. I think we did touch upon this. We have another question from Rodrigo Albornoz. Apologies if I have that wrong. I think this is very similar. We touched on this with exoplanets, which is it possible to see atmospheres on, I think, trans-Neptune, sub-Neptune, and I'm going to make sure I get this up, because TNOS is trans-Neptunian object. There we go. Sorry, sometimes the acronyms are a bit fun to try.
So is it possible to see atmospheres?
Yeah. So I guess similar to what we were talking about with the auroras, there is an element.
Yeah. So like if you were able to detect H2 plus at an exoplanet, then you would be like, oh yeah, we can tell that its atmosphere has H2 plus in it. So you can detect. And they've obviously not been able to detect H2 plus, but they've been able to detect other elements and stuff. So they can detect atmospheres at exoplanets. And they would do it in a similar way to how we do with spectra. So they would say, aha, we have got the planet in our slit and we found these spectra signatures. So then you'd be able to characterize the atmosphere and you would know that what it has in it. But obviously you may not be able, you wouldn't be able to like see cloud structures. But maybe you'd be able to, if you monitor it over time, you might be able to see different intensities and different amounts of the different molecules that you've been detecting. So that's interesting. So you can definitely characterize the atmospheres that way.
Awesome. Thank you. Thank you so much on that one, Rosie. So I was just saying we are about 7 minutes, so we still have a little bit of time before we're going to be checking in at the telescope. We have had a couple of interesting developments. We'll probably have Tom come back in again to keep us updated on what's happening at the telescope at the moment. In the meantime, there's a very good question from John Moreau on YouTube, who asks, is there Hg plus in the Earth's outer atmosphere? And if I'm being honest, I don't know if I can answer that one. That may be one we need to ask with Tom. My first...
there isn't.
I wouldn't think so, no. But
no, because it's like at Jupiter, it's just like massive abundance of like hydrogen. It's like the main thing. So like when we're looking for Hg plus exoplanets, and when we're expecting it, like at Neptune, like these planets have like sort of like abundances of like hydrogen that we are sort of looking for. We do have like quite a lot of like hydrogen in our magnetosphere, but not in like our upper atmosphere, and yeah, not Hg plus, sorry.
Awesome. Thank you for that one. I said I felt that it was a no, but I am still very new to knowing everything with Hg plus. I think one of the things for me that stands out is if there is the interaction with Hg plus in the upper atmosphere, there's a lot more work we would need to do to scrub out that Hg plus from Earth's atmosphere, because that would also come in at the same wavelengths that we're looking at.
Yeah,
so
you're
be a lot more
completely
work.
right. Yeah, so you should trust your instincts.
So I trust, but I always like a bit of backup on these things. I fully appreciate I'm still very new when it comes to fully understanding everything. And I hope that's a message for everyone here, that you may feel that you're still very new, and even the professionals, as today I am a professional astronomer, will still feel that there's a lot more I need to know. There's a lot more that there is to know in the universe. And I mean, at the end of the day, it doesn't matter which science we're looking at, but there's always more to know. There's always more to do. There's always more to know. So please never feel that you don't know anything. A lot of us always feel like we don't know anything. You're in the same boat as us all. No worries. So I think we have Dr. Tom Stallard joining us again. So are we connected?
I'm here.
Excellent. Yes. So I haven't mentioned it in too much detail, but we were having slight technical issues I saw on the screen, perhaps with viewing at Uranus. Would you be able to give us a bit of a fill in? I will see if I can transfer us over for a bit of a view. Back to.
Well,
So
we're all back, but it's obvious that something happened, because the spectra is not nearly as clear as it was a few minutes ago. I don't actually know what happened. My guess is that something like a cosmic ray fell near the slit, and so the guide camera decided it would track on that. And once you move too far away from the planet, it's just trying to track on noise. And so by the time I noticed, there was no Uranus at all. We couldn't see Uranus anywhere. So I stopped the observation, and we asked the telescope operator to move us back to Uranus. That took a little bit of time, and then since basically there is a shutter on the telescope that can be put into a low position or a high position on the sky, and so nearly always that's in a low position to allow you to see the sky all the way across. But as you start to sink to a lower and lower height on the sky, you tend to want to move that up. We're not nearly at the point of that being a problem yet, but in maybe an hour and a half, 2 hours, we would have had to have done that to get the end of the night. So since we were low enough in the sky to allow us to do that, we also did that, which also took a little bit of time to correct for. So we're back on. Hopefully now we will be able to stay on until the end of the night. One of the vagaries of doing these observations, and why you always have to try and keep an eye on things, because all of this is just a wing and a prayer. Ultimately, we're just hoping that everything works, and things will inevitably break, because if it wasn't hard, everyone would do it. So we're back and we're taking data again, and hopefully we didn't lose too long in the grand scheme of things.
I think I'm incredibly appreciative of yourself and Nahid, who are working behind the scenes whilst I do a lot of the front-facing talk today. Again, I've said this so many times, but without everybody today working on the camera, that includes the TOs, that includes everybody that makes the telescope available and keeps it running for us, there'd be no way that we would get any of our data. So we are so incredibly thankful for their work today. Especially with our observers who are just having to stare at the screen for hours on end and are not involved with half of the back and forth that we're doing in today as well. I should probably reiterate, we did have kind of a mention of that we've had to reposition Uranus back. It will affect the data somewhat. It will mean that there will be a couple of pictures, a couple of spectras that will be, we will need to highlight that Uranus is not in this, so we do not include that in our data. It won't affect massively as long as it wasn't for a long period. I don't think it was for longer than perhaps 10-15 minutes from when I last checked. But it will be something I'll have to look through in my data itself. The worst scenario I would possibly imagine, which it hasn't happened today, is if we ended up with several hours where we weren't observing Uranus. That is where it starts becoming quite detrimental. We mentioned before, Uranus has a 17.24 rotational rate, which basically means that's a Uranian day at the planet. So as soon as you stop looking at Uranus for 1 hour, let's see if I can do my maths very quickly on Google. We lose about, about 20 degrees of rotation in 1 hour. So if we stop looking at Uranus for an hour, I'd lose about 20 degrees on the map that I'm trying to prepare for Uranus, roughly. So again, a couple of minutes isn't too bad, 10 minutes isn't too bad. It's when we start getting into the hours is where it would become a bit more detrimental. But at the moment we're okay. And the fun part of, I suppose, putting this proposal forward was that I ensured that there were these overlaps where we were looking at Uranus. So every night we are viewing for about 150 degrees of rotation at Uranus, with about 8 hours observing at the planet. Because of this, if you 3 times 150, you end up with 450 degrees, which obviously is one rotation of Uranus plus 150. No, I'm getting myself muddled. 90 degrees extra. So we have these nice little overlaps between days, where if we do lose if we do lose some data, we're going to be hopefully covered by those overlaps. So we are now just 1 minute past 3 in the afternoon here in the UK. I believe that is about 3 in the morning in Hawaii. Let me just check the cameras if I can. I don't think I can at the moment, but it's about 3 o'clock, I believe.
It's 4 in the morning in Hawaii right now.
4 in the morning, apologies on that one. So 4 in the morning, so it's getting towards daylight break on their end. I believe, let's just have a quick check of the schedule here. We are making our way towards the Q&A section with the HC Plus team. Perhaps I will very quickly bring up the presentation, which I got rid of, so I'll bring that back up again, of today's schedule and kind of what's going on. So we are kind of at the end of the day, but I thought it would be good just as a kind of another reminder of today's event. So we have the Weird and Wonderful World of Uranus, which is a live stream of the planet Uranus in collaboration with the Royal Astronomical Society and the University of Leicester with the School of Physics and Astronomy. That has been taking place over the last 3 days, with today being our last day that we are observing at Uranus. Let's see if I can get to the next slide. So we are today using the IRTF telescope facility. or the Infrared Telescope Facility, apologies. That's what it stands for. The IRTF stands on Mauna Kea, which is found in Hawaii, which is how we at Leicester are able to observe up at the sky. As I'm sure you can tell from the background, it's very bright at the moment in Leicester, and there wouldn't be a way that we could see Uranus without being able to see the night sky. So here you're able to see the telescope itself, the images that we are producing, and you can possibly see on my second screen once we come out of the screen share that we have at the moment, are the live images that we are taking from the telescope, which are looking up into the sky and observing not only Uranus, but the moons around it, along with showing you pretty much the raw data that we are obtaining from these observations. So we hope you've been thrilled from the amount of data that we've been getting, but as well the discussions that we've been having here, not only with Dr. Rosie Johnson, who is with us, and Dr. Tom Stallard, but also many of our other speakers who, if you would like to hear any of their talks from the previous days, I believe there are YouTube links, very similar to the YouTube link that we currently have for today. But if you type in the Weird and Wonderful World of Uranus onto YouTube, I'm sure you can find those links. I should also stress we have our affiliates for today's stream and Zoom chat, as far as of the Royal Astronomical Society, the University of Leicester, the School of Physics and Astronomy, the Herschel Museum of Astronomy, and the Bath Preservation Trust, which without them, there'd be no way that we'd be having this live stream at this moment. So going on to today's program, so that's Friday's program. Apologies, I thought I had changed that one. There we go. Thank you for bearing with me on that one. So we have just finished up discussing with Dr. Rosie Johnson about her work with HD+ and at Jupiter, and the fascinating properties that we're able to understand with HD+, such as velocity and temperatures, and even looking at intensity levels, which are kind of the brightnesses that we see at the planets. We are now making our way towards a Q&A discussion with the HD+ team, which will be with myself, Dr. Tom Stallard, along with Dr. Rosie Johnson. I don't think we're able to have anybody else from the HD+ team, but if they are listening into this live stream or in the Zoom call, we would love to have them come along and chatter with us. They know that we are lovely. Well, hopefully they know we're lovely people. And once again, we'd love to hear from them on that front. Otherwise, the next 2 hours or so, we will also be dispersing in the view that we're getting from Uranus, along with the moons, and I will hopefully also be able to bring up some of the links that we've had from previous speakers. Specifically, Professor Steve Miller has mentioned about some of the work that he's done, and I'd like to kind of bring that back up, as perhaps it hints on why we in science are a lot of our science is required with collaboration. Collaboration is such a key thing, especially when it is international collaboration. And as one of Steve's works that he's brought up really points on this. So I want to kind of bring that up a little bit later, along with a raw view of the spectrograph that we were mentioning before with Carl and Cartman. We'll bring that back up for live streaming, so you guys can see exactly what we as the astronomers see. So there we go. So that's today's schedule. So we are pretty much making our way towards the Q&A. I may start that just a little bit earlier, unless we have any further questions for Rosie. We have a start of one. Let me just have a quick look. Oh, that's a that's a hard question. I don't know if Rosie, you're going to have much have an opinion. Well, I say an opinion, insight with this part, just because it's with the atmosphere side of things. I wish we had Dr. Lee Fletcher with us, because he is an absolute whiz when it comes to these kind of questions. But we have from YouTube, we have what are the cloud compositions on Uranus, and how different are storms on Uranus in comparison to that on Earth? I suppose for yourself, Rosie, if you have any insight with any kind of cloud formations with Jupiter, or perhaps any kind of things that you've noted whilst doing your research at Jupiter.
Yeah, so the cloud formations at Jupiter, they're different to the cloud formations at Earth, but they're also kind of similar. So like I said in my talk, Jupiter spins really fast. It's like going around like once every 10 hours. And this kind of like makes these like different atmospheric layers. And if I don't know, if I could prepare a presentation, then there's like these nice pictures where you can kind of see like underneath the Jupiter stripes, there's kind of like these tubes. I don't know, this is not a very good explanation. Basically, like at the Earth, I don't know if any of you did geography, but we kind of like have 3 atmospheric cells. Cannot remember the names of them off the top of my head, but there's like kind of like one in the equatorial regions and like one mid-latitude, like one polar one, and then like the stripes at Jupiter, like we can't really, like Earth doesn't have these like 3 stripes, but if you see like, oh yeah, Hadley cell, Tom has said one, it's probably like Arctic cold polar cell, I imagine it's called that, and then like equatorial one. But anyway, like we can't see like those as like 3 stripes on the Earth because our like air isn't so colorful, but like you can like if there's like a tornado, like it will go and it will kind of like work its way through a stripe like that, and it'll work like diagonally because of the Coriolis force from the Earth spinning. Like the storms like to go in a certain way. And then yeah, so thinking about Jupiter, it's got like more than 3 of these like cells, and these like make the stripes, and then the stripes kind of like have different colors because of the like, so like ammonia, and like I think ammonia is red, and then like the what do you call it, like the foggy, what's another word for fog? Hazy like white, like water vaporyness. So there's just like the different colors, and then they make the stripes and they sort of like interact, and then yeah, and then you have the really long-lived storms like the Great Red Spot, that like people often describe as like a massive hurricane, and it's just like so big that it can last for like years and years and years, whereas like on the Earth they're like too small, so then they will like disperse eventually. So then like going over to Uranus, which I'm less familiar with, it sort of like looks like more smooth. So I guess it's like kind of the same, like it doesn't have that like it will have like cells, but then like at Jupiter there's just like so many and they're so stripy. That it's not the atmospheric composition at Uranus is different. So yeah, it doesn't look as stripy. I don't know how many cells it has.
So that, I mean, there's likely to be a moderate number. It's really interesting. The ice giants have weather cells that sort of fall somewhere between Earth and Jupiter. Jupiter has these very long-lived weather systems. Saturn has much shorter-lived weather, but often great storms that last a year or so occur once every 20, 40 years. And then Earth's weather, you know, for a few days at the most, usually, or maybe a week or so at the most. And both Uranus and Neptune tend to have intermediately spaced weather. So it's one of the big questions that we have. One of the reasons we want to go back is to understand what allows those to develop. Famously, Neptune is much more active and has much more interesting looking surface features.
It's got its great white spot, doesn't it?
Well, it's had a whole range of different spots, but they have all gone. So the classic one is the great dark spot from when Voyager went by. But Heidi Hamill was talking about that yesterday and explaining how when she went back to observe, I think it was only a year later, it had already gone. They're very much less stable, even though they're very large in terms of the size of the planet. Certainly bigger in terms of the radius of the planet than even the Great Red Spot. Uranus is frustratingly described as being very blank and not having very much. It's not really fair or true. It's partly less active because it doesn't seem to have any heat inside of it. So when you look at the temperature of the lower atmosphere of Uranus, it is basically heated by the sun, which limits the amount of activity you can have. But even then, if you look at the right wavelengths, there's a whole range of cloud activity and all sorts of wonderful swirls and patterns that you see at Uranus. So it's definitely still got lots of activity. It doesn't spin as fast, and it's that spin speed that really determines how many cells you get. So Jupiter has all these very, very narrowly constrained bands because it's spinning so fast, and Uranus and Neptune spin more slowly. And the color comes from the differences in composition. So unlike Jupiter and Saturn, both worlds are dominated by methane. So they both look bluish. The level of absorption is different for the two. So there's more deep red absorption, more methane absorption at Neptune. And so it gets this wonderful deep navy blue, whereas it's a slightly less high level of red absorption. So you get more of a cyan color at Uranus. That's the main clouds that we see, especially for Uranus. It's almost all methane. There is a little bit of hydrogen sulfide, if I remember rightly, H2S, I think it is, remembering back to Lee's talk 2 days ago, which seems an eternity ago now. And I think they see some ammonia as well. So Henrik Mellon, who was speaking a little while ago, two days ago, 1 day ago, who knows, at this point, has been working on modeling those using the Nemesis toolkit that Lee was talking about, modeling both the methane and the ammonia clouds at different depths for these planets. Then there's all sorts of theoretical clouds too. There's probably water clouds deep down, but we can't see them, unlike Jupiter, where we see these beautiful white clouds at the top layers of Jupiter. So that's, I think, covers everything that was asked. I hope so.
Pretty much.
And more.
Yeah. So say thank you very much, Rosie and Tom, for your input on that one. Again, I wanted to say thank you very much, Rosie, for your slides and your talk today. I don't think I highlighted that before. So again, thank you so much for your time. Again, if you don't mind hanging around for the Q&A with HC+, I guess we've already started that one, but if you don't mind hanging around longer, that'd be awesome. We would appreciate it. I'm just looking through some of the questions today. So I think we've got some more rounded off questions with Zoom. So I'm going to go back to Zoom. So there was, I think, we have a good question, but I might have another question just because we've kind of touched on a similar kind of topic at the moment. So I'm going to go back to another question from the audience who says, I'd like to ask what Tom doesn't know about the solar system / universe that he wished he did. I mean, is there anything that Tom doesn't know?
No.
It does feel that way.
Vast swathes of everything that I don't know. I think we all live in a large amount of unknowing, but I mean, there's things I don't know that other people do know. There's a lot that I wish I knew more about. I wish I understood life and biology better. That's something I continually work on, understanding the processes. I'm very fortunate that I work on an undergraduate program at Leicester called Natural Sciences, and that's a joy because we just did a workshop this last week, and it was me, a chemist, and a biologist in a room talking to undergraduate students, and that's just such a fantastic opportunity. So John Perlman, who works at Leicester, is a microbiologist. It's also very helpful when you hear people talking about the pandemic, because I know virologists that can tell me the right answers, which is very useful. But that whole aspect of the life question is a boundary that we are slowly walking towards an understanding of. That's stuff that other people know that I don't know, but there's a huge swathe of stuff that none of us know as well. That's really interesting and fascinating. I think the big question that sits in the presence and mind of everyone within solar system science is there a super Earth somewhere on the edges of the solar system? Just like we were able to use the orbit of Uranus to measure and find the gravitational pull of a new planet. That was the discovery of Neptune, the first mathematically discovered planet in the universe. And of course, there's been many mathematically discovered ones since around other stars. We were able to show that there had to be a planet out there before we were able to see it in terms of reflected light. And more recently, there's been a whole investigation into the various orbits of some of these far out small dwarf planet worlds, a bit like Pluto, that sit at ever increasing distances from the sun, and they all seem to have an odd alignment in their orbit, which really potentially indicates, it could be statistical, it could just be luck, but as we're finding more and more of them, it seems more and more likely that somewhere out there sits an enormous planet, something bigger than Earth. And so let's hope we can find that. The other really, really big mystery, again, going back to life, is there life elsewhere than the Earth in the solar system? Can we detect it on Mars? We certainly haven't detected it on Venus, but maybe we'll detect it on Europa or around Enceladus, or possibly even on Triton. Who knows? So those are big. There's a lot of things that we wish we knew about. And there's a lot of things that we do know about that I don't know about. That's the joy, is finding out those things as much as you can.
Of course. I mean, I think the world would be a whole lot more boring if we only had 3 or 4 people who knew absolutely everything. You know, it's so much more fantastical that we have thousands, possibly even millions of people that all know, all experts in their own way of specific areas of science. And it's why at the end of the day we have such a big push on needing to have collaboration between, not even just in physics, just as Thomas pointed out, over many sciences and even past the sciences, looking towards the arts. It's such a needed thing, and we really do need to push a lot more when it comes to those kind of collaborations. So again, just reiterating so many points that we've said over the weekend, but it's the collaboration between so many people that really makes the work that not only we do, but I would imagine so many others do in many fields of science and past science. So say thank you very much. So I think we have a couple more questions. I was going to pick up on this one because I think we might even be able to give our own opinions here at the HT Plus team. So we have a Zoom anonymous question asking, how often do professional astronomers have problems or issues with observing? Have there been any fiascos with observing that have affected anyone's careers or lifelong work? So I was going to open that up to Rosie first, if there's any stories that you have for us with observing.
Wow. One time I observed Saturn's rings instead of Saturn's aurora. And I think Tom is still my friend. So thankfully it didn't affect my career. Tom didn't send me away from astronomy, and he didn't tell me never come back. And I learned.
I think I'm trying to think what you could do as an astronomer that would end your career. I think it would be really hard. I know that some telescopes have limits on how far you can tilt them over, and I'm not aware of a way of breaking those limits. But if you were to say force IRTF to keep slowing down and down, there would come a point that the mirror would fall out, because there's no constraints on the mirror, as far as I know, holding it in place, because no one would ever be mad enough to tip it all the way over. So that might do it. That might end your career. Or you would crash it into the ground and break it forever. I mean, those kinds of things. But I'm fairly certain every telescope in the world where that's a possibility must have a multitude of limits on you being able to do that. So unless you're actively being pernicious, I don't think there is a way of breaking things to the point where it goes horribly wrong. And, observing is hard. So of course there's mistakes. We always make mistakes. We made a mistake today. It's a natural consequence of doing difficult astronomy. But the outcomes ultimately are pretty unconsequential. We're not asked to pay the money back for the time that we wasted in our observations. We do our best. It's in our interest to make sure our observations come out right. And so it is difficult, especially if you're observing from the mountain itself. I mean, it's very relaxing to sit in your living room and observe. But when you're up a mountain, it's very cold. It's nighttime. You've probably not had enough sleep, because it's really difficult to sleep at 3,000 meters up a mountain. it is even harder to sustain your oxygen levels at 4 kilometers up a mountain. So you are always struggling with a certain level of altitude sickness, which, is difficult enough if you're doing exercise, but it's even harder when you're just sitting and the only thing you're supposed to do is think. It's the hardest thing in the world. So I think all observers have made silly mistakes because they don't have enough oxygen and they haven't realized something is wrong. So you may not open the shutter on the telescope, or you may not put the slit in, which is something we almost did yesterday. These things happen all the time. It would be a madness to get mad at someone for doing it, because everyone makes those mistakes. It's a natural consequence of what we do, that we have to be pretty relaxed, because there's so much that can go wrong that is no one's fault. The weather might be bad, or the computers might crash, or the server might break, or you might have some cable fall out, which has happened to me before, or there might be an earthquake, which has happened to me before, or who knows, that your instrument might explode, which has happened to me before. There's 100 things that can go wrong, and even something really dangerous and dramatic like an instrument exploding, no one is at fault for that. It's the difficult nature of what we do in astronomy. So I don't think you could ever be in the place of ruining your career. I hope not. So something else to keep me up at night, certainly the idea that I might be able to do something that would ruin everything.
There you go, Emma. So
Awesome.
don't worry about it.
Oh, I know not to worry. I've already had 1 or 2 observing runs myself where I have thought I picked the right place, and then I've gone to the right ascension and the declination, which is essentially your point in the sky, and gone, oh, nothing there, and found out, oh, I put the declination and then the right ascension, so I've put things the wrong way around, and gone, that makes a lot more sense, let's go over to that way instead. But that will usually mean that we have to wait about 10 to 15 minutes for the telescope to move over and get to the right object again. So I said, thankfully, now being about midway in, I'm a lot more patient with myself for getting things wrong, rather than at the very start where you're very conscientious that you want to get everything correct the right time. I'm a lot more accepting, especially with myself, when it comes to, oh no, we've mucked something up. I'm like, it's okay, deep breaths, but just continue on. Yeah, all thumbs up. So excellent stuff. So thank you both of you again for your excellent responses. I am just seeing, so I wanted to touch back. So this is a question that I saw that was going to be quite interesting for a HD Plus talk, I think. So it's a discussion with have electrical storms on Uranus similar to those we've seen on Jupiter been observed? That one, I don't know myself. I possibly need to ask with Tom. But could these produce any significant quantities of HD plus if occurring at a sufficiently high enough altitude in the atmosphere?
So there definitely are electrical storms at Uranus. This is something that was brought up a couple of days ago, I think.
Yes,
we haven't been able to observe them directly, but one thing that electrical storms do is throw out a whole load of radio emission. So when we were flying past with Voyager, they were able to detect the radio emission from some of those lightning storms. It's a technique that we've used for Jupiter and Saturn, and for both those worlds, we've been able to do it at the same time as taking images of the night side, so you can actually see that very clearly. But those lightning storms typically happen much, much deeper down in the atmosphere. So it's possible that they could run some kind of current and drive some kind of variability. They don't sit super deep, so it's possible that there's some kind of interaction, but it's unlikely, I think. So generally speaking, I mean, if you were able to somehow induce those currents at the top where the H3 plus is stable, then it will probably have a very dramatic effect, yes. But I think generally, in order to build those storms, you need to have them quite deep because you need all of the friction. And so the atmosphere is a bit thin to do that.
Also, I'm afraid I haven't much to add to that. Tom's going to know that a lot more than I have. It'd be incredible if we just had bits of lightning just shooting up HD plus, but I think that would lead to so many more questions within our field. There'd be so much variability we'd see on Uranus if that was the case.
I mean, it's a great way to sort of understand dynamics because, you know, you can use imaging on the day side sometimes, but that also can have some limitations, especially with a place like Uranus where there's a lot of haze. So what you can actually get from that is if you are able to image on the night side, you can see the bright sparks of those lightning storms really clearly if you do a nice long integration. So certainly for Neptune, that was something that we were looking at for the Triton mission, whether we could do observations as we left the system, but looking back at the dark disk and seeing whether we could just see the bright flashes from the lightning. And then, of course, we could tie that in with any of the radio signal that we saw. So if we are able to return, that will definitely be a focus of investigation. We'll be looking at the radio signals, all of those wonderful like Whistler waves and stuff that you get in the radio signals that you get off of the planet. And then also, hopefully, very high resolution imaging that we'll be able to search for and find small scale spots that are very bright and show us the exact location and dynamics on the night side. It'd be really cool.
Yeah, that'd be amazing. I'd love to see high res images. Awesome, thank you very much, Tom. So I've spotted an interesting question, just because I think there may be in context with Uranus, but I kind of wanted to touch on this a little bit with Jupiter as well. So perhaps even with Saturn, are there any solid structures in the planet? Now, this could be probably taken two ways. It could mean solid the matter, but I think one of the interesting questions that would lead to this is what are constant structures that we see at Jupiter and at Saturn, and even with Uranus and Neptune? We've discussed a little bit on Uranus and Neptune, but I don't think we've actually mentioned much about the structures that we see at Jupiter and Saturn. So I open the floor to both of you if there's particular structures that you'd like to point out for the audience.
So I didn't understand what you meant by structures. Otherwise, I was just going to say the Aurora.
There's the Aurora, of course. So
does that count?
I mean, the Aurora certainly counts. It certainly counts.
Do you want them to be more solid?
So I'm thinking possibly consistent structures similar to at Jupiter. We have the Great Red Spot. That one's a great highlight that we have our own HD Plus research in at the moment. Tom can probably go into more detail on that than I can, because I only know kind of the script notes than anything.
Jupiter's got a lot more constant nature in its atmosphere than any of the other planets, and so I mean it's really the only place where you have some level of continuity. I think you've got this really weird storm, which we are still not completely sure how old it is. There's some people that think Hooke saw it back in 16 something, and there's other people that thought it took till the 1800s before we were able to see it for the first time. We know it's changed in size over time. So over the hundreds of years, it's shrunk by more than a factor of 2. It's much smaller than it used to be, if we believe the drawings of our forefathers. But it's definitely changeable, and it's probably not very constant, I would say. I mean, Saturn's rings seem like a constant structure, but some of the work that James O'Donoghue has been doing has suggested that they may not be more than about 300 million years old, certainly old, but nothing in comparison to the age of the solar system. You know, probably less than a tenth of the age of the solar system.
And there's also there's like the storms at the poles of Jupiter. So there's like massive hurricanes like in this structure with like a hurricane in the middle. They look really cool. And then at Saturn you've got your hexagon with the little storms in each corner. So those are both sort of permanent, like evolving features. Like they are changing, but they've been there for a while so far, and they're very interesting to try to understand, because like a hexagon kind of feels like a geometric shape that isn't like sort of natural in a way. It sort of looks a bit weird maybe in an atmosphere, but actually like when they try to model the fluid dynamics of the situation, the hexagon is kind of like coming up naturally. So even though it looks a bit weird, like that's kind of like, you know, they've solved an equation of fluid dynamics and they get a hexagon. So that's really interesting.
We're talking about solid in the more traditional way. Well, we should probably talk about the Earth a little bit to try and give some context, because we all know that there's obviously a solid surface on Earth, but as you move further and further into the planet, it gets a bit more difficult to say whether something is solid or not. As you move down into the mantle, over very long time scales, there's certainly overturn and active dynamics that allow heat to rise and the motion of various areas. But really, I mean, in terms of how we understand solid, it's still a solid, even though over those very long time scales it's able to move. There are limited areas, like a percentile, that is actually liquid as well, so there'll be small areas of melt, and that's largely how volcanoes are able to form, through those boundaries between crystals where melt can occur. And then, you know, as you go deeper, you get to a layer where suddenly there's a very sharp boundary between rock and metal, and then you move into an iron liquid core where it's very much a liquid, but it's not a liquid that we would really recognize. It's such incredible pressure and temperature. It's just that whenever you have a combination of pressure and temperature, you can have phases of solid, liquid, or gas. And so as long as you have a balance between the pressure and the temperature, you can have either a liquid or a solid. But it's, you know, a massively, vastly more pressured system that is also super, super hot, and it happens to allow liquid iron to exist. And then as you go deeper, the pressure goes up more than the temperature goes up, and so you end up with a solid iron core. And so you do have solid and liquid, and you presumably have structures within the Earth associated with that. We talk about these wonderful spheres, but maybe those spheres aren't really spheres, and there's undoubtedly all sorts of interesting stuff. Sorry, my neighbor is busy drilling right now. So you undoubtedly have like all sorts of wonderful columns and heat welling up, causing volcanoes on the core of the Earth, spouting out material into the liquid surrounding it. But is that something that we could really talk about as being a structure? I don't know. And so the same thing must happen in Uranus. What we do know is that, you know, if you were to drop a probe into Uranus, it would be destroyed before you get to anything but gas. Under the current techniques that we have, you wouldn't really get very deep. Maybe it would become not either a gas or a liquid, but then that's a bit of a cop-out. A supercritical gas is sort of a gas. And, you know, the surface of Venus might have supercritical CO2 on it. We don't talk about oceans on Venus's surface. We think of it as a gas. So generally that would be true quite to some depth, but then pressures would change, and we would start allowing things to solidify. So certainly we're used to the idea of ice and water in liquid phase. So you cool water down and it turns into ice. So that's the ice we know. But there's very many other kinds of ice that only exist if you've got a lot of pressure. So there's a lot of models of the interiors of the icy moons, for instance, that deep down form different forms of ice. And so certainly those will exist in the cores of both Uranus and Neptune. So there will be areas of that interior that will be solid ices in different phases, in much higher pressure phases. We're much more aware of ice in terms of water because there's so much investigation into those, but there presumably are other phases for other substances. And if you start blending them, they will have very different configurations that allow solid or liquid. And we just don't know. The answer is we just don't have a good enough understanding of the interior to really know what the boundaries are. What we do know is that there is probably a bit of iron. There's probably some silicates, like Earth is made of, in the middle somewhere. We don't know the pressure or temperature regimes for those, so we can't say whether that would be liquid or solid. And then there will be a huge array of different ices that may well be turned into a solid or a liquid. It could be that there's a vast oceans deep under Uranus and Neptune, but they will be under such incredible pressure. They won't really be comparable to the oceans that we know.
Awesome, thank you very much, Tom. That was a great way of going through. I mean, we went through a lot of solid structures, many different definitions too. So I greatly appreciate both of your insight there. I really don't have much to add actually, so thank you both. So I'm just having a look for any more questions. My thinking at the moment is we will continue for another 7 to 8 minutes with a couple of Q&As, and then I thought it might be a nice idea to go back to focusing with the cameras. So the cameras going back to the view that we're getting at Uranus, a bit of discussion about, obviously, since unfortunately having possibly a galactic cosmic ray derail us for a little bit. So a little bit of discussion of how we return back to work in terms of returning back to doing spectra, any kind of things that we have to do in between. So I have probably the last 2 or 3 questions before we move our way over, and then possibly, I think we've got plenty of time, so I will also bring up Professor Steve Miller's work discussing about the global collaboration to find HT plus at Jupiter. So let me just see. So I think I've answered most of our questions on YouTube. So this is back to Zoom. We have 2 questions. So I have one quick question, which I think Tom will be able to very quickly answer. Is Dr. Stallard's whale model supposed to be a blue or a sperm whale? I'm afraid you're muted, Tom.
Right. Yeah, it's I believe. Well, it looks like a sperm whale to me, looking at it in the camera. It is. I see it as an ancient god that's about to devour the moon. That's what I like to think. Certainly.
Little mascot that I always see every day.
Definitely.
Awesome.
It's an imposing figure in my background.
A reminder to us all. A second one that I think would be interesting. It's going to be difficult on knowing exactly how we can go about answering this, because obviously it brings up some of the politics when it comes to science itself, which is, but on the topic of sharing knowledge, how do we feel about Sci-Hub? It may be a charged topic they mentioned, so perhaps you want to skip it if that is the case. I mean,
I'm
I don't know too
Googling
much.
Sci-Hub because I have no idea what it is.
It's the place where, so like, people can put up papers, so people can access them for free. So for those of you who might not know, when we publish journals, if sometimes maybe I'll start from the start, because this is I find this very, very interesting, because some people don't understand. They think because we publish work that we get paid for publishing work. We do not get paid to publish work. So we publish work because we're really interested in it and we find it really exciting, and we really want to share our results with everyone. And then also when we publish work, it really helps us in our careers. So it helps us to get like our next jobs and things like that. So we just want to share our results with the world so that everyone can work together. And well, that's what I think. And I think Tom and Emma probably agree. But so when we publish a paper, we have to pay that journal to publish our work. So that money will either come from like a grant that you're working on. It can come from like your institution. So your university might have money, and then they can help you pay. So it doesn't come out of our wages. We don't pay for it ourselves, but it will come out of some sort of pot of money that our institute or grant will have. And then if we want to share our research with the world for free, and we want to make sure that everyone can access it and they don't come up against these paywalls. So the journal might have a subscription that you have to pay. And maybe not everyone can afford to pay that. So quite a lot of scientists like to do open access, it's called, so that your paper is like available to everyone. But that costs more money. You have to pay more to have your paper published as open access. But it's now often a requirement. If you receive funding, you have to publish open access. So can be quite like difficult. That's why Emma was like, oh, it's like a little bit political. So yeah, so to get round, sometimes people can't always afford to publish open access. And then, this is quite often why things end up on websites such as Sci-Hub, where the papers are there, someone's like downloaded them and then they just put them on there for free for everyone to access. So that's kind of like just a quick summary, because not everybody knows how this like publishing thing works. Like a lot of the time I get my friends and family, like they think that we get paid, like, like an author writes a book, they get paid to write a book. We do not get paid. We just have to write papers as part of our job, and then we have to pay thousands of pounds to publish that. And then if we want more people to read it, so we really do want more people to read it, because not every scientist can afford to buy access to these papers. So anyway,
you
that's
also need to pay for access to those papers, and sometimes our universities don't have access to those papers. So I've certainly been in the position
to access your own paper
of not being able to access my own paper because my own university doesn't have a license to access the paper that I have made. So it's super frustrating. I can understand why people would want to pirate. I don't think it's the right approach. I think the right approach is what we're moving towards, which is the requirement that we have to have everything remotely available. So if you have funding from within Europe from any government agency, at the moment you have to make sure that it is available through some route. So whether that's on one of the more official repositories or your own university's repository. And I think it's moving towards a more absolute version of that, where we will be required to only put our papers into journals that have full gold access, as it's called. So the problem with that is that it does provide real tension within the international community, because if you can afford to publish in Nature, which is for open access about $4,000, something like that, then you can get into the most esteemed journal in the world. And if you can't afford to do it, then your papers won't be seen as broadly, and that's really problematic. So, I mean, the ideal would be that we would just burn down all publishing houses and start anew, but that doesn't work. I mean, there's been many examples of people starting new journals that are open access. The New Journal of Physics, for instance, started way back in 1998, and one of my colleagues was one of the first to publish in it. But it's still out there, but it's not considered as weighty or as important as others. And it's a sad facet of the way that we work, that we want our papers to be read and people don't have time to read them all. I think that's less true these days, because it's not that we're going into a library anymore. But it's still certainly true that if you have a Nature paper that's seen around the world, and if you have a paper in the monthly notices of the Royal Astronomical Society, if it's a really important result, it may be seen, but it's unlikely to be seen as widely, even if it's just as important a result. And so because of that, it's incumbent on us to try and sell our work as well as we can. And so we are caught in that nasty loop. And the only way around that loop is government action. So that's why in Europe, at least, things are a lot better. And what we really need to do is to ensure that happens everywhere, not just in Europe, that the whole world plays on an even playing field, and that everyone has to make sure that their material is available, open access, so that everyone can read it. And it's super frustrating. The people were asking questions on chat, and I wish I could send them some of the papers, and you just can't. You send them a link to a thing that requires them to pay for it. So it's not a good situation to be in. Ultimately, something like Sci-Hub won't work because it's not official enough, and so it will be taken down because it's copyright infringement. So you can't rely on it, and you have to have systems that you can rely on. So there are really good repositories where, as academics, we can say that we give up our version of copyright, but of course sometimes we are giving away our copyright to the journals. So we're not getting paid, we're giving up our copyright, and then we have to pay to access them. So
imagine if we got paid.
We don't get paid to review them either, so we are incumbent on every stage.
I was just going to add on this. It's a slight detour, but I guess on a similar topic of sharing information, there is, on the flip side, there is GitHub rather than Sci-Hub. GitHub has been incredibly helpful. I know Henrik has done a good couple of bits of his work he has put on GitHub. GitHub itself is a website where anyone with any bits of code, to my knowledge, can put in what they have and basically put it up for anyone in the world to be able to download. Well, I'm more familiar with GitHub in terms of the Python packaging. That's what Python, I use the language for a lot of my coding. For the analysis that we're doing today, I will be using Python to try and understand what's going on. And if there was anywhere that I would say, even for coding, for data analysis, you want to really get a wealth of knowledge. GitHub has so many different coding projects that people have put up there, and to my knowledge, most of them are pretty much free, whether they are individuals that have perhaps their own Patreons or have their own support from fans or people who use their own work. But it is an incredibly useful site, I find, when coming to coding, especially with Python. So places like GitHub is incredibly great. It's an amazing place. That's what I can highly stress. If you're doing any coding, I would strongly go to GitHub and just see what's there, see what you can play with. So thank you both again for answering. I think that's the last of our questions that we have on Zoom, but we are just a bit over actually from when I said we were going to make our way back over to the telescope. So I am going to share my screen, but this time rather than sharing Kyle, I will share Cartman instead, which causes this interesting view on the other camera. So let me just bring up a in-between image whilst I sort this out. So there we go, sharing the screen, hopefully now, and this is with Cartman. So Cartman is a little bit different, obviously, than that of Kyle. Kyle is the imager that we use, so that's to give us an idea of what's happening at Uranus. Instead, we have with us at the moment, this is Cartman. This is our spectrograph. Again, if you haven't been here for kind of the discussions we've had about what a spectrograph is, a spectrograph is essentially a very fancy prism. Remember, with the prism of light, we can basically shine light in, and we actually get a diverse amount of colors that come out of the prism. In this case, we're actually looking far beyond what we'd normally see as a rainbow. We're looking in the infrared or the near infrared, which is found between, for our investigations, about 3 to 4 microns. So what we're seeing here is basically, this is exactly my view, just on my other monitor that's just above this laptop. This is what we use to capture the data that we're getting from Uranus. So you can possibly see the screen that I have been broadcasting is with screen 3 here, just at the very bottom right of the display panel, just in the very middle of the screen that we're observing at the moment. For those of you that were around when we were showing the raw view from Kyle, I think you'll see a lot of similarity, a lot of similarity that's happening at this screen than the previous one. And what I mean by that is on the very left-hand side, we have the UI or the interface for Cartman, where we have the I time, that is the integration time, that's the amount of time that we spend at a single focus or a single point. There's the coads, which the coads we use to basically add on signals. So in this case, we have 30 I time with 3 coads. So that means we take about 90 seconds for, I believe, each frame. And we're doing 100 cycles all the way through. What we mean by 100 cycles is we have what is known as this beam pattern AB. And we're just saying at the moment, very live, is this is our observation log. I think before we were mentioning, we have our own log where we note to ourselves or note to our later selves of what is going on at the time. As you're seeing here, we have a number of comments telling us what's going on, where we saw things, if something went wrong, if it did, where it went, that kind of thing, as well as letting us know if there are any issues. So at the moment, I believe we've just had observing going well. Uranus still looking quite clear, maybe 40 minutes more at Uranus. So that's a nice little heads up for myself when I do the data reduction, knowing how much longer the observations are going for. These are incredibly vital. Some of the work that I have been using, this is with observing Uranus back in 2006. I had comments from Tom way back then in 2006, which gave me the heads up that we were shifting from Neptune to Uranus, but as well the heads up that we had changed the orientation of the slit. So suddenly north was south and south was north, which at the time when I was trying to go through the data, I spotted something was very, very odd. So the first thing you always want to go back to is the observation log to find out who it was at the time. And second of all, what was going on, if they also commented on this. And thankfully, Tom did mention this. So past this, we then have the object. So we're looking at Uranus. The comment for today is that Uranus is the planet. So we have that part. And the observer, which we have our lovely and esteemed colleague, Nahid Chowdhury, who has been wonderful these last 3 days, has been patiently and diligently observing Uranus. I feel terrible that we haven't been able to have him come over, but unfortunately, due to the technical difficulties with Zoom, it is very hard to have 2 Zoom calls up on the same account. You have to be in one or the other, and so we needed to have at least one observer at the telescope Zoom as possible, as we're doing remote observing rather than being on the mountain itself. Finally, we have the autosave function, which again is a life sent. Autosave ensures that every image that we're getting, not only from Uranus, but also of our spectra, is saved into our directory, which our directory, numbers-wise, it looks a bit of a jumble. That's this path, path sentence, I suppose. It's not actually that much of a jumble. What you can decipher from it is that the 2021B079 is actually in accordance to which semester of observing we're in. So we're in the 2021B semester at IRTF, and the program number, so that's the program that I'm doing with the observing runs, is 079. So that's how you can know the coding there. And finally, the numbers just at the very end actually are mean the date that we're observing today. So it is back to front, however, so it is the year, so that is 2021. It's the 10th month, or October for October, and it is the 10th day here for for Hawaii, and here in the UK actually. We're now at the same time, but it's always good to kind of keep an eye exactly on these, especially when it comes to doing observations across many countries. So I don't think we discussed much about it, but there's actually these weird and funny pictures just at the very bottom. I'm sure we may have had a couple of questions about this, or at least some people scratching their head, and that's perfectly fine. We're not expecting you to understand it. When I first came to this, I too was having to ask the main observer on the day, what's this? Why does that look like that? Why is it that number? Why can't it be something else? So parts that I do know I can specifically talk about. We have the cal box. That is short for calibration box, to my knowledge. This is for when we need to take calibrations. What I mean by that is, I don't know if any of you are here for Dr. Sarah Casewell's discussion, but she mentioned about there being flat fields, about dark fields that we need to take. Essentially, a calibration box ensures that we have as much spectra that doesn't have anything lit up, or at least gives us a background lighting so we can see if there are any defects, if there's inconsistencies when it comes to the detector itself, where any consistencies that are on the detector, as well as any dead pixels, i.e. pixels that can no longer receive light, so that we're not having to try and guess in our data to try and clean it up. I've said this over the last 2 days, but when it comes to our data, what you're seeing at the moment is the raw data, and we will need to go through thoroughly, basically with a brush and dustbin bag, where we're getting rid of all the data. When I say data, all of these dead pixels, all of these inconsistencies that are across the CCD screen, in order to capture the data that we need for our investigations. We also have the rotator image. I know we've just had a comment on that one, which is, it's a lovely rotator image. Basically, that is, we right click on the rotator. I won't do it because I don't want to change the rotator whilst we are currently observing. but you right click on the rotator and you input which numbers you need to rotate the slit to. So you can decide if you're going to place this onto a planet, put it on straight onto 0. In this case, we want to ensure the slit is lined up with the north and the south pole of the planet. So at the moment, if you use a website, a very useful website, we use NASA Horizon, you can input basically, I'd like to know all of these variables about Uranus. That's the size it's going to be in the sky, its position in the sky according to its right ascension and declination. Again, that's basically how far up it is and how far left or right it is in the sky. Additionally, you can find out variables. Again, the most useful one in accordance with this one with the rotator is knowing where the North Pole angle is. So in this case, the North Pole angle is about 260 degrees, I believe, which I'm sure that by saying that, I'm going to have a lot of people go, but you're at about 870, about 90 degrees. What's going on there? Why aren't you more? Well, you know, why aren't you at that 260, 270 degrees? And that's because of a bit of an interesting time with Uranus. So when Uranus was first being observed by Voyager, we first defined the North Pole as the pole that is rotated by a whole 97.7 degrees, I believe, with the South Pole being, in fact, the one that was sticking up if we look at the plane where the Sun and the Earth are kind of rotating around, up being this way and down being this way. Since then, to keep all the planets in the same kind of consistency with one another, the IAU, that's the International Astronomical Union, I think. Again, don't quote me on that, that may be incorrect. They decided that they would actually flip this. And so in fact, what was known as the North Pole, and we call this the North Pole ULS, that's for the ULS is the Uranian longitudinal system. We instead now have the North Pole being at the top, though that was the previous South Pole, and the South Pole is the previous North Pole. So it gets very confusing, especially when discussing with other scientists about Uranus. You always need to, International Astronomical Association, apologies, thank you, Tom, Union, apologies. So yes, it can end up with a lot of fun discussions. You always need to preface when you're talking about Uranus or Uranus. I'm going to say it because I'm sure we've had a lot of people ask, why aren't you saying specific definitions? I am happy with whichever. If it gets a couple of giggles, I'm happy with that too. But whenever you're discussing with scientists, it can end up very confusing if you don't mention which system you're using. So when it comes to our papers, we always want to stress on that. So I've talked enough about the rotator. That was a long discussion on that. Finally, we have elements here such as the slit size. So we're using a 0.375. The reason we're using or reference 0.375 is actually the width of the slit that we're using at Uranus. So what I mean by that is Uranus in the sky, though it is many kilometers wide, in our sky it only appears a fraction of a degree. We're about 3.6 or 3.7 arc seconds for Uranus. So if you think on that, we're using a 0.3, we're about a tenth or so, possibly just over a tenth. Of the size of Uranus using with a slit. But the reason we're using this is, one, it's the smallest slit width that we can use with the slit, to my knowledge. And the reason we're going for such a small slit is to ensure that we can have the highest number of so that we can document as much as possible that's going on with the planet. The wider that we go with the slit, the more difficult it is to do our data. So specifically, we're looking for these emission lines because we have basically an analysis that we use with these lines to document the intensities. By widening up the slit, it becomes harder for us to not only to be able to pull out these factors, but actually to define localized areas. As soon as we start getting towards, let's say, if we were using a 1 arc slit, we would have a single pixel that would cover probably about third or so of the planet's disk itself, and we start losing pretty much a lot of the spatial resolution by going much wider than that. So hence why we're going as small as possible that we can with IRTF. I've probably discussed enough that's kind of going on here. I should probably discuss a little bit on the fact that, yes, we have 4 screens here. So screen A or screen 0, we have, I believe, the whole array that we're using for IRTF, which has a lot of lines. You're seeing kind of these little dotted lines. These are sky lines or emission lines that are still coming up within our spectra. We then have C and D, which I think C itself is a single spectra that we're getting through. I think it's single AB, but because the signal from Uranus is incredibly weak, if you remember I was discussing earlier, it takes us about 30 minutes to just about see a line from Uranus. The C that you're seeing is actually only 1 minute and 30 seconds. So hence why we really can't see anything, but as soon as we start building up that signal, that's where we can start getting an idea of what's going on. And finally, D in screen 1, and we also have D, but a zoomed in version on D at the very bottom. And these are the total spectra. Now, I should again stress, because we had the galactic cosmic ray, we think, unfortunately interact with our guiding at Uranus, we've had to reset with Cartman a little bit. We've had a slight reset with Cartman. So these are very similar to images that we were seeing back at the beginning of observations when we were starting to build up that signal. So if you weren't here for this morning, this is kind of a great way to visualize what we are seeing. What is kind of really cool again is we are starting to see the emission lines come through. So we're seeing Q1 just down at the very bottom with Q3 and Q3-1. When I'm using these letters Q1, Q3. What I mean by that is these are specific names we give to almost like fingerprints of H3+. H3+ only says hi at specific wavelengths, and that's why we're covering such a vast array of wavelengths on this spectrograph. So when it comes to these lines, we're very excited to see them, but it's more exciting when we can see a couple of them, because by seeing more than one, we can actually start getting a ratio of comparison of how these emissions are, how intensely these emissions are seen. From those ratios, we actually get an understanding of the upper atmosphere temperatures, and that gives us a good idea of what's happening with Uranus. Our colleague Henrik Millen has been diligently working over the last 10 to 20 years investigating the temperature at Uranus. We have consistently seen it being cooling by 6 Kelvin. I think that was the last approximation every year, with current theories thinking that this will continue to 2028, I believe, or roughly around then, where we are hoping the temperatures will pick back up again. But because of these phenomenally cold temperatures, this means that trying to detect H3+ at Uranus is actually getting much, much harder the closer that we reach 2028, which we should be the winter solstice for the planet. So I believe I've covered most of the things here. We do have the T3 remote, which again, we're not going to touch, because this is the old way that we used to do guiding at IRTF. So the red buttons are if we wanted to move on the sky by 5 arc seconds, we could press one of those and we'd suddenly shift over, whilst the yellow buttons are if we wanted to move by 1 arc second, so a little bit smaller, but in the past that would be the way that we'd need to keep on the planet if we saw the planet slowly moving off from the slit itself. I'm very thankful that iShell does that all automated these days, but obviously in the past that's what we had to do at the time. So I'm going to finish up there with sharing the screen and go back to our view in general. So I will bring back up, hopefully that's myself. I mean, oh, sorry, I'll bring back both of you back in. Apologies. I didn't know if you both wanted to have a longer break, take over a little bit on what we're seeing a little bit.
I just wanted to point out that, you know, those arrows on that digital system are also a very new invention and actually a great improvement on what we used to have. And so actually there used to be a big metal box in the control room with 4 buttons on it, and you'd have to press those buttons and manually move the telescope, and then we would have a guide camera that would be this flickering image of Saturn on a TV screen, and you'd have to sort of move it and hope that you were doing it right. That's why maybe some of my older observations aren't quite as accurately framed as these new ones are. Doing it all by hand. But yeah, obviously it's very dry at the summer because you want an environment where there's not a lot of water to look through. So it's very dry, and obviously static electricity loves dry conditions. So a big metal box in which you are about once every 5 minutes shocking yourself. It's a great way of spending an evening.
I hate electric shocks. I hated that so much. It also happens in like when I was in Svalbard, like, so yeah, in the Arctic, it's also very dry. And you're wearing a lot of like synthetic clothes and big woolly socks. Maybe you might be sliding down the hallway in your socks. It's constantly electric shocks.
Nightmare, I can imagine.
I did notice that Nahid said hello to everyone. While we were like, you missed it, but he wrote something in the ops log. So.
Oh no, I'm so sorry. Oh goodness. I may see if I can put it back up again and poke him to say hello to the audience in a very analog kind of way. I was just going to reiterate kind of back to the Uranus can. So I think the moons are starting to come back into focus. We were having a little trouble earlier spotting them, but I think we now have back. So, oh goodness. Goodness, for a light show.
There we
go. Yeah. So we should still have Umbriel, that is at the very top of Uranus. We then have Ariel just to the very side. And again, Miranda.
Yes, Miranda.
That is just peeking its way towards the slit at the moment.
Looks like it might go into the slit at some point soon, but hopefully it won't affect us too badly. I did look to see whether Ariel was going to go into the slit, because you can see now that it sits underneath the slit. But the slit that you can see here, the black line you can see here, is the full slit length. So that's how much is machined out. But we're using a more limited range than that. So sometimes you can see red lines. I can't see them right now on the particular, they are back now. So there's a red line over here and a red line over here. And those are the actual limits of where we're looking. So you can see that we're just capturing Uranus in this one side here. And Ariel was right here, right next to it. So I think it just missed. I was wondering if we would be able to see it as it crossed, but it didn't impinge in the data. If we'd been using a 25 arc second slit instead of a 15 arc second slit, it would have been wide enough that we maybe could have measured the reflected sunlight on Ariel as it crossed the slit.
Awesome, thank you for that one, Tom, because I know we've had a couple of discussions in the weekend regarding, we had a star come in and say hello yesterday. I'll see if I can get the video that we had up for that. Yeah, so this is yesterday's video sped up. So this is 8 hours of film sped up at Uranus, and you can see kind of what looks almost like a moon at the very start, shifting from the top left, making its way towards and just past the slit itself. But there was a lot of discussion at the time where we were wondering if it did come into the view, what we'd expect to see, but also discussions about trying to avoid seeing stars when we're doing observations. I think the best one we had was if you did end up with something in the way, what would you do? But also, I guess, discussions on the fact of just even trying to observe stars. Again, another topic we've mentioned a lot on is calibration stars. Something that I think pretty much is almost needed with a lot of spectra. I know Dr. Sarah Casewell was mentioning that she also has to do calibration stars to ensure that she knows what flux is coming out, and we too need to know, because at the end of the day, the numbers that we get from Cartman are CCD counts. That's basically photon counts. So that's the amount of light it's receiving. But I guess in that very GCSE physics kind of way of, well, that's nice that you've got a number, but what does that mean? What's your units? What's that in reference to? So that's why we use the calibration star, so that we can actually refer back to a known constant. So that's usually an A0 star, so that we can get an idea of the amount of light that we're getting from Uranus.
I think one thing worth pointing out, of course, is that that star looks like it's shooting across the sky, but it's actually not moving at all. Stars don't move very much in the night sky because they're so far away. So they do all move at some rate, but it's very, very low on a single night. What we're actually seeing is that Uranus is shooting past the star. So Uranus is moving through its orbit as we watch it. It's drifting across the night sky, and so we see it having a relative motion to the background, and it's that relative motion that makes everything we do a little bit more difficult, but a lot more fun at the same time.
Awesome. So I was mentioning a little bit earlier, and I think now's a great time possibly. We have Professor Steve Miller had mentioned about some of his work that he had put in, and I'll see if I can get the document back up again and be able to share my screen. So bear with me. There we are. So there we go. So we have here the collaboration collection, which is with the Royal Society, which discusses a number of collaborations which are found throughout many science areas. So we have the fine balance of the ATP activated potassium channels, as well as discussions into vaccine research and Cold War hot science. And there's a lot of discussions on the collaboration that occurred between scientists at the time. We particularly wanted to highlight, let's see if I can get to the correct page again, with Steve's work in this, there we go, which is discussing the collaboration that actually was pretty much the only way that we came across finding H3 plus at Jupiter. I took some notes actually, let's see if we can have these in time. There we go. So I wanted to just bring some really cool parts. Again, I would highly recommend if anyone has time to have a look at works that Steve has done, similar to these. We look up to Steve massively when it comes to this kind of work. He has done many, many years of H2 plus research, particularly in Steve's notes. Well, in Steve's insert here, he mentions about the paper back in 1989, which was the detection of H3 plus and Jupiter. In this, Steve highly discusses about the fact that the way that we managed to do this was through a lot of world collaboration. This is with scientists and physicists from both France, Canada, Korea, the UK, and the USA, with authors from Germany, Australia, India, Italy, and Canada, and the UK again. So there have been a wide range of people that have been key people in trying to discover H3 plus at the atmospheres of our gas giants, but in this case, specifically for Jupiter. Additionally, he also wanted to highlight that there is, unfortunately, there's a lot of unacknowledgement, but he wanted to stress of the people and the natural resources of Hawaii's cooperation when trying to do these kinds of investigations. So again, he wanted to highlight them as they are also key to these kinds of investigations. He wanted to mention that the detection of H3 plus at Jupiter relied really on the new generation of telescopes that were coming out at the time. There'd been a massive focus, particularly in the 1970s, on observing at Jupiter, which is the largest planet that we can observe, well, one of the largest planet in our sky, along with that of Saturn, but a lot of focus with Jupiter, with it being so large in our sky. So that was one of the key interests of trying to look for with a new telescope to see what was happening at Jupiter with this newfangled ion. Although I say newfangled, H3 plus actually was first discovered in a laboratory environment by J.J. Thomson back in 1911. So we're actually about 110 years of H3 pluses discovery, which is mind-boggling to imagine. And the paper for it is actually really fascinating. If you ever get a chance to put in for J.J. Thompson's paper on this, he has a long discussion of what he thinks H3 plus could possibly be, but he doesn't actually name it. H3 plus is not something that we fully understood until about 50 years later.
You may not be aware about this, Emma, but as you know, you are my student, and that Steve Miller is my supervisor. J.J. Thomson is in the lineage of our supervisors. So if you go up the supervisorial tree above Steve, because he was a chemist, it goes up through some very esteemed chemistry professors up to J.J. Thomson himself. So you are the great-great-great-great-granddaughter of J.J. Thomson himself.
Wow. It's, yeah, it blows your mind. It blows your mind to think that somebody so far up the academic tree of where you are was responsible essentially for figuring out the first parts of where your research could eventually end up to be. We also highlighted that Takeshi Oka from the University of Chicago measured the first fingerprints lines of the infrared spectrum that we see for HD+, and a lot of their work, I mean, even with what I'm doing myself, I frequently go back to and have a look at the spectra that Takeshi Oka provided. And we're so thankful for that. Kind of led us to begin to investigate HT+, but also look for HT+ outside of Earth and start investigating further with the outer planets. We also mentioned this kind of, I'm going to round off a little bit because I don't want to go into too much detail, as I'm hoping by doing so that a lot of our audience will be intrigued to want to know further on Steve's mentions of a lot of the history that he discussed about yesterday, but in his own words written up. But he mentions back in the 1980s, it was Casewell who observed emissions from Jupiter due to the hydrocarbons that were in the atmosphere. And so I would imagine that a lot of the questions that led us to investigating HD+ at Jupiter were due to these kinds of investigations that were looking at the emissions at Jupiter and wanting to just find out, to see what would happen. I mean, even these days, we have a lot of investigations where we don't know what the answer is going to be. We do it because we want to know what the answer is going to be. So again, I'm going to plug that. I will see if at some point I can put the link in when I have a spare chance. In the meantime, we are now at 20 minutes past 4 here in the UK. So we are at the last half an hour of our observations at Uranus. And unfortunately, this is our last day of observing on Uranus and live streaming at the same time. So if you have any key questions for today, it would be great if you can put them in the next 15-20 minutes, because we'll be starting to sign off as we get more towards 5 o'clock here in the UK. That's British summer time. I'm just going to have a quick look to see if on YouTube or if in Zoom we've had any extra questions. I see, Tom, thank you very much. You've been diligently working with YouTube questions. Thank you so much. Oh, okay, it's not really a question, but again, thank you so much. This I have from AC. Emma, best of luck on your research project and hoping for smooth sailing for your PhD and then further work. Great effort on your part in coordinating the presentation. It's also been a pleasure to remotely observe and greatly expand my knowledge on Uranus. Bye. Oh, thank you. Thank you so much. I appreciate all the well thoughts on that. I too also hope that there's smooth sailing for my PhD. So far, I would say so good. Obviously, that there has been a world pandemic, which wasn't in the job description, of course. But I don't think, Tom, you would have imagined that was going to happen either.
I really apologise for that.
So to my knowledge, it's not your fault.
Hope not.
So it's totally understandable. And I said, I too hope everything will work its way out. It's one of those fascinating ones. I stop for a moment. I'm just there like, it's weird to imagine in 10 years time, I'll be looking back at this and I don't know how things will have changed. They may be that I will still be doing the same things. Maybe I'll be doing something entirely different. It's crazy. It's crazy to think about, but it will happen. I'll be here. It'll be 2031. That's a weird concept to think of. It'll be 2031, and I will be here going, oh wow, my PhD years. I was doing, sat here. I was live observing Uranus, seeing what was going on, and one of the first people that were here to try and get the best resolution map that we've ever had for Uranus with the infrared, and also to enhance our understanding of what's going on at this planet. So yeah, it just blows my mind to think on that. Just seeing if we have any more. So I think there was a couple of questions though, Tom. I think you have answered most of these questions, so I may just be touching up on the same stuff unless there's anything you wanted to pull in. I did spot we have just Mark asking, do you all have Twitter handles we can follow? That's a good question. So I do have a Twitter handle, but I am afraid I sparsely use it. I mostly use it when I have a good observational film that I can show that looks interesting. Some of the observational films that I produce are quite naff, so they end up not being shown that much. But if I'm pleased enough in it, I'll send it. Otherwise, I tend to retweet and try and at least get the word out on other people's events, on work that they've done. But hopefully I might post one day, that I have graduated, and here's evidence of my graduation that may be there. But watch this space, because it'll be about 2 years time. I'll see if I can put that down. Now this is the issue, because I always can't spell physicist, despite the fact that I put it into my Twitter handle. So let's see if I've got this correctly. There we go. There we go. I hope by putting it in, I'm not going to end up with too much people coming along to hate on me, but we'll find out. Either way, that's my Twitter handle. I don't know if Tom or Rosie, you wanted to put in your own ones. If you don't, that's totally understandable.
Well, my main problem is I don't think I have one that I have the password for anymore. Desperately trying to get back into mine. Every time I try it, I can't find my way in. So
it's fine.
I don't really use Twitter so much, so I recommend following James O'Donoghue. Yes. And Henrik always also puts up a lot of nice GIFs whenever he does observing. So yeah.
Yeah, I think I should point out the film that we're currently seeing. Some way, I don't know which way the camera is, sorry. It very kindly, Henrik made the code for this, and I have simply just been the coding monkey that has just pressed enter and put all the images together to make the pretty pictures. So again, I want to stress that Henrik's diligent work has been with making these, and I hope that he will be able to put these movies up onto his Twitter account, because I wouldn't want to pretend that these are mine. These are definitely not made by me. I've tried my best. Mine are getting better, but they are not at the quality that Henrik has. So I will try and put James's and Henrik's Twitter handle in. Let's see if I can. No, that's the wrong James O'Donoghue. That is a rugby player. Oh dear, there we go. So James O'Donoghue is Physics J. So I'll just put that in. There we go. And Henrik is, let's see if I can get Henrik's up as well. Oh, no. There we go. Apologies on this, everyone. You're seeing live in action as I quickly try and Google and go through everything. There we go. So we have at physics with a capital J for James O'Donoghue, and at HMillen _ for Henrik Millen, who is one of our most diligent observers when it comes to Uranus. If you have any questions about infrared at Uranus, Henrik is a world-leading expert in that area. I saw that we have another question similar on this, which is, do we have Instagram handles? Unfortunately, I don't use Instagram. I'm terrible when it comes to photos. I know Lucinda was asking us kindly to send pictures of ourselves. Last picture I took of myself was back in first year to show other students what I looked like. And even then it wasn't a very good picture. It was me at 3 in the morning, so I looked very tired. I didn't look anything like what I feel like I didn't look like anything I looked like normally. So yeah, I open up to you too. Do you have any Instagram?
I can go better than you, Emma, on that. My last pictures on Instagram were from about May or April last year, when I was reaching peak madness, and
you did like a small like lockdown
I photographed
series.
my entire wall. I picked a wall of my house and photographed it in really minute detail. That's the only thing I've done for a year and a half.
Mentioned that because Katie said, "Have you seen Tom's Instagram? What's he doing?"
Yeah. It's what happens when you lock someone in a house for too long.
Yeah. Yeah, I don't use Instagram for work, so no, yeah, I barely use Twitter anymore anyway.
No worries.
I have a question in the Zoom chat. So, what questions would you look to have answered from a hopeful and eventual future mission to Uranus? Someone suggests having it bring a sample back from different layers, and they'd love to see scientists goes crazy to work on those.
Yeah, an atmospheric probe that went in would be really amazing. I think that could tell us some really interesting stuff about the top of the atmosphere. Certainly Galileo had a probe that tells us something interesting about the top. It tells us a lot more interesting stuff about deeper down. There's all sorts of mysteries further down that are very unusual. But I mean, it's got to be the magnetic field of Uranus and the aurora of Uranus, right? What can we answer about that environment? What drives the aurora? How do they work? That's something that I would love to be able to answer. And we can hopefully get better pictures of the aurora and get some inkling of that with James Webb and maybe with the work that we've been doing today. But ultimately, we need to go back with a magnetometer in orbit, and that will give us a much clearer picture of what the magnetic field lines are doing and help us deconstruct exactly what is driving these aurora.
Exactly. I mean, I concur with Tom. We're always going to be biased. We want to know. We're going to have these amazing pictures like we do at Jupiter and Saturn, where we're able to see the aurora, rather than going, here's 6 pixels which have been lit up, and that's probably the aurora that we do for Uranus. Yeah, I would love in my lifetime if we could have like a high definition version, but obviously that's for something in the future. I kind of want to, part of me is here thinking as well that we haven't discussed much about the moons. That would be great if we could actually see what moons off in the ice giants. This is more past Uranus, this is just Uranus and Neptune. It would be great to find out what's going on with moons so far out in our solar system, in comparison to the ones that we're seeing at Cassini, as well as with Juno at Jupiter and Saturn.
Yeah, I mean, you know, I'm a huge fan of Triton. I really want to see Triton around Neptune. I think it's a wonderful world. It's like a super Pluto. It's got all of the fun things that Pluto has and a whole lot more. So that would be great, but sticking with Uranus, because otherwise we'll talk about anything and everything all day. Does Ariel have volcanoes? Does Ariel have outgassing? There's lots of different ways we could answer that. We could maybe image them directly on the surface. We could maybe see the spouts coming up above the limb like we did with Io. We probably should be able to measure it with a magnetometer and measure the particles, or even directly measure the particles streaming off. Which is how we found out about Enceladus with Cassini. So a fully resourced mission to Uranus will help resolve that question in like a whole load of different ways, and it'll be a race between all of the different instruments to figure out who can answer it first, basically.
Rosie, do you have anything that you're looking forward to?
Well, mainly just the same. I don't think I can add anything on top of what you both said, to be honest. Yeah, my favorite thing is always the aurora, so just want to see that.
Yes, I think a possible another question would be, it would be interesting to see if there are any additional features that we're seeing with HT plus at Uranus, and I mean in the sense of like with the Great Red Spot, we're seeing some of the activity, some emissions from there. And again, touching a little bit, we've kind of gone into detail on parts, which is the ring rain that we're seeing at Saturn, which is, again, we've seen within HT+. And again, Uranus has its own rings, which again, we've been able to see in parts with our observations. I think it would be fascinating, especially when we get a stronger satellite.
That's a really interesting thing.
About that.
Yeah.
Good thoughts. My goodness. I just thought, can we answer that now? With what we've got now, we've got these wonderful spectra of Uranus. If we take all of our spectra and add it up, always taking the equator out and comparing it with the pole, we could measure how much dimmer the equator is than the pole, and provides some form of limitation on the amount of ring material coming off of the planet. That's an interesting
Emma, you got yourself
science
some more
idea.
homework.
I do. Oh dear.
That could be really good, because we could talk to Luke more about that and have
Yes.
him run through the model that he produced for Saturn, and get a constraint on what we think the level of destruction is on that. Well, that's your third chapter for you.
There we go. Yeah,
Oh, okay.
we are science in action. You're literally writing Emma's thesis.
Exactly. That's one of the nice things, I suppose, of the PhD is there's a lot of flexibility when it comes to the topics that you go for. When I first came to the PhD, I always thought it was like, okay, here is my plan, and I'm going to stick to this plan. And then you learn about 2 months in, actually the plan is a suggestion. And what actually happens is a lot more than what's on that plan. You may return back to that plan. You may go off it for about a couple of months and do something else. You may return back to it. You may find out the first year of your plan wasn't actually that helpful. And you're probably going to be using stuff in the last 2 years. It can really vary, and it's very fluid. So if anyone's looking for a PhD, it is, from what at first glance may seem like, oh, it's very studious, it's very serious business we're doing here. It's not. We're very flexible. Usually everyone's very, very cool. Usually your supervisor's very excited for you as well if you're, touching on something that no one's thought about before, that you really want to go in and investigate, So yes, sorry. So I can say thank you very much for this question. I think we have another one which leads into a little bit on the data analysis side, and I just want to highlight, so we're now at 4:30. We now have about 25 minutes left on the telescope at the moment. So the image that you're seeing with us at the moment of Uranus and the spectra will be up for another 25 minutes before we're going to be logging out from the telescope.
But seriously, Emma, we should ask James and Luke about that. I'm really excited.
It is noted, but I'm not going to write them an email right now. We can write them an email later.
Put a bookmark.
I'll put a bookmark in that. So we have from Paul Whitmarsh on YouTube asking, why is an A0 class star used as calibration star of choice rather than an F0 or a G0 class star?
So I was almost going to ask you that, Emma, then I thought it sounded a little bit like a Viva question.
Well, I can answer part of it, which is we use the A0 star because we can, oh goodness, I don't know how to quite explain this, because we use the Blackwell paper. That's the one that it comes up so many times in the references, which gives us an idea of how we can convert the observations that we're seeing. We can get an approximate on the flux or the intensity of a star, basically from this paper written back in, I want to say the mid 1900s, but I might be way off on that part. It's been a while since I've double checked on the year. It's an old paper, I know that much, but we can refer back to that paper, which gives us a good insight of, at a set temperature for a star, what the flux we should expect. And because, now this is the point where I may need Tom to step in a little bit, but my understanding is that A0 stars are relatively constant with the temperature side of things and the intensity. So we can assume that any A0 star that we're using is outputting the expected intensity that we would have. So if we have a known value for the intensity, we can essentially make a ratio between the CCD counts that we see on our spectra of a star and basically go, right, we've seen it at 223 CCD counts, and this equals to 1.7 times 10 to the something. Again, the numbers are eluding me at this point because apologies, this is our third day and I think my mind is slowly draining out as we get into the last half an hour, but we end up with a flux at the end of it, which we can then use to help define the intensity on Uranus, rather than having to use, basically we found 12 photons from Uranus at this set point. However, I will apologize because I am not that familiar with stars themselves. That is something that I'm sure when I get closer to my Viva, and as Tom said, a key Viva question almost, but why do we use the A naught star rather than F naught and G naught? That one I'm not as knowledgeable on.
Something to revise for sure.
Yeah, exactly.
I won't ask Rosie because I don't want to put someone who's already passed their Viva into trouble, because I think I know the answer to this. So I mean, there's a couple of reasons.
I'll test you, Tom.
You'll trust me. Okay, that's really good.
No, I'll test you.
You'll test me.
I'll tell you
Go.
if you're right.
Okay. So the main thing that we're doing, you're completely right. We want to test brightness, and all stars are pretty stable in terms of what we expect their brightness to be. You basically get a whole load of gas and you ram it together, and it's going to, the mass of the stuff that you've rammed together is going to drive a certain level of fusion of its hydrogen. Yeah, so you're going to have a good understanding of what your temperature and brightness are, no matter what. But depending on the type of star that you have, you're going to have all sorts of other emission lines as well trapped within that star. So the reason why AE naught stars are particularly useful is because they are one of the least interesting stars. They have much less in the way of those absorption lines, so it's much easier to get back to the pure, what we call black body. So basically what happens if you heat something up and it emits perfectly at a certain temperature, and so it allows us to have a really good picture. I'm also, if I remember rightly, it's all based around the Vega being a particularly bright A naught V star, and Vega has a constancy across its magnitudinal scale. So it's the same brightness at all wavelengths, which also makes the calculations much easier when we're comparing and contrasting, because it basically means we can compare with the brightness of Vega and do a very much easier job of the calibration calculations as well. How did it do, Rosie? B?
Yeah, I think you would pass your Viva.
C plus?
Yeah, definitely
Pass your,
A plus. A star.
Pass your surprise Viva. Awesome. Thank you so much for that, Tom, and thank you for your consideration there, Rosie. Tom's Viva. So I saw another really good question from YouTube. Again, I want to stress we are now on the last 20 minutes of observation. That is last 20 minutes of observing at Uranus. That is for the whole weekend. So we are not going to be coming back to Uranus at least for another 2 months. That's here for Leicester. And the question we have from Colin Maher, I believe. Again, apologies if I'm pronouncing people's names, surnames incorrectly. I can only apologize on that front. But they ask, are the aurora on Uranus visible, or are they limited to infrared observations? I'm happy to take this.
It's a good test. Let's go.
Yeah, this is an interesting test. I'm sure I'll say something and then we'll find out it's entirely different. But again, this probably points out this probably points out very well that whilst you're doing your PhD, there is a lot that you learn, and there's a lot of things that you think you understand, and then you'll come back to a couple of months later and you'll find, actually, no, I had the complete wrong idea on that. But that's good, because that is the only way that in science you're going to learn anything, is by keep refining and keep understanding. I mean, that's why we're doing these observations, is because we expect the infrared aurora to be at these set locations similar to that of the ultraviolet, but we haven't actually confirmed that yet. That's still something that we are ongoing analysis with. We just, as I said, we're hoping that they're going to be in the same position. So on that point, back in 1986, when we had Voyager 2 visit Uranus, we observed the ultraviolet aurora at Uranus. If you want to find those papers, I don't know if they're open access, that's the issue, as Tom was pointing out before, but there are some wonderful images that we get basically from the UVS instrument on board Voyager at the time, which basically detected photons at the ultraviolet spectrum that are emitting back off, and they were basically the first and only in situ image that we ever got showing both saw the southern and northern aurora, but they really showed us a fascinating view. Again, I can't fully show it on this image, but James did a wonderful animation which shows the rough positions that we have, the slits that we have. I tried to make a mock-up of the slit that's in the red box over the Uranus itself, but we saw that the aurora in the ultraviolet was at these very weird and wonderful locations. For anyone that wasn't here earlier, Uranus's aurora are really, really wacky. Unlike here at Earth, where we have the northern lights, and that's at the North Pole, and the southern lights, which are at the southern pole, Uranus's northern aurora actually covers a large majority of the northern hemisphere of Uranus and actually dips past the equator towards about 30 degrees south. It's really quite fascinating. So it's mind-boggling to imagine if you were here on Earth and you were at the equator and somebody would go, yeah, let's go see the northern lights tonight. That would be very easy to do at Uranus. In comparison, from a much larger northern aurora that we see at Uranus, we saw a much smaller, denser southern aurora at Uranus with those detections, which just puzzled us for a very long time, and has continued to puzzle us for pretty much a very, very long time. And that has been pretty much our key part of observing with Uranus. Has just been this ultraviolet detection. Since the detection in infrared, that was back in 1992, if I recall correctly. I think Professor Steve Miller was mentioning actually it was on the 1st of April, so it wasn't an April Fool's joke. We did find it at the time, and that has led to my area of research. But the investigation for detection has started back in the 1992, but it's actually not been entirely confirmed that we've seen the infrared aurora. I say hesitantly because I am currently writing a paper on this very topic at the moment. It still needs to go through reviews, and I can't show any of the work at the moment because, again, a lot on the science politics side of things. But we are hoping to show some of our work that discusses about this, but I can discuss about what Henrik has done, which he had previously back in 2 years ago, had shown a result where we saw a surprised localization. So what we mean by that is a peak of lights at the edge of the slit, which he was not expecting and he couldn't explain as something that we would expect on the planet itself. So the result from that, we were very excited that we had possibly seen the aurora coming into the slit, but unfortunately we weren't able to confirm that, as with infrared, the way that we go about confirming if we have the presence of aurora is by looking at the physical I say characteristics, but I mean in the sense of we look at the temperature. So again, that is looking at the ratio difference of the intensity of the lines. That's how bright the lines that we are seeing, to get an idea of the temperature that HT plus is when it emits, as well as looking at what is known as ion densities. That's the number of molecules that basically is in that environment. That gives us a great insight if it is something that is something internal, so something internally driven, like with weather, or if it is something external, such as the interaction of the solar wind with the magnetic field, which creates the aurora not only here at Earth, but at Uranus as well. And final comment, we had Dr. Will Dunn back on Friday discussing about the detection of X-rays at Uranus, which had been an ongoing investigation for many years with a lot of telescopes, where I think we got a whole 5 photons at Uranus, which doesn't sound like a lot, but it is one of those ones where the probabilities of showing that these 5 photons were only possible, I believe, in every 30,000 attempts of trying to do a random probability of if these 5 photons would all learn. Again, I may be getting that number wrong, and if I
think it was closer to 1 million.
There we
so
go.
1 in a million.
So that blows mine entirely out of the water.
So I mean, that's a very detailed answer to a question, but I don't think you've answered the question yet. The question Colin asked was, are there aurora on Uranus visible? Which would to me mean that we can see them with our eyes. So I don't know if you can answer that question.
I really like this question. It's one of my favorites.
It's a really good question.
I'm afraid I don't know if I can answer that one, because I don't recollect seeing any papers that specifically talk about us seeing the visible
So
Aurora,
we've never
but
seen the
that's-
visible aurora.
yeah.
We know that we can see visible aurora at gas giants. We've got these beautiful images from Cassini and from Galileo looking at these arcs of emission on the night side of Jupiter and Saturn. So you can definitely see aurora in the visible. The color of those aurora is a little bit difficult to figure out, but we think that they're probably pinky purple in color. They're basically hydrogen emission lines, and it's very similar to the kind of emission you see at Earth, but it's green at Earth because it's oxygen. You also get some red oxygen lines, and you also get some red nitrogen lines. And it happens that in the visible wavelengths that our eyes have evolved to see, the strongest lines are a combination of atomic hydrogen and molecular hydrogen lines that are in that kind of range. So there is a greenish line, but then there's also more of those reddish, purplish lines coming through from molecular hydrogen. So that's why we think what we see, and we've definitely got spectral measurements of those at Jupiter and Saturn. So it tells us not only that we see them, because the images we take are usually open images, so it's the whole of the visible taking data. We've never seen anything like that from Uranus, but what we do know, as you know, is we've got UV emission, and those UV emissions come from hydrogen. So the hydrogen emission lines that we see, the Lyman alpha atomic hydrogen and the molecular hydrogen lines that we were able to observe in the UV are part of a suite of lines. So, you know, you've got a whole set of higher energy lines that are more common, and then the higher order lines, the Balmer lines, all come in the visible. So we're almost certain that there will be auroral lines falling in the visible, because we know from the other planets that we have those visible lines as a direct matching. They'll be weak. We won't be able to see them on the day side. So no observations we ever take from Earth, or no matter how large a telescope we have, we'll ever see them, because they'll be swamped out by all of the atmospheric weather. But one of the things that we hoped to do with the Triton mission when we were going past Neptune was to try and look for those lines with the visible camera. Now, obviously, much more preferable to have a UV instrument. Triton was a very, very stripped down flyby instrument, so we made it as light as we possibly could, but hopefully a much larger, more powerful instrument. We'll have a whole suite of instruments that will allow us to study in detail in the UV, but also see images of those narrow arcs in the visible. But we have no idea what we'll see, because we don't know what the aurora looks like at any wavelength, as you said. But yeah, hopefully they will be there, and we will see them when we get back there at some point in the 2040s or beyond.
Exactly. Oh, wonderful. Sorry. Thank you very much, Tom. Yeah, I did go off on a bit of a tangent there. I suppose it's showing the information that is in my head, but at the same time, there's still a little bit more to keep in there and still ascertain for further knowledge for the Viber that ever looms for closer and closer. So we are now at the last 12 minutes or so. I'm just trying to think if there's anything else that we should cover as we're wrapping up here.
Will we be? How much longer will be on Uranus? Because did you say it's only really like 5 minutes ish?
Yes.
Now?
I think we've actually
6
stopped. I think we've
Okay,
finished on Uranus now, and they're taking the calibration frames.
Yep.
So I think that we're basically done. I'll just have a look and see. I think the guide camera is also stopped. Yes.
Yes, I believe it is. So unfortunately, we have now stopped with our live images. I have gone to yesterday's short looping clip of what we were seeing with Uranus. So thankfully, Nahid, who is currently operating, is now getting those calibrations. So if you remember before, I was discussing about the calibration box. So we are now getting those flat fields, dark fields, and they are what we need to be able to hopefully reduce our data. And what I mean by that is essentially going along with a dustpan and brush and cleaning away our data for any dead pixels, for any inconsistencies, so that we can adjust for those in our data. Unfortunately, in the process of doing that, it can be quite blinding, so I have shifted over to another slide to avoid blinding anyone in the process. So we now have the, I believe, last 10 minutes of the live streams. We're finishing up here at 5 o'clock British summer time here in the UK. If we have any last questions for us, as I believe we won't be on, I'm not sure when we'll next be on RAS. It would be wonderful when we next can be, but at the moment I don't know if we have anything for this year.
We'll be back,
yes.
but not this year.
Exactly. So of course, it'll be lovely to re-come back, but we do hope everyone has a lovely couple of months whilst they may not hear much from us from the HT Plus team. We will, of course, be trying to put out papers and discussions and possibly live streams and any other appearances we will be about. But in terms of our observations, I think this will be the last time that we will be doing our observations this year live streamed, to my knowledge. We do have another set of observations. We may do that ourselves, I think, possibly live stream. We've tried it once on Twitch, but it is... Twitch is an interesting time trying to do observations on. There isn't actually an observing tag that you can put on Twitch because Twitch is more affiliated with the gaming side of things, but we can, we'll have a look. Perhaps it's something that we'll investigate with YouTube, but watch this space, I suppose, for what may go on. So I'm just thinking if we have any final comments from Rosie and Tom. Do you have any final comments you want to add for today or for the last 3 days or anything in particular?
Well, just to reiterate that it's such a joy to be able to share this with everyone out there, because this is the best bit of our job that we do. Tomorrow morning I'll be lecturing mechanics into first years. That's not going to be as fun as doing this. So hopefully, you can get a sense and a grasp of why we enjoy doing these observations so much, and how, this is basically the grindstone that we grind our daily bread out of. This is the science that we do to, try and explore and understand the universe a little bit better. And it's great to be able to do big press releases with fantastic and wonderful results, but it all starts here with just long, slow staring at objects very distant in the sky.
Thank you so much, Tom. I believe Nahid has mentioned if you wanted to head back over just to do some experimentation with carbon.
Yeah, I'm going to play around and try and improve things, but I'll stick around till we're done here before I do that.
So Rosie, I was going to ask, do you have any closing remarks that you wish to put out there for the audience today?
Just the same as Tom, really. Observing is one of the highlights of the job, and I just like how practical it is and how different it is to the rest of the other roles that we have in our jobs. And yeah, it is really nice to show everyone what it is we do, because quite a lot of my friends will think that we're looking through the telescope, so it's really fun to be able to actually show the data and explain a bit more about what we do. And
sorry, just bear with me, I'm just responding to that, but thank you very much, Rosie, on that part. Sorry, there we go. Seeing live as I am, trying to respond back and sort things. So I guess that kind of just leaves myself. So I have my own closing remarks, which of course I want to say thank you so much to everyone that has joined us. It is crazy to think that there's been so many people. I know Lucinda mentioned on, I think, Saturday that our Friday video got 2.8 thousand views, and that is one day. That blew my mind that there had been so many people who are interested, and it's so mind-blowing the amount of engagement we get from people. It is very heartwarming, the amount of engagement, because sometimes you'll be doing these kinds of results and you're just there like, well, I find this really, really cool, and a lot of my colleagues find this cool, but if I ask the average Joe, they'll probably be like, well, why are you wasting your time doing that? Why aren't you trying to help with everything that's going on in the world at the moment? Like, can't you use your time doing something else? So it's really heartwarming having so many people coming along and engaging and asking questions, and perhaps even being people who can now, not, I wouldn't say advocate, but in the sense of being people that perhaps you may have people who go, oh, you observed, like you were part of the observations on Uranus, were you? Like you were in that audience. Can you let me know on anything that's going on? And you'll be able to pass on the knowledge that we've been saying today, not only from ourselves, but from our lovely panel of speakers that we've had this week. We've had such a large array. Of course, I want to thank every single one of our speakers that came along all the way through the week. So we've had Dr. Lee Fletcher, we've had Dr. Will Dunn, we have had obviously Dr. Sean Prosser, as well as, oh goodness, there's Charles, but I'm trying to remember full names here. So I'm going to make sure I have got correct names. So let me just make sure on this one. With Charles, again, I greatly apologize. Yes, so with Charles Draper for coming along, we had Dr. James O'Donoghue join us on Saturday, along with Dr. Heidi Hamill, as well as, I believe, Dr. or Professor, I would need to confirm that, but I believe Dr. Elizabeth Tasker. And today with the Bath astronomers, we had Simon along with Jonathan Hall join us from the Herschel Museum. Of course, we had our lovely speakers. We've had Dr. Sarah Casewell and Dr. Rosie Johnson all give their lovely talks today, and really inspiring us all on the types of research that's going on in our solar system.
Yeah, big highlight for all of us was Heidi Hamill coming. That was amazing.
Blew our minds. She is such a world expert, really, in her own fields, and so many fascinating stories. So we are now here about 4 minutes or so. We want to say again a big thank you to everyone that has come along today. We greatly appreciate all your enthusiasm, your questions that you have given us today. I quickly just want to mention the closing remarks we have from Lucinda regarding today's. So Lucinda has written that on behalf of RAS, the Royal Astronomical Society, Lucinda would love to thank Tom, whose decision it was to ask us again to collaborate with the HT Plus team. And of course to Emma, who has had the courage to share her observation experience with us all. Thank you as well to the rest of the HT Plus team, as it is obvious that this has been a success because of the help and the skills of a lot of people. And again, I want to highlight that part. Nahid and Riyang, we are so thankful for your patience in the last 3 days. You have been incredible stars. I'm going to use that pun, but we always do with space. You've been stars when it comes to these observations. These kinds of data would not be possible with those in the background that have to diligently work without getting much of the fun FaceTime that we're doing at the moment. Again, I also want to thank Luke Moore and Omakshi, who came in on Saturday as well, and so very kindly sat in for many hours, I think 2-3 in the morning for them. So again, we want to thank them for coming in at those god-awful hours. We want to thank you to the Royal Astronomical Society for allowing Lucinda to produce this event with the HT Plus team. They have not only brought in brilliant speakers and contributions, but have shared the hosting with us during this 3-day observations. Also, a huge thanks to Lucinda's colleague, Dr. Sean Prosser, the Herschel Museum, the Herschel Society, for sharing all of their historical knowledge of the Herschels with us to inspire future astronomers. Again, congratulations, I think. Sorry, bear with me, going through this. Congratulations to Emma. We wish her all the success as a professional astronomer and the breakthroughs that you may bring. Thank you for being our woman in space to help us contribute to World Space Week and sharing your research and weekend with us.
and for an inside look at a PhD astronomer's life. And that is from Lucinda Offer, Education, Outreach and Events Officer, and HC Plus's biggest fan, as she had written, which again, we thank you so much. Again, Lucinda, without having your help and work this weekend, none of this would have been possible. So again, we're so thankful for your time, your patience, and the number of hours that you've been putting into this. Again, this would not be possible without yourself. We are now at 1 minute to 5, so we'll start looking to pack up. So again, thank you so much, everyone. Thank you for your time. Thank you for your patience. We hope to watch this space to see what kind of science will be coming out from the University of Leicester. And if you do see us in person, you're always welcome to ask what happened. It may end up being an awkward question. It may end up being a very interesting question. We may end up going on for hours and hours on end. But please do feel free to ask those questions to us. Again, we've put some of our Twitter handles in, but you can be found about on the web. So do feel free to poke us if you see us. Awesome, wonderful. Thank you so much, everyone. This is us signing off from the HT Plus team. You've been a wonderful audience, and we look forward to hearing from some of you soon, or we look forward to at least expressing some of our research soon. Take care all. We look forward to seeing you again